But let me ask that you also had a very interesting, and we talked about rich representations. You had a rich life journey. Uh, you did your bachelor's in China and your master's and PhD in the United States, CMU in Berkeley. Are there interesting differences? I told you I'm Russian. I think there's a lot of interesting difference between Russia and the United States. Are there, in your eyes, interesting differences between the two cultures, from the silly romantic notion of the spirit of the people to the more practical notion of how research is conducted, that you find interesting or useful in your own work of having experienced both?
That's a good question. I think so. I studied in China for my undergraduate, and that was more than 20 years ago. So it's been a long time.
Is there echoes of that time in you?
Things have changed a lot.
Yes.
Actually, it's interesting. I think even more so, maybe something that's even maybe more different from my experience than a lot of computer science researchers and practitioners is that, so for my undergrad, I actually studied physics.
Nice. Very nice.
And then I switched to computer science in graduate school.
What happened? Is there another possible universe where you could have become a theoretical physicist at Caltech or something like that?
That's very possible. Some of my undergrad classmates, then they later on studied physics, got their PhD in physics from these schools, from top physics programs.
So you switched to, I mean, from that experience of doing physics in your bachelor's, what made you decide to switch to computer science, and computer science at arguably the best university, one of the best universities in the world for computer science, with Carnegie Mellon, especially for the grad school and so on. So what, second only to MIT, just kidding. Okay. I had to throw that in there. No, what was the choice like, and what was the move to the United States like? What was that whole transition? And if you remember, if there's still echoes of some of the spirit of the people of China in your work.
Right.
It's like three questions in one.
Yes, I know.
I'm sorry.
No, that's okay. So yes, so I guess, okay, so first transition from physics to computer science.
Yes.
So when I first came to the United States, I was actually in the physics PhD program at Cornell.
Yeah.
I was there for 1 year, and then I switched to computer science, and then I was in the PhD program at Carnegie Mellon. So the reasons for switching. So one thing, so that's why I also mentioned that about this difference in backgrounds, about having studied physics first in my undergrad. I really did enjoy my undergrad's time and education in physics. I think that actually really helped me in my future work in computer science. Actually, even for machine learning, a lot of machine learning stuff, the core machine learning methods, many of them actually came from physics. Statistical.
So, for honest, most.
But anyway,
most of everything came from physics.
Right. But anyway, so when I studied physics, I was I think I was really attracted to physics. It's really beautiful. And I actually call it physics is the language of nature. Mm. And I actually clearly remember like one moment in my undergrads, like I did my undergrad in Tsinghua, and I used to study in the library. And I clearly remember like one day I was sitting in the library, and I was like writing on my notes and so on. And I got so excited that I realized that really just from a few simple axioms, a few simple laws, I can derive so much. It's almost like I can derive the rest of the world.
Yeah, the rest of the universe.
Yes. So that was like amazing.
Do you think have you ever seen, or do you think you can rediscover that kind of power and beauty in computer science in the world that
that's very interesting. So that gets to, the transition from physics to computer science. It's quite different. for physics in grad school, actually things changed. So one is I started to realize that when I started doing research in physics, at the time I was doing theoretical physics, and a lot of it, you still have the beauty, but it's very different. So I had to actually do a lot of the simulation. So essentially, I was actually writing, in some cases, writing Fortran code.
Good old Fortran, yep.
To actually do simulations and so on. That was not exactly
not beautiful.
Right. I enjoyed doing. And also at the time, from talking with the senior, students in the program, I realized many of the students actually were going off to like Wall Street and so on. So, and I've always been interested in computer science, and actually, essentially taught myself the C programming, like
program,
right, and so on.
When?
In college.
In college somewhere?
In the summers.
For fun. Physics major, learning to do C programming. Beautiful.
Actually, it's interesting, in physics, at the time, I think now the program probably has changed, but at the time, really the only class we had in related to computer science education was introduction to computer science or computing, and Fortran 77.
There's a lot of people that still use Fortran. I'm actually, if you're a programmer out there, I'm looking for an expert to talk to about Fortran. They seem to, there's not many, but there's still a lot of people that still use Fortran, and still a lot of people that use Cobalt. So,
but anyway, so then I realized, instead of just doing programming for doing simulations and so on, then I may as well just change to computer science. And also one thing I really liked, and that's a key difference between the two, is in computer science, it's so much easier to realize your ideas. If you have an idea, you write it up, you code it up, and then you can see it actually, right?
Exactly.
Running, and you can see it.
You can bring it to life quickly.
Bring it to life. Whereas in physics, if you have a good theory, you have to wait for the experimentalists to do the experiments and to confirm the theory, and things just take so much longer. And also the reason in physics I decided to do theoretical physics was because I had my experience with experimental physics. First, you have to fix the equipment.
Yeah.
You spend most of your time fixing the equipment first. So
super expensive equipment. So there's a lot of you have to collaborate with a lot of people. It takes a long time.
Just takes really much longer.
Yeah, it's messy.
So I decided to switch to computer science. And one thing I think maybe people have realized is that for people who study physics, actually, it's very easy for physicists to change to do something else.
Yes.
I think physics provides a really good training. And so actually it was very easy to switch to computer science. But one thing, going back to your earlier question, so one thing I actually did realize, so there is a big difference between computer science and physics, where physics you can derive the whole universe from just a few simple laws. And computer science, given that a lot of it is defined by humans, the systems are defined by humans, and it's artificial, essentially you create a lot of these artifacts and so on. It's not quite the same. You don't derive the computer systems with just a few simple laws. You actually have to see there's historical reasons why a system is built and designed one way versus the other.
There's a lot more complexity, less elegant simplicity of E equals MC squared that kind of reduces everything down to those beautiful fundamental equations. But what about the move from China into the United States? Is there anything that still stays in you that's contributes to your work? The fact that you grew up in another culture?
So yes, I think especially back then it's very different from now. So, now I see these students coming from China, and even undergrads, actually they speak fluent English. It was just, amazing. and they have already understood so much of the culture in the US and so on. And
it was all foreign. It was
a very different time. At the time, actually, even we didn't even have easy access to email.
Right.
Not to mention about the web.
Yeah.
I remember I had to go to, specific, privileged server rooms to use email.
Yeah.
Right. And hence, at the time, we had much less knowledge about the Western world. And actually, at the time, I didn't know, actually, the in the US, the West Coast weather is much better than the East Coast. Yeah, things like that, actually. It's very interesting.
Yeah.
But now it's so different. At the time, I would say there's also a bigger cultural difference because there's so much less opportunity for shared information. So it's such a different time and world.
So let me ask, we've talked about it a million times, but let's try to sort of do that old basic terminology definitions. What is panpsychism? Like, what are the different ways you can try to think about, to define panpsychism, maybe in contrast to naturalistic dualism and materialism, and other kind of views of consciousness?
Yeah, so that you've basically laid out the different options. So I guess probably still the dominant view is materialism, that roughly that we can explain consciousness in the terms of physical science, wholly explain it just in terms of the electrochemical signaling in the brain. Dualism, the polar opposite view, that consciousness is non-physical, outside of the physical workings of the body and the brain, although closely connected. And, when I studied philosophy, we were taught, basically they were the two options you had to choose, right? Either you thought you were dualist and you thought it was separate from the physical, or you thought it was just electrochemical signaling. And yeah, I became very disillusioned because I think there are big problems with both of these options. So I think the attraction to panpsychism is it's kind of a middle way. It agrees with the materialist that there's just a physical world. Ultimately, there's just particles and fields. But the panpsychist thinks there's more to the physical than what physical science reveals, and that the ultimate nature of the physical world is constituted of consciousness. So consciousness is not outside of the physical, as the dualist thinks. It's embedded in, underlies the kind of description of the world we get from physics.
What to you are the problems of materialism and dualism?
Starting with materialism, it's a huge debate, but I think that the core of it is that physical science works with a purely quantitative description of the physical world, whereas consciousness essentially involves qualities. If you think about the smell of coffee or the taste of mint or the deep red you experience as you watch a sunset, I think these qualities can't be captured in the purely quantitative language of physical science. And so as long as your description of the brain is framed in the purely quantitative language of neuroscience, you'll just leave out these qualities and hence really leave out consciousness itself.
And then dualism?
So I've actually changed my mind a little bit on this since I wrote the book. So, I argued in the book that we have pretty good experimental grounds for doubting dualism. And roughly the idea was, if dualism were true, if there was, say, an immaterial mind impacting on the brain every second of waking life, that this would really show up in our neuroscience. There'd be all sorts of things happening in the brain that had no physical explanation. It would be like a poltergeist was playing with the brain. But actually, and so the fact that we don't find that is a strong and ever-growing inductive argument against dualism. But actually, the more I talk to neuroscientists and read neuroscience, and we have at Durham, my university, an interdisciplinary consciousness group, I don't think we know enough about the brain, about the workings of the brain to make that argument. I think we know a lot about the basic chemistry. how neurons fire, neurotransmitters, action potentials, things like that. We know a fair bit about large-scale functions of the brain, what different bits of the brain do. But what we're almost clueless on is how those large-scale functions are realized at the cellular level, how it works. People get quite excited about brain scans, but it's very low resolution. Every pixel on a brain scan corresponds to 5.5 million neurons, and we're only 70% of the way through constructing a connectome for the maggot brain, which has, is it 10,000 or 100,000 neurons? But the brain has 86 billion neurons. So I think we'd have to know a lot more about how the brain works, how these functions are realized, before we could assess whether the dynamics of the brain can be completely explicated in terms of underlying chemistry or physics. So, we'd have to do more engineering before we could figure that out. And there are people with other proposals. Someone I got to know, Martin Picard at Columbia University, who has the psychobiology mitochondrial lab there and is experimentally exploring the hypothesis that mitochondria in the brain should be understood as sort of social networks, perhaps as an alternative to reducing it to underlying chemistry and physics. So I'm less... It is ultimately an empirical question whether dualism is true. I'm less convinced that we know the answer to that question at this stage. I think still, as scientists and philosophers, we want to try and find the simplest, most parsimonious theory of reality. And dualism is still a pretty inelegant, unparsimonious theory. Reality is divided up into the purely physical properties and these consciousness properties, and they're radically different kinds of things. Whereas the panpsychist offers a much more simple, unified picture of reality. So I think it's still the view to be preferred. To put it very simply, why believe in two kinds of thing when you can just get away with one?
And materialism is also very simple, but you're saying it doesn't explain something that seems pretty important.
Yeah, so I think materialism can't, science is about trying to find the simplest theory that accounts for the data. I don't think materialism can account for the data. Maybe dualism can account for the data, but panpsychism is simpler. It can account for the data, and it's simpler.
What is panpsychism?
So in its broadest definition, it's the view that consciousness is a fundamental and ubiquitous feature of the physical world.
Like a law of physics? What should we be imagining? What do you think the different flavors of how that actually takes shape in the context of what we know about physics and science and the universe?
So in the simplest form of it, the fundamental building blocks of reality, perhaps electrons and quarks, have incredibly simple forms of experience, and the very complex experience of the human or animal brain is somehow rooted in or derived from these very simple forms of experience at the level of basic physics. But I mean, maybe the crucial bit about the kind of panpsychism I defend, what it does is it takes the standard approach to the problem of consciousness and turns it on its head, right? So the standard approach is to think, we start with matter and we think, how do we get consciousness out of matter? So I don't think that problem can be solved for reasons I've kind of hinted at. We could maybe go into more detail. But the panpsychist does it the other way around. They start with consciousness and try to get matter out of consciousness. So the idea is basically, at the fundamental level of reality, there are just networks of very simple conscious entities. But these conscious entities, because they have very simple kinds of experience, they behave in predictable ways. Through their interactions, they realize certain mathematical structures. And then the idea is those mathematical structures just are the structures identified by physics. So when we think about these simple conscious entities in terms of the mathematical structures they realize, we call them particles, we call them fields, we call their properties mass, spin, and charge. But really, there's just these very simple conscious entities and their experiences. So in this way, we get physics out of consciousness. I don't think you can get consciousness out of physics, but I think it's pretty easy to get physics out of consciousness.
Well, I'm a little confused by why you need to get physics out of consciousness. I mean, to me, it sounds like panpsychism unites consciousness and physics. I mean, physics is the mathematical science of describing everything. So physics should be able to describe consciousness. Panpsychism, in my understanding, proposes is that physics doesn't currently do so, but can in the future. I mean, it seems like consciousness. You have like Stephen Wolfram, who's all these people who are trying to develop theories of everything, mathematical frameworks within which to describe how we get all the reality that we perceive around us. To me, there's no reason why that kind of framework cannot also include some accurate, precise description of whatever simple consciousness characteristics are present there at the lowest level, if panpsychist theories have truth to them. So, like, to me, it is physics. You said kind of physics emerges, by which you mean like the basic four laws of physics that, as we currently know them, the standard model, quantum mechanics, general relativity, that emerges from the base consciousness layer. That's what you mean.
Yeah, so maybe the way I phrased it made it sound like these things are more separate than they are. What I was trying to address was a common misunderstanding of panpsychism, that it's a sort of dualistic theory. The idea is that particles have their physical properties like mass, spin, and charge, and these other funny consciousness properties. So that the physicist Sabine Hossenfelder had a blog post critiquing panpsychism maybe a couple of years ago now that got a fair bit of traction, and she was interpreting panpsychism in this way, and then her thought was, well, look, if particles had these funny consciousness properties, then it would show up in our physics, like the standard model of particle physics would make false predictions because its predictions are based wholly on the physical properties. If there were also these consciousness properties, we'd get different predictions. But that's a misunderstanding of the view. The view is, it's not that there are two kinds of property, that mass, spin, and charge are forms of consciousness. How do we make sense of that? Because actually, when you look at what physics tells us, it's really just telling us about behavior, about what stuff does. I sometimes put it by saying doing physics is like playing chess when you don't care what the pieces are made of. You're just interested in what moves you can make. So physics tells us what mass, spin, and charge do, but it doesn't tell us what they are. So the idea...
the experience of mass.
So the idea is, mass in its nature is a very simple form of consciousness. So physics in a sense is complete, I think, because it tells us what everything at the fundamental level does. It describes its causal capacities. But for the panpsychist, at least, physics doesn't tell us what matter is. It tells us what it does, but not what it is.
To push back on the thing I think she's criticizing, is it also possible, so I understand what you're saying, but is it also possible that particles have another property like consciousness? I don't understand the criticism we would be able to detect it in our experiments. Well, no, if you're not looking for it. I mean, there's a lot of stuff that are orthogonal. Like, if you're not looking for the stuff, you're not going to detect it, because like all of our basic empirical science through its recent history, and yes, the history of science is quite recent, has been very kind of focused on billiard balls colliding, and from that understanding how gravity works. But like, we just haven't integrated other possibilities into this. I don't think there will be conflicting, whether you are observing consciousness or not, or exploring some of these ideas. I don't think that affects the rest of the physics, the mass, the energy, all the different kind of like the hierarchy of different particles and so on, how they interact. I don't think it feels like consciousness is something orthogonal, like very much distinct. It's the quantitative versus the qualitative. There's something quite distinct that we're just almost like another dimension that we're just completely ignoring.
There might be a way of responding to Sabine and to say, well, that there could be properties of particles that don't show up in the specific circumstances in which physicists investigate particles. My colleague, the philosopher of science, Nancy Cartwright, has got this book, How the Laws of Physics Lie, where she says, physicists explore things in very specific circumstances and then in an unwarranted way generalize that. But I mean, I guess I was thinking Sabine's criticism actually just misses the mark in a more basic way. Her point is we shouldn't think there are any more properties to particles other than those the standard model attributes to them. Panpsychists would say, yeah, sure, there aren't. There are just the properties, the physical properties like mass, spin, and charge that the standard model attributes to them. It's just that we have a different philosophical view as to the nature of those properties.
So those properties are turtles. They're sitting on top of another turtle, and that big turtle is consciousness. That's what you're saying. But I'm just saying I don't. It's possible that's true. It's possible also that consciousness is just another turtle playing with the others. Like it's just not interacting in the ways that we've been observing. In fact, to me, that's more compelling because then that's going to be. Well, no, I think both are very compelling, but it feels like it's more within the reach of empirical validation if it's yet another property of particles that we're just not observing. If it's like the thing from which matter and energy and physics emerges, like it makes it that much more difficult because to investigate how you get from that base layer of consciousness to the wonderful little spark of consciousness, complexity, and beauty that is the human being. I don't know if you're necessarily trying to get there, but one of the beautiful things to get at with panpsychism or with a solid theory of consciousness is to answer the question, how do you engineer the thing?
Yeah.
How do you get from nothing, vacuum in the lab, if there is that consciousness base layer, how do you start engineering organisms that have consciousness in them?
Yeah.
Or the reverse of that, describing how does consciousness emerge in the human being from conception, from a stem cell to the whole full neurobiology that builds from that. How do you get this full, rich experience of consciousness that humans have? It just, it feels like that's the dream. And if consciousness is just another player in the game of physics, it feels more amenable to our scientific understanding of it.
That's interesting. I mean, I guess it's supposed to be a kind of identity claim here that physics tells us what matter does. Consciousness is what matter is. So matter is sort of what consciousness does. So at the bottom level, there is just consciousness and conscious things. There are just these simple things with their experiences, and that is their total nature. So in that sense, it's not another player. It's just all there is, really. And then in physics, we describe that at a certain level of abstraction. We capture what Bertrand Russell, who was the inspiration for a lot of this, calls the causal skeleton of the world. So, physics is just interested in the causal skeleton of the world. It's not interested in the sort of flesh and blood, although that's maybe suggesting separation again too much. All metaphors fail in the end. But, so you're totally right. Ultimately, what we want to explain is how our consciousness and the consciousness of other animals comes out of this. If we can't do that, then it's game over. But I think it maybe makes more sense on the identity claim that if matter at the fundamental level just is forms of consciousness, then we can perhaps make sense of how those simple forms of consciousness in some way combine in some way to make the consciousness we know and love. That's the dream.
Yeah, so I guess the question is, so the reason you can describe, like the reason you have material engineering, material science, is because you have from physics to chemistry, like you keep going up and up in levels of complexity in order to describe objects that we have in our human world. And it would be nice to do the same thing for consciousness, to come up with the chemistry of consciousness, right? Like how do the different particles interact to create more greater complexity? So you can do this kind of thing for life. Like, what is life? Well, like living organisms. Well, at which point do living organisms become living? How do you know if I give you a thing that thing is living? And there's a lot of people working on this kind of idea, and some of it has to do with the levels of complexity and so on. It'd be nice to know, like, measuring different degrees of consciousness as you get into a bigger, more and more complex objects. And that's what chemistry, like bigger and bigger conscious molecules, and to see how that leads to organisms. And then organisms like start to collaborate together like they do inside a human body to create the full human body. To do those kinds of experiments would be, that it seems like that would be kind of a goal. That's what I mean by player in a game of physics, as opposed to like the base layer. If it's just the base layer, it becomes harder to track it as you get from physics to chemistry to biology to psychology.
Yeah. In every case, apart from consciousness, I would say what we're interested in is behavior.
Yeah.
We're interested in explaining behavioral functions. So at the level of fundamental physics, we're interested in capturing the equations that describe the behavior there. And when we get to higher levels, we're interested in explicating the behavior, perhaps in terms of behavior at simpler levels. And with life as well, that's what we're interested in, the various observable functions of life, explaining them in terms of more simple mechanisms. But in the case of consciousness, I don't think that's what we're doing, or at least not all that we're doing. In the case of consciousness, there are these subjective qualities that we're immediately aware of, the redness of a red experience, the itchiness of an itch, and we're trying to account for them. We're trying to bring them into our theory of reality, and postulating some mechanism does not deal with that. So I think we've got to realize dealing with consciousness is a radically different explanatory task from other tasks of science. Other tasks of science, we're trying to explain behavior in terms of simpler forms of behavior. In the case of consciousness, we're trying to explain these invisible subjective qualities that you can't see from the outside, but that you're immediately aware of. The reason materialism perhaps continues to dominate is people think, look at the success of science, it's incredible, look at all the, it's explained all this, surely it's going to explain consciousness. But I think we have to appreciate there's a radically different explanatory task here. And so the neuroscientist Anil Seth, who I've had lots of intense but friendly discussions with, wants to compare consciousness to life. But I think there's this radical difference that in the case of life, again, we come back to public observation. All of the data are publicly observable data. We're basically trying to explain complex behavior. And the way you do that is identify mechanisms, simpler mechanisms that explicate that behavior. That's the task in physics, chemistry, neurobiology. But in the case of consciousness, that's not what we're trying to do. We're trying to account for these subjective qualities, and you postulate a mechanism that might explain behavior, but it doesn't explain the redness of a red experience. So, but still ultimately the hope is that we will have some kind of hierarchical story. So we take the causal dynamics of physics, we hypothesize that that's filled out with certain forms of consciousness, and then at higher levels we get more complex causal dynamics filled out by more complex forms of consciousness, and ultimately we get to us, hopefully. So there's still a sort of hierarchical explanatory framework there.
So you kind of mentioned the hierarchy of consciousness. Do you think it's possible to, within the panpsychism framework, to measure consciousness? Or put another way, are some things more conscious than others in the panpsychist view?
It's a difficult question. I do see consciousness as dealing with consciousness an interdisciplinary task between something more experimental, which is to do with the ongoing project of trying to work out what people call the neural correlates of consciousness, what kinds of physical brain activity correspond to conscious experience. That's one part of it, but I think essentially there's also a theoretical question of more the why question. Why do those kinds of brain activity go along with certain kinds of conscious experience? I don't think you can answer that. Because consciousness is not publicly observable, I don't think you can answer that why question with an experiment. But they have to go hand in hand. And I mean, one of the theories I'm attracted to is the integrated information theory, according to which we find consciousness at the level at which there is most integrated information, and they try to give a mathematically precise definition of that. So on that view, probably this cup of tea isn't conscious because there's probably more integrated information in the molecules making up the tea than there is in the liquid as a whole. But in the brain, what is distinctive about the brain is that there's a huge amount of there's more integrated information in the system than there is in individual neurons. So that's why they claim that that's the basis of consciousness at the macro level. Now I like some features of this theory, but they do talk about degrees of consciousness. They do want to say there is gradations. I'm not sure conceptually I can kind of make sense of that. I mean, there are things to do with consciousness that are graded, like complexity or levels of information, but I'm not sure whether experience itself admits of degree. I sort of think something either has experience or it doesn't. It might have very simple experience, it might have very complex experience, but experience itself, I don't think it admits of degree in that sense. It's not more experience, less experience. I sort of find that conceptually hard to make sense of. But I'm kind of open-minded on it.
So when we have a lot higher resolution of sensory information, don't you think that's correlated to the richness of the experience? So doesn't more information provide a richer experience? Or is that, again, thinking quantitatively and not thinking about the subjective experience? Like you can experience a lot with very little sensory information, perhaps. Like, do you think those are connected?
Yeah. So there are features, characteristics here we can grade the complexity of the experience, and on the integrated information theory, they correlate that in terms of mathematically identifiable structure with integrated information. So roughly, it's a quite unusual notion of information. It's perhaps not the standard way one thinks about information. It's to do with constraining past and future possibilities of the system. So the idea is in the retina of the eye, there's a huge amount of possible states the retina of my eye could be in at the next moment, depending on what light goes into it. Whereas the possible next states of the brain are much more constrained. Obviously, it responds to the environment, but it heavily constrains its past and future states. And so that's the idea of information they have. And then the second idea is how much that information is dependent on integration. So in a computer where you have transistors, you take out a few transistors, you might not lose that much information. It's not dependent on interconnections. Whereas you take a tiny bit of the brain out, you lose a lot of information because the way it stores information is dependent on the interconnections of the system. So so that's one proposal for how to measure one gradable characteristic which might correspond to some gradable characteristic in qualitative consciousness. And maybe I'm being very pedantic, which is, philosopher's professional pedant. I just sort of don't think that is a quantity of experience. It's a quantity of the structure of experience, maybe, but I just find it hard to make sense of the idea of how much experience do you have? I've got, 5 units of experience. I've got 1 unit of experience. I don't know. I find that a bit hard to make sense.
Well,
but maybe I'm being just pedantic.
I think just saying the word experience is difficult to think. So it was wide open in the computing space, but in physics, you were as optimistic about physics as
No, I mean, I was one of three brothers who were all in the same grade. I have a twin and a younger brother who skipped second grade and was with us the whole time after that. And he went on. He actually studied under Kip Thorne at Caltech.
Wow.
But he also didn't. He ended up in software. He taught about physics. So,
does it make you sad that theoretical physics, even with string theory, hasn't really had any foundational breakthroughs in the latter part of the 20th century? In fact, I'd say the problem is theory over experiment. I would say we need more Aristotle and less Plato. Mathematics is not all physical. There are lots of mathematics that cannot be realized, as far as I know, in this world. So to understand the world, you need to do experiments. You need to not just dream up inductive theories that could have lots of alternative theories competing with them, with no way to decide between them except aesthetics, which is not a good guide, in my opinion. I don't know if you are friends with or have a relationship with Elon Musk. Where's in terms of like what you would love to see our society investing in, building up, is it closer to Elon or is it closer to Feynman and Einstein and those?
Well, those gentlemen are no longer with us, and I think that's noticed. So, like I said, the real glory days of physics, the famous pictures from Germany before the Second War, were just a fantastic assembly of brains. Schrodinger and Einstein, and physics, I think, took a wrong turn that maybe all of I would say Western science took in going for models over reality. Right? You see this in all sorts of fields now. We can build models that are very predictive and generative, and then we build actual devices or semiconductors, things like that. That's good. I'm not dismissing that. We need good models. We need to experiment and prove them and test them. But the problem I've seen in physics, which you see certainly in economics, the dismal science, and you see surprisingly in other so-called hard sciences, is models that don't really have to be tested against reality. They can instead become policy tools, or they can become, like I said, one of a large family of alternate theories that could be as predictive, but nobody's doing the winnowing out.
That's such an interesting tension in society. You see this in even the softer sciences, which have a deep love for, like psychology. You see this in epidemiology now with the virus.
Absolutely.
It's this tension of, how much of the world can we understand through just a beautifully fit model? And then at the same time, my main work is in machine learning, where it's like there is no provable thing usually. It's kind of it's all about just getting the right data set and getting tricks and so on. And there's this tension even in my own soul of like, I grew up on theoretical computer science. Like I loved approximation algorithms, like all of that, like different complexity classes, just those little puzzles. I mean, I don't know. To you as somebody who was in math and computer science and then ended up going into places where you engineer some of the most impactful things in this world, do you see the P versus NP, all that whole space as interesting at all?
Yeah, it's not that useful in practice, right? People are using it with sort of cryptanalysis or asymptotic arguments about, can we have a quantum resistant crypto algorithm, things like that, which may not be practical, right? If you follow Mikhail Diakonov or Gil Khalai, there are big questions about how quantum computing will scale up, how practical it will be.
Is that something that you think about, quantum computing?
Not except for spare time. Like you said, I'm not using this kind of computer science in practice because almost everything now is engineering and finding ways to get computers to be more useful for people, which goes from, design problems, which are really kind of an art. Like Knut said, anything you can't automate is an art.
Yeah.
Well, we can have, machine learning compose music and it can imitate, you can train it and it can sound kind of decent, but maybe lacking that je ne sais quoi. But, user interface still, I think, requires human art.
Let me ask the Richard Feynman question then, along that thread, is what do you think is the difference between physics and math? There's a giant overlap. There's a kind of intuition that physicists have about the world that's perhaps outside of mathematics. It's this mysterious art that they seem to possess, we humans generally possess. And then there's the beautiful rigor of mathematics that allows you to, just like as we were saying, invent frameworks of understanding our physical world. So what do you think is the difference there, and how big is it?
Well, I think of math as being the study of like abstractions over patterns and pure patterns in logic. And then physics is obviously grounded in a desire to understand the world that we live in.
Yeah.
I think you're going to get very different answers when you talk to different mathematicians, because there's a wide diversity in types of mathematicians. There are some who are motivated very much by pure puzzles. They might be turned on by things like combinatorics, and they just love the idea of building up a set of problem-solving tools applying to pure patterns, right? There are some who are very physically motivated, who try to invent new math or discover math in veins that they know will have applications to physics or sometimes computer science. And that's what drives them, right? Like chaos theory is a good example of something it's pure math. It's purely mathematical, a lot of the statements being made, but it's heavily motivated by specific applications to largely physics. And then you have a type of mathematician who just loves abstraction. They just love pulling it to the more and more abstract things, the things that feel powerful. These are the ones that initially invented like topology, and then later on get really into category theory and go on about like infinite categories and whatnot. These are the ones that love to have a system that can describe truths about as many things as possible, right? People from those three different veins of motivation into math are going to give you very different answers about what the relation at play here is. Because someone like Vladimir Arnold, who is this, he's written a lot of great books, many about like differential equations and such. He would say math is a branch of physics. That's how he would think about it. And of course he was studying like differential equations related things, because that is the motivator behind the study of PDEs and things like that. But you'll have others who, like especially the category theorists, who aren't really thinking about physics necessarily. It's all about abstraction and the power of generality. And it's more of a happy coincidence that ends up being useful for understanding the world we live in. And then you can get into like, why is that the case? It's sort of surprising that which is about pure puzzles and abstraction also happens to describe the very fundamentals of quarks and everything else.
Maybe it'd be nice to draw a distinction between nuclear physics and plasma physics. What is the distinction?
Nuclear physics is about the physics of the nucleus, and my Department of Nuclear Science and Engineering at MIT, is very concerned about all the interactions and reactions and consequences of things that go on in the nucleus, including nuclear energy, fission energy, which is the nuclear energy that we have already, and fusion energy, which is the energy source of the sun and stars, which we don't quite know how to turn into practical energy for humankind at the moment. That's what my research has mostly been aimed at. But plasmas are essentially the fourth state of matter. So if you think about solid, liquid, gas, plasma is the fourth of those states of matter. And it's actually the state of matter which one reaches if one raises the temperature. So cold things, like ice, are solid. Liquids are hotter water, and if you heat water beyond 100 degrees Celsius, it becomes gas. Well, that's true of most substances, and plasma is a state of matter in which the electrons are unbound from the nuclei, so they become separated from the nuclei and can move separately. So we have positively charged nuclei, and we have negatively charged electrons. The net is still neutral, electrically neutral, but a plasma conducts electricity, has all sorts of important properties that are associated with that separation, and that's what plasmas are all about. And the reason why my department is interested in plasma physics very strongly is because most things, well, for one thing, most things in the universe are plasma. The vast majority of matter in the universe is plasma. But most particularly, stars and the sun are plasmas because they're very hot. And it's only in very hot states that nuclear fusion reactions take place. And we want to understand how to implement those kind of phenomena on Earth.
You've said that with this metaphor analogy that theory of everything is a big mountain, and you have a sense that however far we're up the mountain, that the Wolfram physics model, a view of the universe, is at least the right mountain.
We're the right mountain, yes, without question.
So,
I'm
which aspect of it is the right mountain? So, for example, there's so many aspects to just the way of the Wolfram Physics project, the way it approaches the world. That's clean, crisp, and unique and powerful. So, there's discrete nature to it. There's a hypergraph. There's a computational nature. There's a generative aspect. You start from nothing. You generate everything. Which do you think the actual model is actually a really good one, or do you think this general principle of from simplicity generating complexity is the right? Like, what aspect of the mountain?
Yeah,
is the
right.
correct?
I think that the kind of the meta idea about using simple computational systems to do things, that's the ultimate big paradigm that is, sort of super important. The details of the particular model are very nice and clean and allow one to actually understand what's going on. They are not unique. And in fact, we know that. We know that there's a large number of different ways to describe essentially the same thing. I mean, I can describe things in terms of hypergraphs. I can describe them in terms of higher category theory. I can describe them in a bunch of different ways. They are in some sense all the same thing, but our sort of story about what's going on and the kind of cultural mathematical resonances are a bit different. Yeah. I mean, I think it's perhaps worth sort of saying a little bit about kind of the foundational ideas of these models and things.
Great. So, can you maybe can we like rewind? We've talked about it a little bit, but can you say like what the central idea is of the Wolfram Physics project?
Right. So the question is, we're interested in finding a sort of simple computational rule that describes our whole universe.
Can we just pause on that? It's just so beautiful. That's such a beautiful idea that we can generate our universe from a data structure, a simple structure, simple set of rules, and we can generate our entire universe.
Yes,
that's awe-inspiring.
Right. But so the question is, how do you actualize that? What might this rule be like? And so one thing you quickly realize is, if you're going to pack everything about our universe into this tiny rule, not much that we are familiar with in our universe will be obvious in that rule. So you don't get to fit all these parameters of the universe, all these features of, this is how space works, this is how time works, et cetera, et cetera, et cetera. You don't get to fit that all in. It all has to be sort of packed in to this thing, something much smaller, much more basic, much lower level machine code, so to speak, than that. And all the stuff that we're familiar with has to kind of emerge from the operation of.
So the rule in itself, because of the computational reducibility, is not going to tell you the story. It's not going to give you the answer to, it's not going to let you predict what you're going to have for lunch tomorrow. Right. And it's not going to let you predict basically anything about your life, about the universe.
Right. And you're not going to be able to see in that rule, there's the 3 for the number of dimensions of space and so on.
Right.
That's not going to be there.
So space-time is not going to be obviously.
Right. So the question is then, what is the universe made of? It's a basic question. And we've had some assumptions about what the universe is made of for the last few thousand years that I think in some cases just turn out not to be right. And, the most important assumption is that space is a continuous thing. That is, that you can, if you say, let's pick a point in space, we're going to do geometry, we're going to pick a point. We can pick a point absolutely anywhere in space. Precise numbers we can specify of where that point is. In fact, Euclid, who kind of wrote down the original kind of axiomatization of geometry back in 300 BC or so, his very first definition, he says, a point is that which has no part. A point is this indivisible, infinitesimal thing. Okay, so we might have said that about material objects. We might have said that about water, for example. We might have said water is a continuous thing that we can just pick any point we want in some water. But actually, we know it isn't true. We know that water is made of molecules that are discrete. And so one fundamental question is, what is space made of? And so one of the things that's sort of a starting point for what I've done is to think of space as a discrete thing, to think of there being sort of atoms of space, just as there are atoms of material things, although very different kinds of atoms. And by the way, I mean, this idea, there were ancient Greek philosophers who had this idea. There were, Einstein actually thought this is probably how things would work out. I mean, he said, repeatedly, he thought this is where it would work out, but we don't have the mathematical tools in our time, which was 1940s, 1950s, and so on, to explore this.
Like the way he thought, you mean that there is something very, very small and discrete that's underlying space.
Yes. And that means that, the mathematical theories in physics assume that space can be described just as a continuous thing. You can just pick coordinates, and the coordinates can have any values, and that's how you define space. Space is this just sort of background sort of theater on which the universe operates.
But can we draw a distinction between space as a thing that could be described by three values, coordinates, and how are you using the word space more generally when you say?
No, I'm just talking about space
like
as in what we experience in the universe.
So that you think this 3D aspect of it is fundamental?
No, I don't think that 3D is fundamental at all. Actually, I think that the thing that has been assumed is that space is this continuous thing where you can just describe it by, let's say, three numbers, for instance. But the most important thing about that is that you can describe it by precise numbers, because you can pick any point in space, and you can talk about motions, any infinitesimal motion in space.
And that's what continuous means.
That's what continuous means. That's what, Newton invented calculus to describe these kind of continuous small variations and so on. That's kind of a fundamental idea. From Euclid on, that's been a fundamental idea about space. And so,
is that right or wrong?
It's not right. It's not right. It's right at the level of our experience most of the time. It's not right at the level of the machine code, so to speak. And so
machine code, of the simulation. That's right. The very lowest level of the fabric of the universe, at least under the Wolfram physics model, is your sense is discrete.
Right. So now, what does that mean? So it means what is space then? So in our models, the basic idea is you say there are these sort of atoms of space. There are these points that represent places in space, but they're just discrete points. Mm-hmm. And the only thing we know about them is how they're connected to each other. We don't know where they are. They don't have coordinates. We don't get to say this is a position such and such. It's just, here's a big bag of points. Like in our universe, there might be 10 to the 100 of these points. And all we know is this point is connected to this other point. So it's like, all we have is the friend network, so to speak. We don't have, people's, physical addresses. All we have is the friend network of these points.
Yeah. The underlying nature of reality is kind of like a Facebook. We don't know their location, but we have the friends.
Yeah, right. We know which point is connected to which other points. And that's all we know. And so you might say, well, how on earth can you get something which is like our experience of what seems like continuous space? Well, the answer is, by the time you have 10 to the 100 of these things, those connections can work in such a way that on a large scale, it will seem to be like continuous space in, let's say, 3 dimensions or some other number of dimensions or 2.6 dimensions or whatever else.
Because they're much, 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 much larger. So like the number of relationships here we're talking about is just a humongous amount. So the kind of thing you're talking about is very, very, very small relative to our experience of daily life.
Right. So, I mean, we don't know exactly the size, but maybe 10 to the minus, maybe around 10 to the minus 100 meters. So, the size to give a comparison, the size of a proton is 10 to the minus 15 meters. Yeah. And so this is something incredibly tiny compared to that.
And the idea that from that would emerge the experience of continuous space is mind-blowing. Well, what's your intuition why that's possible? Like First of all, I mean, we'll get into it, but I don't know if we will through the medium of conversation, but the construct of hypergraphs is just beautiful.
Right.
Cellular automata are beautiful. We'll talk about it, but okay.
Right. But this thing about, continuity arising from discrete systems is, in today's world, is actually not so surprising. I mean, your average computer screen, right? Every computer screen is made of discrete pixels. Yet we have the idea that we're seeing these continuous pictures. I mean, it's, the fact that on a large scale, continuity can arise from lots of discrete elements. This is, at some level, unsurprising now.
But wait. But the pixels have a very definitive structure of neighbors on a computer screen.
Right.
There's no concept of space inherent in the underlying fabric of reality.
Right. So the point is but there are cases where there are. So, for example, let's just imagine you have a square grid. Okay, and at every point on the grid, you have one of these atoms of space, and it's connected to four other atoms of space on the northeast, southwest corners, right? There you have something where if you zoom out from that, it's like a computer screen.
Yeah. So the relationship creates the spatial,
right.
The relationship creates a constraint, which then, in an emergent sense, creates basically a spatial coordinate for that thing.
Yeah, right.
Even though the individual point doesn't have a spatial.
Even though the individual point doesn't know anything, it just knows what its neighbors are. On a large scale, it can be described by saying, "Oh, it looks like it's this grid, zoomed out grid." You can say, well, you can describe these different points by saying they have certain positions, coordinates, etc. Now, in the sort of real setup, it's more complicated than that. It isn't just a square grid or something. It's something much more dynamic and complicated, which we'll talk about. But the first key idea is, what's the universe made of? It's made of atoms of space, basically, with these connections between them. What kind of connections do they have? Well, the simplest kind of thing you might say is we've got something like a graph where every atom of space, where we have these edges that go between these connections that go between atoms of space. We're not saying how long these edges are. We're just saying there is a connection from this place from this atom to this atom.
Just a quick pause, because there's a lot of varied people that listen to this. Just to clarify, because I did a poll, actually, what do you think a graph is a long time ago? And it's kind of funny how few people know the term graph outside of computer science.
Let's call it a network. I think
let's call it a network is better. So, but every time I like the word graph though. So let's just say that a graph, we'll use terms nodes and edges maybe. And it's just nodes represent some abstract entity, and then the edges represent relationships between those entities.
Right. Exactly.
Yeah. So that's what a graph is. Sorry. Right. So there you go. So that's the basic structure.
That is the simplest case of a basic structure. Actually, it tends to be better to think about hypergraphs. So a hypergraph is just, instead of saying there are connections between pairs of things, we say there are connections between any number of things. Yeah. So there might be ternary edges. So instead of just having 2 points are connected by an edge, you say 3 points are all associated with a hyperedge, are all connected by a hyperedge. That's just, at some level, that's a detail. It's a detail that happens to make for me, sort of in the history of this project, the realization that you could do things that way broke out of certain kinds of arbitrariness that I felt that there was in the model before I had seen how this worked.
I mean, a hypergraph can be mapped to a graph. It's just a convenient representation, mathematically speaking.
Right, that's correct. But the first question, the first idea of these models of ours is space is made of these, connected sort of atoms of space. The next idea is space is all there is. There's nothing except for this space. So in traditional ideas in physics, people have said there's space, it's kind of a background, and then there's matter, all these particles, electrons, all these other things, which exist in space, right? But in this model, one of the key ideas is there's nothing except space. So in other words, everything that exists in the universe is a feature of this hypergraph. So how can that possibly be? Well, the way that works is that there are certain structures in this hypergraph where you say that little twisty, knotted thing, we don't know exactly how this works yet, but we have sort of idea about how it works mathematically. This sort of twisted, knotted thing, that's the core of an electron. This thing over there that has this different form, that's something else.
So the different peculiarities of the structure of this graph are the very things that we think of as the particles inside the space, but in fact, it's just a property
of the
space. Mind blowing, first of all. It's mind blowing, and we'll probably talk in its simplicity and beauty.
Yes, I think it's very beautiful. I mean, this is.
But that's space, and then there's another concept we didn't really kind of mention, but you think of computation as like a transformation.
Let's talk about time in a second. Let's
sure.
just. I mean, on the subject of space, there's this question of kind of what, there's this idea. There is this hypergraph. It represents space, and it represents everything that's in space. The features of that hypergraph, you can say certain features in this part we do know, certain features of the hypergraph represent the presence of energy, for example, or the presence of mass or momentum. And we know what the features of the hypergraph that represent those things are. But it's all just the same hypergraph. So one thing you might ask is, if you just look at this hypergraph and you say, and we're going to talk about sort of what the hypergraph does, but if you say, how much of what's going on in this hypergraph is things we know and care about, like particles and atoms and electrons and all this kind of thing, and how much is just the background of space. Mm-hmm. So it turns out, so far as in one rough estimate of this, everything that we care about in the universe is only 1 part in 10 to the 120 of what's actually going on. The vast majority of what's happening is purely things that maintain the structure of space. That, in other words, that the things that are the features of space that are the things that we consider notable, like the presence of particles and so on, that's a tiny little piece of froth on the top of all this activity that mostly is just intended to, mostly, I can't say intended, there's no intention here, that just maintains the structure of space.
Let me load that in. It just makes me feel so good as a human being.
Well,
to be the froth on the 1 in the 10 to the
120 or something of,
also just humbling how in this mathematical framework how much work needs to be done on the infrastructure of our universe.
Right, to maintain the infrastructure of our universe is a lot of work. We are merely writing a little tiny things on top of that infrastructure, quantum state.
Is it useful for us to maybe first talk about how quantum mechanics fits into the Wolfram physics model?
Yes.
Let's go there. So we talked about general relativity. Now, what have you found?
What's the story of quantum mechanics? Right.
Within and outside of the Wolfram physics.
Right. So, I mean, the key idea of quantum mechanics, the typical interpretation is classical physics says a definite thing happens. Quantum physics says there's this whole set of paths of things that might happen, and we are just observing some overall probability of how those paths work. Okay, so when you think about our hypergraphs and all these little updates that are going on, there's a very remarkable thing to realize, which is if you say, well, which particular sequence of updates should you do? Say, well, it's not really defined. You can do any of a whole collection of possible sequences of updates. Okay, that set of possible sequences of updates defines yet another kind of graph that we call a multi-way graph. And a multi-way graph just is a graph where at every node there is a choice of several different possible things that could happen. So, for example, you go this way, you go that way. Those are two different edges in the multi-way graph. And you're building up this set of possibilities. So actually, like, for example, I just made the multi-way graph for tic-tac-toe. Mm-hmm. Okay, so tic-tac-toe, you start off with some board that, as everything is blank, and then somebody can put down an X somewhere, an O somewhere, and then there are different possibilities. At each stage, there are different possibilities. And so you build up this multi-way graph of all those possibilities. Now, notice that even in tic-tac-toe, you have the feature that there can be something where you have two different things that happen, and then those branches merge. because you end up with the same shape of, the same configuration of the board, even though you got there in two different ways. So the thing that's sort of an inevitable feature of our models is that just like quantum mechanics suggests, definite things don't happen. Instead, you get this whole multi-way graph of all these possibilities. Okay, so then the question is, so that's sort of a picture of what's going on. Now you say, okay, well, quantum mechanics has all these features of, all this mathematical structure and so on. How do you get that mathematical structure? Okay, couple of things to say. So quantum mechanics is actually, in a sense, two different theories glued together. Quantum mechanics is the theory of how quantum amplitudes work, that more or less give you the probabilities of things happening. And it's the theory of quantum measurement, which is the theory of how we actually conclude definite things. Because the mathematics just gives you these quantum amplitudes, which are more or less probabilities of things happening, but yet we actually observe definite things in the world. Quantum measurement has always been a bit mysterious. It's always been something where people just say, well, the mathematics says this, but then you do a measurement and there are philosophical arguments about what the measurement is, but it's not something where there's a theory of the measurement.
Somebody on Reddit also asked, please ask Stephen to tell his story of the double slit experiment.
Okay. Yeah, I can.
Does that make sense?
Oh, yeah, it makes sense. Absolutely makes sense.
Why is this like a good way to discuss?
A little bit. Let me explain a couple of things first. So the structure of quantum mechanics is mathematically quite complicated. One of the features, let's see, well, how to describe this. Okay, so first point is there's this multi-way graph of all these different paths of things that can happen in the world. And the important point is that these, you can have branchings and you can have mergings. Okay, so this property turns out causal invariance is the statement that the number of mergings is equal to the number of branchings.
Yeah.
So in other words, every time there's a branch, eventually there will also be a merge. In other words, every time there were two possibilities for what might have happened, eventually those will merge.
Yeah. Beautiful concept, by the way. But yeah.
So that idea. Okay. So then, so that's one thing, and that's closely related to the sort of objectivity in quantum mechanics. The fact that we believe definite things happen. It's because although there are all these different paths, in some sense, because of causal invariance, they all imply the same thing. I'm cheating a little bit in saying that, but that's roughly the essence of what's going on. Okay. Next thing to think about is. You have this multi-way graph. It has all these different possible things that are happening. Now we ask, this multi-way graph is sort of evolving with time. Over time, it's branching, it's merging, it's doing all these things. Okay. The question we can ask is, if we slice it at a particular time, what do we see? And that slice represents, in a sense, something to do with the state of the universe at a particular time. So in other words, we've got this multi-way graph of all these possibilities, and then we're asking, and okay, we take this slice. This slice represents, okay, each of these different paths corresponds to a different quantum possibility for what's happening.
Right.
When we take this slice, we're saying, what are the set of quantum possibilities that exist at a particular time?
And when you say slice, are these, you slice the graph and then there's a bunch of leaves?
A bunch of leaves.
And those represent the state of things.
Right. But then, okay, so the important thing that you are quickly picking up on is that what matters is kind of how these leaves are related to each other. So a good way to tell how leaves are related is just to say, on the step before, did they have a common ancestor? So two leaves they might have just branched from one thing, or they might be far away, way far apart in this graph, where to get to a common ancestor, maybe you have to go all the way back to the beginning of the graph, all the way back to the beginning.
So there's some kind of measure of distance.
Right. What you get is by making this slice, what you call it branchial space, the space of branches. And in this branchial space, you have a graph that represents the relationships between these quantum states in branchial space. You have this notion of distance in branchial space. Okay, so
it's connected to quantum entanglement.
Yes, yes. It's basically the distance in branchial space is kind of an entanglement distance. So
That's a very nice model.
Right. It is very nice. It's very beautiful. It's so clean. I mean, it's really, and it tells one, okay, so anyway, so then this branchial space has this sort of map of the entanglements between quantum states. So in physical space, we have, you can say, let's say the causal graph, and we can slice that at a particular time, and then we get this map of how things are laid out in physical space. When we do the same kind of thing, there's a thing called the multi-way causal graph, which is the analog of a causal graph for the multi-way system. We slice that. We get essentially the relationships between things, not in physical space, but in the space of quantum states. It's like which quantum state is similar to which other quantum state. Okay, so now I think next thing to say is just to mention how quantum measurement works. So quantum measurement has to do with reference frames in branchial space. So measurement in physical space, it matters how we assign spatial position and how we define coordinates in space and time. And that's how we make measurements in ordinary space. Are we making a measurement based on us sitting still here? Are we traveling at half the speed of light and making measurements that way? These are different reference frames in which we're making our measurements. And the relationship between different events and different points in space and time will be different depending on what reference frame we're in. Okay, so then we have this idea of quantum observation frames, which are the analog of reference frames, but in branchial space. And so what happens is, what we realize is that a quantum measurement is the observer is sort of arbitrarily determining this reference frame. The observer is saying, I'm going to understand the world by saying that space and time are coordinatized this way. I'm going to understand the world by saying that quantum states and time are coordinatized in this way. And essentially what happens is that the process of quantum measurement is a process of deciding how you slice up this multi-way system in these quantum observation frames. So in a sense, the way the observer enters is by their choice of these quantum observation frames. And what happens is that the observer, this is again another stack of other concepts, but anyway, because the observer is computationally bounded, there is a limit to the type of quantum observation frames that they can construct.
Interesting. Okay, so there's some constraints, some limit on
the
choice of observation frames.
Right, and by the way, I just
space.
want to mention that there's it's bizarre, but there's a hierarchy of these things. So in thermodynamics, the fact that we believe entropy increases, we believe things get more disordered, is a consequence of the fact that we can't track each individual molecule. If we could track every single molecule, we could run every movie in reverse, so to speak, and we would not see that things are getting more disordered. But it's because we are computationally bounded. We can only look at these big blobs of what all these molecules collectively do, that we think that that we describe it in terms of entropy increasing and so on. And it's the same phenomenon, basically, also a consequence of computational irreducibility that causes us to basically be forced to conclude that definite things happen in the world, even though there's this quantum, this set of all these different quantum processes that are going on. So, I'm skipping a little bit, but that's a rough picture.
And in the evolution of the Wolfram Physics Project, where do you feel we stand on some of the puzzles that are along the way? So you're skipping along a bunch of.
It's amazing how much these things are unraveling. I mean, these things. Look, it used to be the case that I would agree with Dick Feynman. Nobody understands quantum mechanics, including me.
Yeah.
Okay, I'm getting to the point where I think I actually understand quantum mechanics. My exercise, okay, is can I explain quantum mechanics for real at the level of kind of middle school type explanation?
Right.
And I'm getting closer. It's getting there. I'm not quite there. I've tried it a few times, and I realize that there are things that where I have to start talking about elaborate mathematical concepts and so on. But I think, and you've got to realize that it's not self-evident that we can explain, at an intuitively graspable level something which, about the way the universe works. The universe wasn't built for our understanding, so to speak. But I think then okay. So another important idea is this idea of branchial space, which I mentioned, this sort of space of quantum states. It is Okay, so I mentioned Einstein's equations describing, the effect of mass and energy on trajectories of particles, on geodesics. The curvature of physical space is associated with the presence of energy according to Einstein's equations. Okay, so it turns out that, rather amazingly, the same thing is true in branchial space. So it turns out the presence of energy, or more accurately, Lagrangian density, which is a kind of relativistic invariant version of energy, the presence of that causes essentially deflection of geodesics in this branchial space. Okay, so you might say, so what? Well, it turns out that the best formulation we have of quantum mechanics, the Feynman path integral, is a thing that describes quantum processes in terms of mathematics that can be interpreted as, well, in quantum mechanics, the big thing is you get these quantum amplitudes, which are complex numbers that represent, when you combine them together, represent probabilities of things happening. And so the big story has been, how do you derive these quantum amplitudes? And people think these quantum amplitudes, they have a complex number, has, a real part and an imaginary part. You can also think of it as a magnitude and a phase. And people have sort of thought these quantum amplitudes have magnitude and phase, and you compute those together. Turns out that the magnitude and the phase come from completely different places. The magnitude comes, okay, so how do you compute things in quantum mechanics? Roughly, I'm telling you, I'm getting there to be able to do this at a middle school level, but I'm not there yet. Roughly what happens is, you're asking, does this state in quantum mechanics evolve to this other state in quantum mechanics? And you can think about that like a particle traveling, or something traveling through physical space, but instead it's traveling through branchial space. And so what's happening is, does this quantum state evolve to this other quantum state? It's like saying, does this object move from this place in space to this other place in space? Okay. Now, the way that these quantum amplitudes characterize kind of to what extent the thing will successfully reach some particular point in branchial space. Just like in physical space, you could say, oh, it had a certain velocity and it went in this direction. In branchial space, there's a similar kind of concept.
Is there a nice way to visualize, for me now, mentally, branchial space?
It's just, you have this hypergraph, you have this multi-way graph. It's this big branching and merging thing.
But I mean, moving through that space. I'm just trying to understand what that looks like.
Space is probably exponential dimensional, which makes it, again, another can of worms in understanding what's going on. That space, as in ordinary space, this hypergraph, the spatial hypergraph, limits to something which is like a manifold, like something like three-dimensional space. Almost certainly, the multi-way graph limits to a Hilbert space, which is something that, it's just a weirder exponential dimensional space. And by the way, you can ask, there are much weirder things that go on. For example, one of the things I've been interested in is the expansion of the universe in branchial space. So we know the universe is expanding in physical space, but the universe is probably also expanding in branchial space. So that means the number of quantum states of the universe is increasing with time.
The diameter of the thing is growing.
Right. So that means that and by the way, this is related to whether quantum computing can ever work.
Why?
Okay, so let me explain why. So let's talk about. Okay, so first of all, just to finish the thought about quantum amplitudes, the incredibly beautiful thing. I'm just very excited about this. The Feynman path integral is this formula. It says that the quantum amplitude is e to the I s over h bar, where s is this thing called the action, and so that can be thought of as representing a deflection of the angle of this path in the multi-way graph. So it's a deflection of a geodesic in the multi-way path that is caused by this thing called the action, which is essentially associated with energy. Okay, and so this is a deflection of a path in branchial space that is described by this path integral, which is the thing that is the mathematical essence of quantum mechanics. Turns out that deflection is the deflection of geodesics in branchial space follows the exact same mathematical setup as the deflection of geodesics in physical space, except the deflection of geodesics in physical space is described with Einstein's equations. The deflection of geodesics in branchial space is defined by the Feynman path integral, and they are the same. In other words, they are mathematically the same. So that means that general relativity is a story of essentially motion in physical space. Quantum mechanics is a story of essentially motion in branchial space. And the underlying equation for those two things, although it's presented differently because one's interested in different things in branchial space than physical space, but the underlying equation is the same. So in other words, it's just, these two theories, which are the two sort of pillars of 20th century physics, which have seemed to be off in different directions, are actually facets of the exact same theory.
That's exciting to see where that evolves, and exciting that just is there.
Right. I mean, to me, look, having spent some part of my early life, working in the context of these theories of 20th century physics, they seem so different, and the fact that they're really the same is just really amazing idea.
But so the standard model of physics is one of the models that's very accurate for describing three of the fundamental forces of physics. And it's looking at the world of the very small.
Right.
And then there's back to the neighbor of gravity, of general relativity. So, and then in the context of a theory of everything, what's traditionally the task of the unification of these theories? And why is it hard?
The issue is you try to use the methods of quantum field theory to talk about gravity, and it doesn't work. Just like there are photons of light, so there are gravitons, which are sort of the particles of gravity. And when you try and compute sort of the properties of the particles of gravity, the kind of mathematical tricks that get used in working things out in quantum field theory don't work. And that's been a sort of fundamental issue. And when you think about black holes, which are a place where sort of the structure of space is has sort of rapid variation, and you get kind of quantum effects mixed in with effects from general relativity, things get very complicated, and there are apparent paradoxes and things like that. And people have, there have been a bunch of mathematical developments in physics over the last, 30 years or so, which have kind of picked away at those kinds of issues and got hints about how things might work. But it hasn't been, and the other thing to realize is, as far as physics is concerned, it's just like, here's general relativity, here's quantum field theory, be happy.
Yeah, so do you think there's a quantization of gravity, so quantum gravity? What do you think of efforts that people have tried to, what do you think in general of the efforts of the physics community to try to unify these laws?
So I think it's interesting. I mean, I would have said something very different before what's happened with our physics project. The remarkable thing is what we've been able to do is to make from this very simple, structurally simple underlying set of ideas, we've been able to build this very elaborate structure that's both very abstract and very sort of mathematically rich. And the big surprise, as far as I'm concerned, is that it touches many of the ideas that people have had. So in other words, things like string theory and so on, twistor theory, it's like, we might have thought, I had thought, we're out on a prong. We're building something that's computational. Right. It's completely different from what other people have done. But actually, it seems like what we've done is to provide essentially the machine code that, these things are various features of domain-specific languages, so to speak, that talk about various aspects of this machine code. And I think this is something that to me is very exciting, because it allows one both for us to provide sort of a new foundation for what's been thought about there, and for all the work that's been done in those areas to give us, more momentum to be able to figure out what's going on. Now, people have sort of hoped, we're just going to be able to get, string theory to just answer everything. That hasn't worked out. And I think we now kind of can see a little bit about just sort of how far away certain kinds of things are from being able to explain things. Some things, one of the big surprises to me, actually, I literally just got a message about one aspect of this, is the it's turning out to be easier. I mean, this project has been so much easier than I could ever imagine it would be. That is, I thought we would be, just about able to understand the first 10 to the minus 100 seconds of the universe. And, it would be 100 years before we get much further than that. It's just turned out it actually wasn't that hard. I mean, we're not finished, but,
So you're seeing echoes of all the disparate theories of physics in this framework.
Yes. I mean, it's a very interesting, sort of history of science-like phenomenon. I mean, the best analogy that I can see is what happened with the early days of computability and computation theory. Turing machines were invented in 1936. People sort of understand computation in terms of Turing machines, but actually there had been pre-existing theories of computation, combinators, general recursive functions, lambda calculus, things like this. But those hadn't been concrete enough that people could really wrap their arms around them and understand what was going on. And I think what we're going to see in this case is that a bunch of these mathematical theories, including some one of the things that's really interesting is one of the most abstract things that's come out of sort of mathematics, higher category theory, things about infinity groupoids, things like this, which to me always just seemed like they were floating off into the stratosphere, ionosphere of mathematics, turn out to be things which our sort of theory anchors down to something fairly definite and says are super relevant to the way that we can understand how physics works.
Give me a sec. By the way, I just threw a hat. Sabine Hossenfelder. I don't know if you're familiar with her. She wrote this book that I need to read, but I forget what the title is, but it's Beauty Leads Us Astray in Physics is a subtitle, something like that, which so much about what we're talking about now, like this simplification, is to us humans seems to be beautiful. Like there's a certain intuition with physicists, with people, that a simple theory like this reducibility, pockets of reducibility is the ultimate goal. And I think what she tries to argue is, no, we just need to come up with theories that are just really good at predicting physical phenomena. It's okay to have a bunch of disparate theories as opposed to trying to chase this beautiful theory of everything is the ultimate beautiful theory. A simple one. What's your response to that?
Well, so what you're quoting, so I don't know the Sabine Hossenfelder's, exactly what she said, but I mean,
I might be misquoting the exact. I'm quoting the title of her book.
Okay, well, let me respond to what you were describing, which may or may not have anything to do with what what Sabine Hossenfelder says or thinks.
Sorry, Sabine.
Right.
Sorry for misquoting.
But I mean, the question is, is beauty a guide to whether something is correct?
That's right.
Which is kind of also the story of Occam's razor.
Right.
If you've got a bunch of different explanations of things, is the thing that is the simplest explanation likely to be the correct explanation? And there are situations where that's true, and there are situations where it isn't true. Sometimes in human systems, it is true because people have kind of, in evolutionary systems, sometimes it's true because it's sort of been kicked to the point where it's minimized. But in physics, does Occam's razor work? Is there a simple, quotes, beautiful explanation for things, or is it a big mess? We don't intrinsically know. I think that before I worked on the project in recent times, I would have said, we do not know how complicated the rule for the universe will be. And I would have said, the one thing we know, which is a fundamental fact about science, that's the thing that makes science possible, is that there is order in the universe. I mean, early theologians would have used that as an argument for the existence of God. Because it's like, why is there order in the universe? Why doesn't every single particle in the universe just do its own thing? Yeah. Something must be making there be order in the universe. We, in the sort of early theology point of view, that's, the role of God is to do that, so to speak. In our, we might say it's the role of a formal theory to do that. And then the question is, but how simple should that theory be? And should that theory be one that where I think the point is, if it's simple, it's almost inevitably somewhat beautiful in the sense that because all the stuff that we see has to fit into this little tiny theory. Yeah. And the way it does that has to be, it depends on your notion of beauty. But I mean, for me, the sort of the surprising connectivity of it is, at least in my aesthetic, that's something that responds to my aesthetic.
But the question is, you're a fascinating person in the sense that you're at once talking about the fundamental computational reducibility of the universe, and on the other hand, trying to come up with a theory of everything, which simply describes the simple origins of that computational reducibility.
Right.
I mean, both of those things are it's paralyzing to think that we can't make any sense of the universe in the general case, but it's hopeful to think like, one, we can think of a rule and that generates this whole complexity, and two, we can find pockets of reducibility that are powerful for everyday life to do different kinds of predictions. I suppose Sabine wants to focus on the finding of small pockets of reducibility versus the theory of everything.
It's a funny thing because a bunch of people have started working on this physics project, people who are physicists basically, and it is really a fascinating sociological phenomenon, because when I was working on this before in the 1990s, wrote it up, it's 100 pages of this 1,200-page book that I wrote, New Kind of Science. 100 pages of that is about physics. Right? I saw it at that time not as a pinnacle achievement, but rather as a use case, so to speak. I mean, my main point was this new kind of science, and it's like, you can apply it to biology, you can apply it to other kinds of physics, you can apply it to fundamental physics. It's just an application, so to speak. It's not the core thing. But then, one of the things that was interesting with that book was, book comes out, lots of people think it's pretty interesting, and lots of people start using what it has in different kinds of fields. The one field where there was sort of a heavy pitchforking was from my friends, the fundamental physics people.
Yeah.
It's like, no, this can't possibly be right. And, it's like, if what you're doing is right, it'll overturn 50 years of what we've been doing. And it's like, no, it won't, was what I was saying. And it's like, for a while when I started, I was going to go on back in 2004, actually, I was going to go on working on this project. And I actually stopped, partly because it's like, why am I, this is like, I've been in business a long time, right? I'm building a product for a target market that doesn't want the product. And it's like,
why work? Why work swim against the current or whatever.
Right. But you see what's happened, which is sort of interesting, is that, so a couple of things happened. And it was like, it was like, I don't want to do this project because I can do so many other things which I'm really interested in, where, people say, great, thanks for those tools, thanks for those ideas, etc. Whereas, if you're dealing with kind of a sort of a structure where people are saying, no, we don't want this new stuff. We don't need any new stuff. We're really fine with what we're doing.
There's like literally millions of people who are thankful for Wolfram Alpha. A bunch of people wrote to me how thankful they are. They are a different crowd than the theoretical physics community, perhaps.
Yeah, well, right. But, the theoretical physics community pretty much uniformly uses Wolfram language and Mathematica, right? And so it's kind of like and that's, but the thing is what happens, this is what happens. Mature fields do not, it's like, we're doing what we're doing. We have the methods that we have, and we're just fine here. Now, what's happened in the last 18 years or so, I think, is a couple of things have happened. First of all, the hope that, string theory or whatever would deliver the fundamental theory of physics, that hope has disappeared. Another thing that's happened is the sort of the interest in computation around physics has been greatly enhanced by the whole quantum information, quantum computing story. Mm-hmm. People, the idea there might be something sort of computational related to physics has somehow grown. And I think, it's sort of interesting. I mean, right now, if we say, it's like, if you're like, who else is trying to come up with a fundamental theory of physics? It's like, There aren't professional
no
professional physicists have that yet.
So if I were to try to summarize the Wolfram Physics project, which is something that's been in your brain for a long time, but really has just exploded in activity, only just months ago.
Yes.
So it's an evolving thing, and next week, I'll try to publish this conversation as quickly as possible, because by the time it's published, already new things will probably have come out. So if I were to summarize it, we've talked about the basics of, there's a hypergraph that represents space. There is transformations on that hypergraph that represents time.
Progress of time.
That progress of time. There's a causal graph that's a characteristic of this. And the basic process of science, of science within the Wolfram physics model, is to try different rules and see which properties of physics that we know of, known physical theories, appear within the graphs that emerge from that rule.
That's what I thought it was going to be.
Okay. So what? So what is it?
It turns out we can do a lot better than that. It turns out that using kind of mathematical ideas, we can say, and computational ideas, we can make general statements, and those general statements turn out to correspond to things that we know from 20th century physics. In other words, the idea of you just try a bunch of rules and see what they do, that's what I thought we were going to have to do. Mm-hmm. But in fact, we can say, given causal invariance and computational irreducibility, we can derive, and this is where it gets really pretty interesting, we can derive special relativity, we can derive general relativity, we can derive quantum mechanics. And that's where things really start to get exciting, is, it wasn't at all obvious to me that even if we were completely correct, and even if we had, this is the rule, even if we found the rule, to be able to say, yes, it corresponds to things we already know, I did not expect that to be the case. And
so for somebody who is a simple mind and definitely not a physicist, not even close, what does derivation mean in this case?
Okay, so let me, this is an interesting question. Okay, so one thing
in the context of computational reducibility.
Right. So what you have to do, let me go back to again the mundane example of fluids and water and things like that, right? So you have a bunch of molecules bouncing around. You can say, just as a piece of mathematics, I happen to do this from cellular automata back in the mid-1980s, you can say, just as a matter of mathematics, you can say the continuum limit of these little molecules bouncing around is the Navier-Stokes equations. That's just a piece of mathematics. It doesn't rely on, you have to make certain assumptions that you have to say there's enough randomness in the way the molecules bounce around, that certain statistical averages work, et cetera, et cetera, et cetera. Okay, it is a very similar derivation to derive, for example, the Einstein equations. Okay, so the way that works, roughly, the Einstein equations are about curvature of space. Curvature of space, I talked about sort of how you can figure out dimension of space. There's a similar kind of way of figuring out, if you just sort of say, you're making a larger and larger ball, or larger and larger, if you draw a circle on the surface of the Earth, for example, you might think the area of a circle is pi r squared. But on the surface of the Earth, because it's a sphere, it's not flat, the area of a circle isn't precisely pi r squared. As the circle gets bigger, the area is slightly smaller than you would expect from the formula pi r squared. It has a little correction term that depends on the ratio of the size of the circle to the radius of the Earth. Okay, so it's the same basic thing, allows you to measure from one of these hypergraphs what is its effective curvature. And that's...
the little piece of mathematics that explains special general relativity is... can map nicely to describe fundamental property of the hypergraphs, the curvature of the hypergraphs.
So special relativity is about the relationship of time to space. General relativity is about curvature in this space represented by this hypergraph.
So what is the curvature of a hypergraph?
Okay, so first I have to explain, what we're explaining is, first thing you have to have is a notion of dimension. You don't get to talk about curvature of things. If you say, oh, it's a curved line, but I don't know what a line is yet, So
what is the dimension of a hypergraph then? Where we've talked
Right.
about effective dimension, but
right, that's what this is about. What this is about is you have your hypergraph. It's got 1 trillion nodes in it.
Yep.
What is it roughly like? Is it roughly like a grid, a 2-dimensional grid? Is it roughly like all those nodes are arranged on a line? What's it roughly like? And there's a pretty simple mathematical way to estimate that by just looking at this thing I was describing, this sort of the size of a ball that you construct in the hypergraph. You just measure that. You can just, compute it on a computer for a given hypergraph, and you can say, oh, this thing is wiggling around, but it's roughly corresponds to 2 or something like that, or roughly corresponds to 2.6 or whatever. So that's how you have a notion of dimension in these hypergraphs. Curvature is something a little bit beyond that. If you look at how the size of this ball increases as you increase its radius, curvature is a correction to the size increase associated with dimension. It's a sort of a second order term in determining the size. Just like the area of a circle is roughly pi r squared, so it goes up like r squared. The 2 is because it's in 2 dimensions. But when that circle is drawn on a big sphere, the actual formula is pi r squared times 1 minus r squared over a squared and some coefficient. So in other words, there's a correction and that correction term, that gives you curvature. And that correction term is what makes this hypergraph have the potential to correspond to curved space. Now, the next question is that curvature, is the way that curvature works, the way that Einstein's equations for general relativity, is it the way they say it should work? And the answer is yes. And
really?
And so how does that work? The
calculation of the curvature of this hypergraph for some set of rules?
No, it doesn't matter what the rules are. It doesn't, so long as they have causal invariance and computational irreducibility, and they lead to finite dimensional space, non-infinite dimensional space. Non-infinite dimensional. It can grow infinitely, but it can't be infinite dimensional. So,
what does a infinitely dimensional hypergraph look like? So that means,
for example, so in a tree, you start from one root of the tree, it doubles again, and that means if you ask the question, starting from a given point, how many points do you get to? Remember, like a circle, you get to r squared with a 2 there. On a tree, you get to, for example, 2 to the r. It's exponential dimensional, so to speak, or infinite dimensional.
Do you have a sense of, in the space of all possible rules, how many lead to infinitely dimensional hypergraphs? Is that
no?
Okay. Is that an important thing to know?
Yes, it's an important thing to know. I would love to know the answer to that. But it gets a little bit more complicated because, for example, it's very possibly the case that in our physical universe, that the universe started infinite dimensional, and it only at the Big Bang, it was very likely infinite dimensional, and as the universe sort of expanded and cooled, its dimension gradually went down. And so one of the bizarre possibilities, which actually there are experiments you can do to try and look at this, the universe can have dimension fluctuations. So in other words, we think we live in a 3-dimensional universe, but actually there may be places where it's actually 3.01 dimensional, or where it's 2.99 dimensional. And it may be that in the very early universe, it was actually infinite dimensional, and it's only a late stage phenomenon that we end up getting 3-dimensional space.
But from your perspective of the hypergraph, one of the underlying assumptions you kind of implied, but you have a sense, a hope, set of assumptions that the rules that underlie our universe, or the rule that underlies our universe, is static. Is that one of the assumptions you're currently operating under?
Yes, but there's a footnote to that which we should get to because it requires a few more steps.
Okay. Well, actually, then let's backtrack to the curvature, because we're talking about as long as it's finite dimensional.
Finite dimensional, computational irreducibility, and causal invariance. Then it follows that the large scale structure will follow Einstein's equations. And now let me again qualify that a little bit more. There's a little bit more complexity to it. So Einstein's equations in their simplest form apply to the vacuum. No matter, just the vacuum. And they say in particular, what they say is if you have, so there's this term geodesic, that's a term that means shortest path, comes from measuring shortest paths on the Earth. So you look at a bunch of, a bundle of geodesics, a bunch of shortest paths. It's like the paths that photons would take between 2 points. Then the statement of Einstein's equations is basically a statement about that as you look at a bundle of geodesics, the structure of space has to be such that although the cross-sectional area of this bundle although the actual shape of the cross-section may change, the cross-sectional area does not. That's a version, that's the most simple-minded version of r mu nu minus a half r g mu nu equals 0, which is the more mathematical version of Einstein's equations. It's a statement of a thing called the Ricci tensor is equal to 0. That's Einstein's equations for the vacuum. Okay, so we get that in as a result of this model, but footnote, big footnote, because all the matter in the universe is the stuff we actually care about. The vacuum is not stuff we care about. So the question is, how does matter come into this? And for that, you have to understand what energy is in these models. And one of the things that we realized, late last year was that there's a very simple interpretation of energy in these models. Okay, and energy is basically, well, intuitively, it's the amount of activity in these hypergraphs and the way that remains over time. So a little bit more formally, you can think about this causal graph as having these edges that represent causal relationships. You can think about, oh boy, there's one more concept that we didn't get to. What's that? The notion of space-like hypersurfaces. So this is not as scary as it sounds. Yeah. It's a common notion in general relativity. The notion is you're defining where in space-time might be a particular moment in time. So in other words, what is a consistent set of places where you can say this is happening now, so to speak, and you make this series of sort of slices through the space-time, through this causal graph to represent sort of what we consider to be successive moments in time. Okay. It's somewhat arbitrary because you can deform that if you're going at a different speed in special relativity. You tip those things. There are different kinds of deformations, but only certain deformations are allowed by the structure of the causal graph. Anyway, be that as it may, the basic point is there is a way of figuring out. You say what is the energy associated with what's going on in this hypergraph, and the answer is there is a precise definition of that. And it is, the formal way to say it is, it's the flux of causal edges through space-like hypersurfaces. The slightly less formal way to say it, it's basically the amount of activity. The reason it gets tricky is you might say it's the amount of activity per unit volume in this hypergraph, but you haven't defined what volume is. So it's a little bit, you have to be a little bit. But this
hypersurface gives some more formalism to that.
Yeah. It gives a way to connect that.
But intuitively, we should think about it as the
amount of activity. Right. So the amount of activity that kind of remains in one place in the hypergraph corresponds to energy. The amount of activity that is kind of where an activity here affects an activity somewhere else corresponds to momentum. And so one of the things that's kind of cool is that, I'm trying to think about how to say this intuitively. The mathematics is easy, but the intuitive version, I'm not sure. But basically, the way that things sort of stay in the same place and have activity is associated with rest mass. And so one of the things that you get to derive is E equals mc squared. That is a consequence of this interpretation of energy in terms of the way the causal graph works, which is the whole thing is sort of a consequence of this whole story about updates in hypergraphs and so on.
So for people curious to kind of learn more, so this is more like, this is not middle school. We're going to go to elementary school for a second. Maybe middle school. Let's go to middle school. So if I were to try to maybe write a pamphlet of like Wolfram physics project for dummies, AKA for me, or maybe make a video on the basics, but not just the basics of the physics project, but the basics plus the most beautiful central ideas. How would you go about doing that? Could you help me out a little bit?
Yeah. I mean,
We've
you know,
covered
as a really
but
practical matter, we have this kind of visual summary picture that we made.
That's right.
Which I think is a pretty good, you know, when I've tried to explain this to people, and, you know, it's a pretty good place to start. Is you got this rule, you know, you apply the rule, you're building up this big hypergraph. You've got all these possibilities. You're kind of thinking about that in terms of quantum mechanics. I mean, that's a decent place to start.
So basically, the things we've talked about, which is space represented as a hypergraph, transformation of that space is kind of time.
Yes.
And then
structure of that space, the curvature of that space as gravity. That can be explained without going anywhere near quantum mechanics. I would say that's actually easier to explain than special relativity.
So going into general, so going to curvature.
Yeah, I mean, special relativity, I think it's a little bit elaborate to explain.
Yeah.
And honestly, you only care about it if you know about special relativity, if you know how special relativity is ordinarily derived and so on.
So and general relativity is easier.
Is easier, yes.
And then what about quantum? What's the easiest way to reveal?
I think the basic point is just this fact that there are all these different branches, that there's this kind of map of how the branches work, and that, I mean, I think actually the recent things that we have about the double slit experiment are pretty good, because you can actually see this, you can see how the double slit, you know, phenomenon arises from just features of these graphs. Now, you know, having said that, right, there is a little bit of sleight of hand there, because the true story of the way that double slit thing works depends on the coordinatization of branchial space that, for example, in our internal team, there is still a vigorous battle going on about how that works. And it's what's becoming clear is that it's mathematically really quite interesting. I mean, that is that there's it involves essentially putting space-filling curves. You basically have a thing which is naturally two-dimensional, and you're sort of mapping it into one dimension with a space-filling curve. And it's like, why is it this space-filling curve and not another space-filling curve? And that becomes a story about Riemann surfaces and things, and it's quite elaborate. And there's a little bit sleight of hand way of doing it, where it's surprisingly direct.
So a question that might be difficult to answer, but for several levels of people, could you give me advice on how we can learn more? Specifically, there is people that are completely outside and just curious and are captivated by the beauty of hypergraphs, actually. So people that just want to explore, play around with this. Second level is people from, say, people like me, who somehow got a PhD in computer science, but are not physicists. But fundamentally, the work you're doing is of computational nature. So it feels very accessible.
Yes.
So what can a person like that do to learn enough physics or not to be able to, one, explore the beauty of it, and two, the final level of contribute something of a level of even publishable, strong, interesting ideas. So at all those layers, complete beginner, a CS person, and the CS person that wants to publish.
Right. I mean, I think that, I've written a bunch of stuff. A person called Jonathan Gorod, who's been a key person working on this project, has also written a bunch of stuff. And some other people have started writing things too.
And he's a physicist.
Well, I would say, a mathematical physicist. He's pretty mathematically sophisticated. He regularly out-mathematizes me.
Yeah. Strong mathematical physicist. Yeah. I looked at some of the papers.
Right. But so, I mean, I wrote this kind of original announcement blog post about this project, which people seem to have found. I've been really happy, actually, that people people seem to have grokked key points from that. Much deeper key points people seem to have grokked than I thought they would grok.
And that's a kind of a long blog post that explains some of the things we talked about, like the hypergraph and the basic rules.
Yes.
And I forget. It doesn't have any quantum mechanics.
Oh,
in
yeah.
it.
It goes
does.
through quantum mechanics. Yes,
Okay.
it does. But we know a little bit more since that blog post that probably clarifies. But that blog post does a pretty decent job. And, talking about things like, again, something we didn't mention, the fact that the uncertainty principle is a consequence of curvature in branchial space.
How much physics should a person know to be able to understand the beauty of this framework and to contribute something novel?
Okay, so I think that those are different questions. So, I mean, I think that why does this work? Why does this make any sense? To really know that, you have to know a fair amount of physics. Okay? And for example, have a decent
when you say why does this work, you're referring to the connection between this model and
general relativity, for example.
General
like
relativity.
you have to understand something about general relativity.
There's also a side of this where just as the pure mathematical framework is fascinating.
Yes.
If you throw the physics out completely.
Then it's quite accessible to, I mean, I wrote this sort of long technical introduction to the project, which seems to have been very accessible to people who are, who understand computation and formal abstract ideas, but are not specialists in physics or other kinds of things. I mean, the thing with the physics part of it is, there's both a way of thinking and literally a mathematical formalism. I mean, it's like, to know that we get the Einstein equations, to know we get the energy momentum tensor, you kind of have to know what the energy momentum tensor is. And that's physics. I mean, that's kind of graduate level physics, basically. So that, making that final connection requires some depth of physics knowledge.
I mean, that's the unfortunate thing, the difference between machine learning and physics in the 21st century. Is it really out of reach of a year or two worth of study?
No, you could get it in a year or two, but you can't get it in a month.
Right.
I mean,
but it doesn't require necessarily like 15 years.
No, it does not. And in fact, a lot of what has happened with this project makes a lot of this stuff much more accessible. There are things where it has been quite difficult to explain what's going on, and it requires much more, having the concreteness of being able to do simulations, knowing that this thing that you might have thought was just an analogy is really actually what's going on, makes one feel much more secure about just sort of saying, this is how this works. And I think it will be, I'm hoping the textbooks of the future, the physics textbooks of the future, there will be a certain compression. There will be things that used to be very much more elaborate. Because, for example, even doing continuous mathematics versus this discrete mathematics, to know how things work in continuous mathematics, you have to be talking about stuff and waving your hands about things. Whereas with the discrete version, it's just like, here is a picture. This is how it works. And there's no, did we get the limit right? Did this thing that is of, zero, measure zero object, interact with this thing in the right way? You don't have to have that whole discussion. It's just like, here's a picture. This is what it does. And, then it takes more effort to say, what does it do in the limit when the picture gets very big?
But you can do experiments to build up an intuition, actually.
Yes, right. And you can get sort of core intuition for what's going on. Now, in terms of contributing to this, I would say that the study of the computational universe and how all these programs work in the computational universe, there's just an unbelievable amount to do there. And it is very close to the surface. That is, high school kids, you can do experiments. It's not... and you can discover things. I mean, you can discover stuff about, I don't know, like this thing about expansion of branchial space. That's an absolutely accessible thing to look at. Now, the main issue with doing these things is there isn't a lot of technical difficulty there. The actual doing of the experiments, all the code is all on our website to do all these things. The real thing is sort of the judgment of what's the right experiment to do, how do you interpret what you see. That's the part that, people will do amazing things with, and that's the part that, but it isn't like you have to have done 10 years of study to get to the point where you can do the experiments. You don't.
That's a cool thing. You can do experiments day one, basically.
Right.
That's the amazing thing about, and you've actually put the tools out there.
Yep.
As beautiful, as mysterious. There's still, I would say, maybe you can correct me, it feels like there's a huge number of low-hanging fruit.
Oh, there is.
On the mathematical side, at least, not the physics side, perhaps.
No, look, on the physics side, we're definitely in harvesting mode.
You know,
Of which fruit? The low-hanging ones or
the low-hanging ones.
All right.
Yeah, right. I mean, basically, here's the thing. There's a certain list of, here are the effects in quantum mechanics, here are the effects in general relativity. It's just like industrial harvesting. It's like, can we get this one, this one, this one, this one, this one? And the thing that's really, interesting and satisfying, and it's like, is one climbing the right mountain? Does one have the right model? The thing that's just amazing is, we keep on like, are we going to get this one? How hard is this one? It's like, oh, it looks really hard. It looks really hard. Oh, actually, we can get it. And
you're continually surprised. I mean, it seems like I've been following your progress. It's kind of exciting, all the in harvesting mode, all the things you're picking up along the way.
Right. No, I mean, it's the thing that is, I keep on thinking it's going to be more difficult than it is. Now that's who knows what, I mean, the one thing, so the thing that's been was a big thing that I think we're pretty close to. I mean, I can give you a little bit of the roadmap. It's sort of interesting to see. It's like, what are particles? What are things like electrons? How do they really work?
Are you close to get like are you close to trying to understand like the atom, the electrons, neutrons, protons? Like
okay, so this is the stack. So the first thing we want to understand is the quantization of spin. So particles, they kind of spin. They have a certain angular momentum. That angular momentum, even though the masses of particles are all over the place. The electron has a mass of 0.511 MeV. The proton is 938 MeV, et cetera, et cetera, et cetera. They're all kind of random numbers. The spins of all these particles are either integers or half integers. Mm-hmm. And that's a fact that was discovered in the 1920s, I guess. I think that we are close to understanding why spin is quantized. And it appears to be a quite elaborate mathematical story about homotopy groups in twistor space and all kinds of things. But bottom line is that seems within reach. And that's a big deal because that's a very core feature of understanding how particles work in quantum mechanics. Another core feature is this difference between particles that obey the exclusion principle and sort of stay apart, that leads to the stability of matter and things like that, and particles that love to get together and be in the same state, things like photons, and that's what leads to phenomena like lasers, where you can get sort of coherently everything in the same state. Mm-hmm. That difference is the particles of integer spin are bosons, like to get together in the same state. The particles of half integer spin are fermions, like electrons, that they tend to stay apart. And so the question is, can we get that in our models? And just the last few days, I think we made. I think the story of. It's one of these things where we're really close. It's
this connected fermions and bosons? You're talking about?
So this was what happens is what seems to happen. Okay, it's subject to revision next few days. But what seems to be the case is that bosons are associated with essentially merging in multi-way graphs, and fermions are associated with branching in multi-way graphs, and that essentially the exclusion principle is the fact that in branchial space, things have a certain extent in branchial space that in which things are being sort of forced apart in branchial space, whereas the case of bosons, they clump together in branchial space. And the real question is, can we explain the relationship between that and these things called spinors, which are the representation of half-integer spin particles that have this weird feature that usually when you go around 360-degree rotation, you get back to where you started from. But for a spinor, you don't get back to where you started from. It takes 720 degrees of rotation to get back to where you started from. And we are just, it feels like we're just incredibly close to actually having that, understanding how that works. And it turns out it looks like, my current speculation is, that it's as simple as the directed hypergraphs versus undirected hypergraphs.
Oh, interesting.
The relationship between spinors and vectors. So, which
nice,
is just
interesting. Yeah, that would be interesting if these are all these kind of nice properties of this multi-way graphs of branching and,
right, but
rejoining.
But spinors have been very mysterious, and if that's what they turn out to be, there's going to be an easy explanation of what's going on.
It's directed versus undirected.
It's just, and that's why there's only two different cases.
Why are spinors important in quantum mechanics? Can you just give a?
So spinors are important because they are they're the representation of for electrons which have half integer spin. They are the wave functions of electrons are spinors. Just like the wave functions of photons are vectors, the wave functions of electrons are spinors. And they have this property that when you rotate by 360 degrees, they come back to -1 of themselves, and it takes 720 degrees to get back to the original value. And they are a consequence and we usually think of rotation in space as being, when you have this notion of rotational invariance. And rotational invariance, as we ordinarily experience it, doesn't have the feature. If you go through 360 degrees, you go back to where you started from. But that's not true for electrons. And so that's why understanding how that works is important.
Yeah, I've been playing with Mobius strip quite a bit lately, just for fun. And
yes.
It adds some funk. It has the same kind of funky properties.
Yes, right, exactly. You can have there's the so-called belt trick, which is this way of taking an extended object, and you can see properties like spinors with that kind of extended object. That
it would be very cool if it somehow connects the directive versus undirected.
I think that's what it's going to be. I think it's going to be as simple as that, but we'll see. I mean, this is the thing that this is the big sort of bizarre surprise is that because I learned physics as probably. Let's say a fifth generation, in the sense that, if you go back to the 1920s and so on, there were the people who were originating quantum mechanics and so on. Maybe it's a little less than that. Maybe I was like a third generation or something. I don't know. But the people from whom I learnt physics were the people who were, who've been students of the people who originated the current understanding of physics. And we're now at, probably the seventh generation of physicists or something from the early days of 20th century physics. And, whenever a field gets that many generations deep, it seems the foundations seem quite inaccessible. Mm-hmm. And they seem, it seems like you can't possibly understand that. We've gone through, 7 academic generations, and that's been this thing that's been difficult to understand for that long. It just can't be that simple. But
in a sense, maybe that journey takes you to a simple explanation that was there all along. That's
right,
the whole.
Right. I mean, and the thing for me personally, the thing that's been quite interesting is, I didn't expect this project to work in this way, and but I had this sort of weird piece of personal history that I used to be a physicist, and I used to do all this stuff, and I know, the standard canon of physics, I knew it very well, and but then I'd been working on this kind of computational paradigm for basically 40 years. And the fact that, I'm sort of now coming back to trying to apply that in physics, it kind of felt like that journey was necessary.
When did you first try to play with a hypergraph?
So what happened recent? So what I had was, so this is again, one always feels dumb after the fact. It's obvious after the fact. But so back in the early 1990s, I realized that using graphs as a sort of underlying thing underneath space and time was going to be a useful thing to do. I figured out about multi-way systems. I figured out the things about general relativity I'd figured out by the end of the 1990s. But I always felt there was a certain inelegance because I was using these graphs, and there were certain constraints on these graphs that seemed like they were kind of awkward. It was kind of like, it's like you couldn't pick any rule. It was like you pick any number, but the number has to be prime. It was kind of like you couldn't, it was a kind of an awkward special constraint. I had these trivalent graphs with just 3 connections from every node. Okay, so, but I discovered a bunch of stuff with that. But I thought it was kind of inelegant. And, the other piece of sort of personal history is obviously I spent my life as a computational language designer. And so the story of computational language design is a story of how do you take all these random ideas in the world and kind of grind them down into something that is computationally as simple as possible. And so, I've been very interested in kind of simple computational frameworks for representing things and have, ridiculous amounts of experience in trying to do that.
And actually all of those trajectories of your life kind of came together. So you make it sound like you could have come up with everything you're working on now decades ago, but in reality...
Look, 2 things slowed me down. I mean, one thing that slowed me down was I couldn't figure out how to make it elegant. And that turns out hypergraphs were the key to that, and that I figured out about less than 2 years ago now. The I mean, I think so. That was sort of a key thing. Well, okay. So the real embarrassment of this project, okay, is that the final structure that we have, that is the foundation for this project, is basically a kind of an idealized version, a formalized version of the exact same structure that I've used to build computational languages for more than 40 years.
Yeah.
But it took me, I didn't realize that. Yeah. And you know,
there yet may be other, so we're focused on physics now, but I mean, that's what the new kind of science is about, same kind of stuff. And this, in terms of mathematically, the beauty of it, so there could be entire other kind of objects that are useful for, like, we're not talking about, you know, machine learning, for example. Maybe there's other variants of the hypergraph that are very useful for reasoning.
Well, we'll see whether the multi-way graph for a machine learning system is interesting. Okay,
let's leave it at that. That's conversation number 3.
That's we're not going to go there right now.
You said that there are moments in history of physics, and maybe mathematical physics or even mathematics, where breakthroughs happen and then a flurry of progress follows. So if you look back through the history of physics, what moments stand out to you as important such breakthroughs where a flurry of progress follows?
So the big famous one was 1920s, the invention of quantum mechanics, where, you know, in about 5 or 10 years, lots of stuff got figured out. That's now quantum mechanics.
Can you mention the people involved?
Yeah, that was kind of the Schrödinger, Heisenberg, you know, Einstein had been a key figure, originally Planck, then Dirac was a little bit later. That was something that happened at that time. That's sort of before my time, right? In my time was in the 1970s. There was this sort of realization that quantum field theory was actually going to be useful in physics. And QCD, quantum chromodynamics theory of quarks and gluons and so on, was really getting started. And there was, again, sort of big flurry of things happened then. I happened to be a teenager at that time and happened to be really involved in physics. And so I got to be part of that, which was really cool.
Who were the key figures, aside from your young selves at that time?
You know, who won the Nobel Prize for QCD? Okay, people, David Gross, Frank Wilczek, you know, David Politzer. The people who are the sort of the slightly older generation, Dick Feynman, Murray Gell-Mann, people like that, who were Steve Weinberg, Gerhard Hopfield. He's younger. He's in the younger group, actually. But these are all, you know, characters who were involved. I mean, it was, you know, it's funny because those are all people who are kind of in my time, and I know them, and they don't seem like sort of these historical, you know, iconic figures. They seem more like everyday characters, so to speak. So it's always, you know, when you look at history from long afterwards, it always seems like everything happened instantly. And that's usually not the case. There was usually a long build-up. But usually there's some methodological thing happens, and then there's a whole bunch of low-hanging fruit to be picked. And that usually lasts 5 or 10 years. You know, we see it today with machine learning and, you know, deep learning neural nets and so on. You know, methodological advance, things actually started working in, you know, 2011, 2012 and so on. And, you know, there's been this sort of rapid picking of low-hanging fruit, which is probably, you know, some significant fraction of the way done, so to speak.
Do you think there's a key moment? Like, if I had to really introspect, like, what was the key moment for the deep learning, quote unquote, revolution? I mean,
it's probably the AlexNet business.
AlexNet with ImageNet. So is there something like that with physics where, so deep learning neural networks have been around for a long time.
Absolutely.
There's a bunch of
1940s. Yeah.
There's a bunch of little pieces that came together, and then all of a sudden everybody's eyes lit up. Like, wow, there's something here. Like, even just looking at your own work, just your thinking about the universe, that there's simple rules can create complexity. You know, at which point was there a thing where your eyes light up? It's like, wait a minute, there's something here. Is it the very first idea, or is it some moment along the line of implementations and experiments and so on?
There's a couple of different stages to this. I mean, one is the think about the world computationally. You know, can we use programs instead of equations to make models of the world? That's something that I got interested in at the beginning of the 1980s. I did a bunch of computer experiments. When I first did them, I didn't really, I could see some significance to them, but it took me a few years to really say, wow, there's a big important phenomenon here that lets sort of complex things arise from very simple programs. That kind of happened back in 1984 or so. Then, a bunch of other years go by. Then I start actually doing a lot of much more systematic computer experiments and things, and find out that this phenomenon that I could only have said occurs in one particular case is actually something incredibly general. And then that led me to this thing called principle of computational equivalence. And that was a long story. And then, as part of that process, I was like, okay, you can make simple programs, can make models of complicated things. What about the whole universe? That's our sort of ultimate example of a complicated thing.
Yeah.
And so I got to thinking, could we use these ideas to study fundamental physics? I happen to know a lot about, traditional fundamental physics. My first, I had a bunch of ideas about how to do this in the early 1990s. I made a bunch of technical progress. I figured out a bunch of things I thought were pretty interesting. I wrote about them back in 2002.
With the new kind of science in the cellular automata world. And
right.
There's echoes in the cellular automata world with your new Wolfram physics project world. We'll get to all that. Allow me to sort of romanticize a little more on the philosophy of science. As a small tangent, or actually a very big tangent, but proof by compilation is a beautiful concept. In a sense, the way of doing physics with this model is by running it or compiling it. And
at some level, yes.
Have you thought about, and these things can be very large, is there totally new possibilities of computing hardware and computing software, which allows you to perform this kind of compilation?
Well,
algorithms, software, hardware.
So first comment is, these models seem to give one a lot of intuition about distributed computing, a lot of different intuition about how to think about parallel computation. And that particularly comes from the quantum mechanics side of things, which we didn't talk about much yet. But the question of what, given our current computer hardware, how can we most efficiently simulate things?
Yeah.
That's actually partly a story of the model itself, because the model itself has deep parallelism in it.
Yes.
The ways that we are simulating it, we're just starting to be able to use that deep parallelism to be able to be more efficient in the way that we simulate things. Yeah. But in fact, the structure of the model itself allows us to think about parallel computation in different ways. And one of my realizations is that, so it's very hard to get in your brain how you deal with parallel computation. And you're always worrying about, if multiple things can happen on different computers at different times, what happens if this thing happens before that thing? And we've really got, we have these race conditions where something can race to get to the answer before another thing, and you get all tangled up because you don't know which thing is going to come in first. And usually when you do parallel computing, there's a big obsession to lock things down to the point where you've had locks and mutexes and God knows what else, where you've arranged it so that there can only be one sequence of things that can happen. So you don't have to think about all the different kinds of things that can happen. Well, in these models, physics is throwing us into forcing us to think about all these possible things that can happen. But these models, together with what we know from physics, is giving us new ways to think about all possible things happening, about all these different things happening in parallel. And so I'm guessing
they have built-in protection for some of the parallelism.
Well, causal invariance is the built-in protection. Causal invariance is what means that even though things happen in different orders, it doesn't matter in the end.
As a person who struggled with concurrent programming in in like Java, with all the basic concepts of concurrent programming, that if there could be built up a strong mathematical framework for causal invariance, that's so liberating. And well, that could be not just liberating, but really powerful for massively distributed computation.
Absolutely. No, I mean, what's eventual consistency in distributed databases is essentially the causal invariance idea.
Yeah.
Okay. So that's, but
have you thought about, we're like really large simulations?
Yeah. I mean, I'm also thinking about, look, the fact is, I've spent much of my life as a language designer, right? Yes. So I can't possibly not think about, what does this mean for designing languages for parallel computation? In fact, another thing that's one of these, I'm always embarrassed at how long it's taken me to figure stuff out. But, back in the 1980s, I worked on trying to make up languages for parallel computation. I thought about doing graph rewriting. I thought about doing these kinds of things, but I couldn't see how to actually make the connections to actually do something useful. I think now physics is kind of showing us how to make those things useful. And so my guess is that in time, we'll be talking about, we do parallel programming. We'll be talking about programming in a certain reference frame, just as we thinking about physics in a certain reference frame. It's a certain coordinatization of what's going on. We say, we're going to program in this reference frame. Oh, let's change the reference frame to this reference frame. And then our program will seem different and we'll have a different way to think about it, but it's still the same.
Tell me something.
Let's continue the deep analysis of your tweets. You said that determinism in a tweet, determinism and randomness play important roles in understanding what life is.
Yeah.
So let me ask on this topic of free will, what is determinism? What is randomness? And why the heck do they have anything to do with understanding life?
Yeah. And you threw free will in there. You're just throwing all the stuff in the bag.
Are they not related?
No, they are related. No, that's all right. I was being unfair.
You didn't even capitalize the tweet, by the way. It was all lowercase.
I must have been angry.
Oh, that was can you analyze the emotion behind that?
No, I actually did.
Frustration or
yeah,
hope?
Maybe. So I already argued that I don't think that can happen without that whole causal history. And so I guess in some sense, the determinism for me arises because of the causal history. Mm-hmm. And I'm not really sure actually about whether the universe is random or deterministic. I just had this sort of intuition for a long time. I'm not sure if I agree with it anymore, but it's still kind of lingering and I don't know what to do with this question. But it seems to me, so you asked the question, what is life? But you could also, why life? Why does life exist? What does the universe need life for? Not that the universe has needs, but we have to anthropocentrize things sometimes to talk about them. And I had this feeling that if it was possible for a cup or a desk ornament or a phone on Mars to spontaneously fluctuate into existence, the universe didn't need life to create those objects. It wasn't necessary for their existence. It was just a random fluke event. And so somehow to me, it seems that it can't be that those things form by random processes. They actually have to have a set of causes that accrue and form those things, and they have to have that history. And so it seems to me that life was somehow deeply related to the question of whether the underlying rules of our universe had randomness in them or they were fully deterministic. And in some ways, you can think about life as being the most deterministic part of physics because it's where the causes are precise in some sense.
Or most stable. So
stable, yes, most reliable.
Most reliable
yeah.
for the tools of physics. But what
right, well, so
where's the randomness come from then? So you were at speaking with
I've gone in a tangent, so I'm not sure where we are in the
all of the universe is a kind of tangent. So we're embracing the tangent
at depth. But the other way of kind of thinking about it in terms of like a more physicsy way of talking about it is that what it looks like in biology is that the rules or the laws depend on the state. This is typical in computer science. This is obvious to you. The update rule depends on the state of the machine, right? But you don't think about that being sort of the dynamic in physics. It's the rules given to you, and then it's a very special subclass, say, of computations if you don't ever change the update. But in biology, it seems to be that the state and the law change together as a function of time. And we don't have that as a paradigm in physics. And so a lot of people talked about this as being kind of a perplexing feature, that maybe there are certain scenarios where the laws of physics or the laws that govern a particular system actually change as a function of the state of that system.
That's trippy.
Yeah.
So the hope of physics, it's a hope, I guess, but often stated as a underlying assumption is that the law is static.
Right.
Okay.
And even having laws that vary in time, not even as a function of the state, is very radical.
Time in general, you want to remove time from the equation as much as possible.
Yeah. I do. There's some interesting things in this, like when we think sort of more deeply about the actual physics that we're trying to propose governs life, with collaborators, and then also other people that think about similar things, that time might actually be fundamental, and there really is an ordering to time. And that events in the universe are unique because they have a particular, they happen, like an object in the universe requires a certain history of events in order to exist, which therefore suggests that time really does have an ordering. I'm not talking about the flow of time and our perception of time, just the ordering of events.
Causation of things.
Yes, causation. There's that word again.
So causation, that's when you say time, you mean causation.
Yes.
In your proposed model of the physics of life, the fundamental thing would be causation. If you were to bet your money on one particular horse or whatever.
Yes.
And then space is emergent?
Yes.
So everything is emergent except time.
Kind of. Yeah, or causation.
And laws
I would say
change
causation.
all the time? Why does it look like laws are the same?
Because one way, and this idea comes from Lee Cronin because I work with him very closely on these things, is that the laws of physics look the way they do because they're low memory laws. So they don't require a lot of information to specify them. They're very easy for the universe to implement. But if you get something like me, for example, I require a 4 billion year history to exist in the universe. I come with a lot of historical baggage. And that's part of what I am as a set of causes that exist in the universe. So I have local rules that apply to me that are associated with sort of the information in my history that aren't universal to every object in the universe. And there are some things that are very easy to implement, low memory rules that apply to everything in the universe.
So there's no shortcuts to you?
No. I don't believe in things like Boltzmann brains or, fluctuations out of the vacuum that can produce things like your desk ornaments. I actually think they require a particular causal chain of events to exist.
Well, I appreciate the togetherness of that. But so how does that, if we have to simulate the entire universe to create the ornaments and the two of us, how are we supposed to engineer life?
Yeah, that's
in the lab.
This goes back to sort of the critique of the RNA world. I think one of the problems, and I'll get to answering your question, but I think this is kind of relevant here. Mm-hmm. One of the problems with the RNA world, when we test it in the laboratory, is how much information we're putting into the experiment. We specify the flasks, we make pure reagents, we mix them, we take them out, we put them in the next flask, we change the pH, we change the UV light, and then we get a molecule. And it's not even an RNA molecule necessarily, it might just be a base, right? And so people don't usually think about the fact that we're agents in the universe making that experiment, and therefore we put a little bit of life into that experiment. Because it's part of our biological lineage, in the same sense that a cup or I am a part of the biological lineage. The experiment
our ideas are injecting life.
Yes.
To the
and the constraints that we put on the experiments. Because those conditions wouldn't exist in the universe on planet Earth at that time without us as the boundary condition, right? So
even though we're not actually adding any actual chemistry or biology that it could be identified as life, the constraints we're adding to the experiment, the design of the experiment.
Yeah, you can think of the design experiment as a program. You put information in. It's an algorithmic procedure that you design the experiment. And so the origin of life problem becomes one of minimizing the information we put into physics to actually watch the spontaneous origin of life.
Is it possible in the lab to have an information vacuum then? So
if we could, that would be amazing. I don't know. That's a good question for Lee.
Yeah, you guys, by the way, for people who don't know, Lee Cronin is you guys are colleagues, and I've gotten the chance to listen to the two of you talk, and there's great sort of chemistry, and you're brilliant brainstorming together, and there's a really exciting community here of brilliant people from different disciplines working on the problem of life, of complexity, of I don't know, whatever the words fail us to describe the exact problem we're trying to actually understand here, intelligence, all those kinds of things. Okay, so what from a lab perspective? So Lee, I guess, would you call him a chemist? No?
I think by training he's a chemist, but I think most of the people that work in the field we do have lost their discipline. That's why I couldn't answer your question earlier.
Okay.
I don't know what you call him.
Yeah.
I don't know what I call myself. I don't know what I call any of my friends.
So why is it so hard to create, and it's an interesting question, to create biological life in the lab? From your perspective, is that an important problem to work on, to try to recreate the historical origin of life on Earth, or echoes of the historical origin?
I think echoes is more appropriate. I don't think asking the question of what was the exact historical sequence of events and engineering every step in the process to make exactly the chemistry of life on Earth as we know it is a meaningful way of asking the question. Right. And it's a little bit like, since you're in computer science, like if you know the answer to a problem, it's easier to find a program to specify the output, right? But if you don't know the answer a priori, finding an algorithm for, like, say, finding a prime or something, it's easy to, verify it's a prime number. It's hard to find the next prime. The way the origin of life is structured right now in the historical problem is the answer and you're trying to retrodict it by breaking it down into the set of procedures where you're putting a lot of information in. And what we need to do is ask the question of how is it that the rules of how our universe is structured permit things like life to exist, and what is the phenomena of life? And those questions are obviously essentially the same question. And so you're looking essentially for this missing physics, this missing explanation for what we are, and you need to set up proper experiments that are going to allow you to probe the vast complexity of chemistry in an unconstrained way with as little information put in as possible to see when does information actually emerge? How does it emerge? What is it? Part of the sort of conjecture we have is that this physics only becomes relevant, or at least this is my personal conjecture, and it's sort of validated by this kind of theory experiment collaboration that we have working in this area. That this, sort of, I made the point about like gravity existing everywhere, right? But when you study an atomic nucleus, you don't care about gravity. It's not relevant physics there, right? It's weak. It doesn't matter. And so this idea that there's kind of a physics associated with information, for me, it's very evident that physics doesn't become relevant until you need information to specify the existence of a particular object. And the scale of reality where that happens is in chemistry, because of the combinatorial diversity of chemical objects that can exist far exceeds the amount of resources in our universe. So if you want it, you can't make every possible protein of length 200 amino acids. There's not enough resources. So in order for this particular protein to exist, and this protein to exist in high abundance, means that you have to have a system that has knowledge of the existence of that protein and can build it.
So existence comes to be at the chemical level. So existence is best understood at the chemical level. It's most
evident. It's a little bit like nobody argues that gravity doesn't exist in an atomic nucleus. It's just not relevant physics there.
So the physics of information
is everywhere. It exists at every combinatorial scale, but it becomes more and more relevant the more set of possibilities that could exist, because you have to specify more and more about why this thing exists and not the infinite. It's not an infinite set, but the set of undefined set of other things that could exist.
So can I ask a weird question, which is
to live in? Well, okay, so we're talking about kind of the quest to find the fundamental theory of physics. First point is, it's turned out it's kind of hard to find the fundamental theory of physics. People weren't sure that would be the case. Back in the early days of applying mathematics to science, 1600s and so on, people were like, oh, in 100 years we'll know everything there is to know about how the universe works. Turned out to be harder than that. And people got kind of humble at some level, because every time we got to sort of a greater level of smallness in studying the universe, it seemed like the math got more complicated and everything got harder. Mm-hmm. When I was a kid, basically, I started doing particle physics. And, when I was doing particle physics, I always thought finding the fundamental theory of physics, that's a kooky business. We'll never be able to do that. But we can operate within these frameworks that we built for doing quantum field theory and general relativity and things like this, and it's all good, and we can figure out a lot of stuff.
Did you even at that time have a sense that there's something behind that too?
Sure. I just didn't expect that. I thought in some rather it's actually kind of crazy in thinking back on it, because it's kind of like there was this long period in civilization where people thought the ancients had it all figured out and will never figure out anything new.
Right.
And to some extent, that's the way I felt about physics when I was in the middle of doing it, so to speak, was, we've got quantum field theory. It's the foundation of what we're doing. And there's, yes, there's probably something underneath this, but we'll sort of never figure it out. But then I started studying simple programs in the computational universe, things like cellular automata and so on. And I discovered that they do all kinds of things that were completely at odds with the intuition that I had had. And so after you see this tiny little program that does all this amazingly complicated stuff, then you start feeling a bit more ambitious about physics and saying, maybe we could do this for physics too. And so that got me started years ago now in this kind of idea of, could we actually find what's underneath all of these frameworks like quantum field theory and general relativity and so on. And people perhaps don't realize as clearly as they might that, the frameworks we're using for physics, which is basically these two things, quantum field theory, the theory of small stuff, and general relativity, theory of gravitation and large stuff. Those are the two basic theories, and they're 100 years old. I mean, general relativity was 1915, quantum field theory, 1920s. So basically 100 years old. And it's been a good run. There's a lot of stuff been figured out. But what's interesting is the foundations haven't changed in all that period of time. Even though the foundations had changed several times before that, in the 200 years earlier than that. And I think the kinds of things that I'm thinking about, which are sort of really informed by thinking about computation and the computational universe, it's a different foundation. It's a different set of foundations, and might be wrong, but it is at least, we have a shot. And I think it's, to me, it's, my personal calculation for myself is, if it turns out that finding the fundamental theory of physics, it's kind of low-hanging fruit, so to speak. It'd be a shame if we just didn't think to do it. If people just said, oh, you'll never figure that stuff out. Let's, and it takes another 200 years before anybody gets around to doing it. I think it's, I don't know how low-hanging this fruit actually is. It may be, that, it's kind of the wrong century to do this project. I mean, I think the cautionary tale for me, I think about things that I've tried to do in technology where people thought about doing them a lot earlier. I mean, my favorite example is probably Leibniz, who thought about essentially encapsulating the world's knowledge in a computational form in the late 1600s, and did a lot of things towards that. And basically, we finally managed to do this, but he was 300 years too early. Yeah. And that's kind of in terms of life planning, it's kind of like avoid things that can't be done in your century, so to speak.
Yeah, timing is everything. So you think if we kind of figure out the underlying rules it can create from which quantum field theory and general relativity can emerge, do you think that'll help us unify it at that level of abstraction?
Oh, we'll know it completely. We'll know how that all fits together. Yes, without a question. And I mean, it's already, even the things I've already done, they're very, it's very, very elegant, actually, how things seem to be fitting together. Now, is it right? I don't know yet. It's awfully suggestive. If it isn't right, it's then the designer of the universe should feel embarrassed, so to speak, because it's a really good way to do it.
And your intuition in terms of designing a universe, does God play dice? Is there randomness in this thing, or is it deterministic? So the kind of
that's a little bit of a complicated question, because when you're dealing with these things that involve these rewrites that have
even randomness is an emergent phenomenon, perhaps.
Yes. I mean, randomness in many of these systems, pseudo-randomness and randomness are hard to distinguish. Yeah. In this particular case, the current idea that we have about measurement in quantum mechanics is something very bizarre and very abstract, and I don't think I can yet explain it without kind of yakking about very technical things. Eventually, I will be able to, but if that's right, it's kind of it's a weird thing, because it slices between determinism and randomness in a weird way that hasn't been sliced before, so to speak. So like many of these questions that come up in science, where it's like, is it this or is it that? Turns out the real answer is it's neither of those things. It's something kind of different and sort of orthogonal to those categories. And so that's the current, this week's idea about how that might work. But we'll see how that unfolds. I mean, there's this question about a field like physics and sort of the quest for a fundamental theory and so on. And there's both the science of what happens and there's the sort of the social aspect of what happens. Because, in a field that is basically as old as physics, we're at, I don't know what it is, fourth generation, I don't know, fifth generation, I don't know what generation it is of physicists. And I was one of these, so to speak. And for me, the foundations were like the pyramids, so to speak. It was that way and it was always that way. It is difficult in an old field to go back to the foundations and think about rewriting them. It's a lot easier in young fields where you're still dealing with the first generation of people who invented the field. And it tends to be the case, that the nature of what happens in science tends to be, you'll get, typically the pattern is some methodological advance occurs. And then there's a period of 5 years, 10 years, maybe a little bit longer than that, where there's lots of things that are now made possible by that methodological advance, whether it's, telescopes or whether that's some mathematical method or something. It's, there's something happens, a tool gets built, and then you can do a bunch of stuff. And there's a bunch of low-hanging fruit to be picked. And that takes a certain amount of time. After that, all that low-hanging fruit is picked, then it's a hard slog for the next however many decades or century or more to get to the next sort of level at which one can do something. And it's kind of and it tends to be the case that in fields that are in that kind of, I wouldn't say cruise mode because it's really hard work, but it's very hard work for very incremental progress.
And then in your career and some of the things you've taken on, it feels like you haven't been afraid of the hard slog.
Yeah, that's true.
So it's quite interesting, especially on the engineering side. What kind of computation do you think the fundamental laws of physics might emerge from? So just to clarify, so you've done a lot of fascinating work with kind of discrete kinds of computation that because cellular automata, and we'll talk about it, have this very clean structure. It's such a nice way to demonstrate that simple rules can create immense complexity. But what is that actually, are cellular automata sufficiently general to describe the kinds of computation that might create the laws of physics? Can you give a sense of what kind of computation do you think would create laws of physics?
So this is a slightly complicated issue because as soon as you have universal computation, you can in principle simulate anything with anything.
Right.
But it is not a natural thing to do. And if you're asking, were you to try to find our physical universe by looking at possible programs in the computational universe of all possible programs, would the ones that correspond to our universe be small and simple enough that we might find them by searching that computational universe? We got to have the right basis, so to speak. We got to have the right language, in effect, for describing computation for that to be feasible. So the thing that I've been interested in for a long time is, what are the most structureless structures that we can create with computation? So, in other words, if you say a cellular automaton, it has a bunch of cells that are arrayed on a grid, and it's very, and every cell is updated in synchrony at a particular, when there's a click of a clock, so to speak, and it goes a tick of a clock, and every cell gets updated at the same time. That's a very specific, very rigid kind of thing. But my guess is that when we look at physics and we look at things like space and time, that what's underneath space and time is something as structureless as possible. That what we see, what emerges for us as physical space, for example, comes from something that is sort of arbitrarily unstructured underneath. And so I've been for a long time interested in kind of what are the most structureless structures that we can set up. And actually what I had thought about for ages is using graphs, networks, where essentially, so let's talk about space, for example. Mm-hmm. So what is space? Is a kind of a question one might ask. Back in the early days of quantum mechanics, for example, people said, oh, for sure, space is going to be discrete because all these other things we're finding are discrete. But that never worked out in physics. And so space in physics today is always treated as this continuous thing, just like Euclid imagined it. I mean, the very first thing Euclid says in his sort of common notions is, a point is something which has no part. In other words, there are points that are arbitrarily small, and there's a continuum of possible positions of points. And the question is that true? And so, for example, if we look at, a fluid like air or water, we might say, it's a continuous fluid. We can pour it. We can do all kinds of things continuously. But actually, we know, because we know the physics of it, that it consists of a bunch of discrete molecules bouncing around, and only in the aggregate is it behaving like a continuum. And so the possibility exists that that's true of space too. People haven't managed to make that work with existing frameworks in physics. But I've been interested in whether one can imagine that underneath space and also underneath time is something more structureless. And the question is it computational? So there are a couple of possibilities. It could be computational, somehow fundamentally equivalent to a Turing machine, or it could be fundamentally not. So how could it not be? It could not be. So a Turing machine essentially deals with integers, whole numbers at some level. And, it can do things like it can add 1 to a number. It can do things like this.
It can also store whatever the heck it did.
Yes, right? So it has an infinite storage. But what when one thinks about doing physics or sort of idealized physics or idealized mathematics, one can deal with real numbers with an infinite number of digits. Yeah. Numbers which are absolutely precise, and one can say, we can take this number and we can multiply it by itself.
Are you comfortable with infinity in this context? Are you comfortable in the context of computation? Do you think infinity plays a part?
I think that the role of infinity is complicated. Infinity is useful in conceptualizing things. It's not actualizable. Almost by definition, it's not actualizable.
But do you think infinity is part of the thing that might underlie the laws of physics?
I think that, no. I think there are many questions that you might ask about physics, which inevitably involve infinity. Like when you say, is faster than light travel possible? You could say, given the laws of physics, can you make something even arbitrarily large, even quotes infinitely large, that will make faster than light travel possible? Then you're thrown into dealing with infinity as a kind of theoretical question. But I mean, talking about sort of what's underneath space and time and how one can make, a computational infrastructure. One possibility is that you can't make a computational infrastructure in a Turing machine sense, that you really have to be dealing with precise real numbers. You're dealing with partial differential equations, which have precise real numbers at arbitrarily closely separated points. You have a continuum for everything. Could be that's what happens, that there's sort of a continuum for everything and precise real numbers for everything. And then the things I'm thinking about are wrong. And, that's the risk you take if you're trying to sort of do things about nature, is you might just be wrong. It's for me personally, it's kind of a strange thing, because I've spent a lot of my life building technology where you can do something that nobody cares about, but you can't be sort of wrong in that sense, in the sense you build your technology and it does what it does. Yeah. But I think, this question of what the sort of underlying computational infrastructure for the universe might be, yes. It's sort of inevitable it's going to be fairly abstract, because if you're going to get all these things, like there are 3 dimensions of space, there are electrons, there are muons, there are quarks, there are this, you don't get to, if the model for the universe is simple, you don't get to have sort of a line of code for each of those things. You don't get to have sort of the muon case, the tau lepton case, and so on.
Those all have to be emergent somehow.
Right. So
something deeper.
Right. So that means it's sort of inevitable that it's a little hard to talk about what the sort of underlying structureless structure actually is.
Do you think our human beings have the cognitive capacity to understand, if we're to discover it, to understand the kinds of simple structure from which these laws can emerge? Like, do you think
that's
it's
a good question?
Pursuit?
Well, here's what I think. I think that, I'm right in the middle of this right now.
Right.
So I'm telling you that
this human,
yeah, this human has a hard time understanding, yes, a bunch of the things that are going on. But what happens in understanding is one builds waypoints. If you said, understand modern 21st century mathematics, starting from, counting back in, whenever counting was invented 50,000 years ago, whatever it was, right? That will be really difficult, But what happens is we build waypoints that allow us to get to higher levels of understanding. And we see the same thing happening in language. When we invent a word for something, it provides kind of a cognitive anchor, a kind of a waypoint that lets us, like a podcast or something. You could be explaining, well, it's a thing which works this way, that way, the other way. But as soon as you have the word podcast and people kind of societally understand it, you start to be able to build on top of that. And so I think, and that's kind of the story of science, actually, too. I mean, science is about building these kind of waypoints where we find this sort of cognitive mechanism for understanding something, then we can build on top of it. We have the idea of, differential equations. We can build on top of that. We have this idea, that idea. So my hope is that if it is the case that we have to go all the way sort of from the sand to the computer and there's no waypoints in between, then we're toast. We won't be able to do that.
Well, eventually we might. So if we're us clever apes are good enough at building those abstractions, eventually from sand we'll get to the computer, right? And it just might be a longer journey.
The question is whether it is something that you asked, whether our human brains will quotes understand what's going on. And that's a different question, because for that, it requires steps that are sort of from which we can construct a human understandable narrative. And that's something that I think I am somewhat hopeful that will be possible. Mm-hmm. Although, as of literally today, if you ask me, I'm confronted with things that I don't understand very well.
So this is a small pattern in the computation trying to understand the rules under which the computation functions. And it's an interesting possibility under which kinds of computations such a creature can understand itself.
My guess is that so we didn't talk much about computational irreducibility, but it's a consequence of this principle of computational equivalence. And it's sort of a core idea that one has to understand, I think, which is, the question is, you're doing a computation, you can figure out what happens in the computation just by running every step in the computation and seeing what happens. Or you can say, let me jump ahead and figure out, have something smarter that figures out what's going to happen before it actually happens. And a lot of traditional science has been about that act of computational reducibility. Yes. It's like we've got these equations and we can just solve them and we can figure out what's going to happen. We don't have to trace all of those steps. We just jump ahead because we solved these equations. Okay, so one of the things that is a consequence of the principle of computational equivalence is you don't always get to do that. Many, many systems will be computationally irreducible in the sense that the only way to find out what they do is just follow each step and see what happens. Yeah. Why is that? Well, if you're saying, well, we, with our brains, we're a lot smarter. We don't have to mess around like the little cellular automaton going through and updating all those cells. We can just, use the power of our brains to jump ahead. But if the principle of computational equivalence is right, that's not going to be correct, because it means that there's us doing our computation in our brains. There's a little cellular automaton doing its computation. And the principle of computational equivalence says these two computations are fundamentally equivalent. So that means we don't get to say we're a lot smarter than the cellular automaton and jump ahead, because we're just doing computation that's of the same sophistication as the cellular automaton itself.
That's computational reducibility. It's fascinating, but and that's a really powerful idea. I think that's both depressing and humbling and so on, that we in the cellular automata are the same. But the question we're talking about, the fundamental laws of physics, is kind of the reverse question. You're not predicting what's going to happen. You have to run the universe for that. But saying, can I understand what rules likely generated me?
I understand. But the problem is, to know whether you're right, you have to have some computational reducibility, because we are embedded in the universe. If the only way to know whether we get the universe is just to run the universe, we don't get to do that because it just ran for 14.6 billion years or whatever. And we can't rerun it, so to speak. So we have to hope that there are pockets of computational reducibility sufficient to be able to say, yes, I can recognize those are electrons there. Yeah. And I think that it's a feature of computational irreducibility. It's sort of a mathematical feature that there are always an infinite collection of pockets of reducibility. Yeah. The question of whether they land in the right place and whether we can sort of build a theory based on them is unclear. But to this point about, whether we as observers in the universe, built out of the same stuff as the universe, can figure out the universe, so to speak, that relies on these pockets of reducibility. Without the pockets of reducibility, it won't work, can't work. But I think this question about how observers operate, it's one of the features of science over the last 100 years particularly, has been that every time we get more realistic about observers, we learn a bit more about science. So, for example, relativity was all about observers don't get to say when, what's simultaneous with what. They have to just wait for the light signal to arrive to decide what's simultaneous. Or, for example, in thermodynamics, observers don't get to say the position of every single molecule in a gas. They can only see the kind of large-scale features, and that's why the second law of thermodynamics, law of entropy increase, and so on works. If you could see every individual molecule, you wouldn't conclude something about thermodynamics. You would conclude, oh, these molecules are just all doing these particular things. You wouldn't be able to see this aggregate fact. So I strongly expect that, and in fact, in the theories that I have, that one has to be more realistic about the computation and other aspects of observers in order to actually make a correspondence between what we experience. In fact, they have my little team and I have a little theory right now about how quantum mechanics may work, which is a very wonderfully bizarre idea about how the sort of thread of human consciousness relates to what we observe in the universe. But there's several steps to explain what that's about.
What do you make of the mess of the observer at the lower level of quantum mechanics? Sort of the textbook definition with quantum mechanics kind of says that there's two worlds. One is the world that actually is, and the other is that's observed. What do you make sense of that kind of observer?
I think actually the ideas we've recently had might actually give away into this. And that's, I don't know yet. I mean, I think it's a mess. I mean, the fact is one of the things that's interesting, and when people look at these models that I started talking about 30 years ago now, they say, oh, no, that can't possibly be right. What about quantum mechanics? Right? You say, okay, tell me what is the essence of quantum mechanics? What do you want me to be able to reproduce to know that I've got quantum mechanics, so to speak? Well, and that question comes up very operationally, actually, because we've been doing a bunch of stuff with quantum computing. And there are all these companies that say, we have a quantum computer. And we say, let's connect to your API and let's actually run it. And they're like, well, maybe you shouldn't do that yet. We're not quite ready yet. And one of the questions that I've been curious about is, if I have 5 minutes with a quantum computer, how can I tell if it's really a quantum computer or whether it's a simulator at the other end, right? And turns out it's really hard. It turns out there isn't. It's like a lot of these questions about sort of what is intelligence, what's life.
That's a Turing test for a quantum computer.
That's right. That's right. It's like, are you really a quantum computer? And I think
a simulation.
Yes, exactly. Is it just a simulation or is it really a quantum computer? Same issue all over again.
Yeah.
But that this whole issue about the sort of mathematical structure of quantum mechanics and the completely separate thing that is our experience, in which we think definite things happen, whereas quantum mechanics doesn't say definite things ever happen. Mm-hmm. Quantum mechanics is all about the amplitudes for different things to happen, but yet our thread of consciousness operates as if definite things are happening.
To linger on the point, you've kind of mentioned the structure that could underlie everything, and this idea that it could perhaps have something like a structure of a graph. Mm-hmm. Can you elaborate why your intuition is that there's a graph structure of nodes and edges and what it might represent?
Right. Okay. So the question is, what is, in a sense, the most structureless structure you can imagine? Right? So, and in fact, what I've recently realized in the last year or so, I have a new most structureless structure.
By the way, the question itself is a beautiful one and a powerful one in itself. So even without an answer, just the question is a really strong question.
Right.
But what's your new idea?
Well, it has to do with hypergraphs. Essentially, what is interesting about the sort of model I have now is it's a little bit like what happened with computation. Everything that I think of as, oh, well, maybe the model is this, I discover its equivalent. And that's quite encouraging. because it's like I could say, well, I'm going to look at trivalent graphs with 3 edges for each node and so on, or I could look at this special kind of graph, or I could look at this kind of algebraic structure. And turns out that the things I'm now looking at, everything that I've imagined that is a plausible type of structureless structure is equivalent to this. So what is it? Well, a typical way to think about it is, so you might have some collection of tuples, collection of let's say numbers. So you might have 1, 3, 5, 2, 3, 4, little just collections of numbers, triples of numbers, let's say, quadruples of numbers, pairs of numbers, whatever. And you have all these sort of floating little tuples. They're not in any particular order. And that sort of floating collection of tuples, and I told you this was abstract, represents the whole universe. The only thing that relates them is when a symbol is the same, it's the same, so to speak. So if you have 2 tuples and they contain the same symbol, let's say at the same position of the tuple, at the first element of the tuple, then that represents a relation. Okay, so let me try and peel this back.
Wow. Okay, so
I told you it's abstract, but this is
so the relationship is formed by some aspect of sameness.
Right, but so think about it in terms of a graph.
Yeah.
So a graph, a bunch of nodes. Let's say you number each node. Okay, then what is a graph? A graph is a set of pairs that say this node has an edge connecting it to this other node. So and a graph is just a collection of those pairs that say this node connects to this other node. So this is a generalization of that, in which instead of having pairs, you have arbitrary n tuples. That's it. That's the whole story. And now the question is, okay, so that might represent the state of the universe. How does the universe evolve? What does the universe do? And so the answer is that what I'm looking at is transformation rules on these hypergraphs. In other words, you say this whenever you see a piece of this hypergraph that looks like this, turn it into a piece of hypergraph that looks like this. Mm-hmm. So on a graph, it might be when you see the subgraph, when you see this thing with a bunch of edges hanging out in this particular way, then rewrite it as this other graph. Mm-hmm. Okay? And so that's the whole story. So the question is, so now you say, as I say, this is quite abstract. And one of the questions is, where do you do those updating? So you've got this giant graph.
What triggers the updating? Like, what's the ripple effect of it? Is it?
Yes.
And I suspect everything's discrete, even in time. So.
Okay. So the question is, where do you do the updates?
Yes.
And the answer is, the rule is you do them wherever they apply. And you do them, the order in which the updates is done is not defined. That is, that you can do them. So there may be many possible orderings for these updates. Now, the point is, imagine you're an observer in this universe. Mm-hmm. So, and you say, did something get updated? Well, you don't in any sense know until you yourself have been updated.
Right.
So, in fact, all that you can be sensitive to is essentially the causal network of how an event over there affects an event that's in you.
That doesn't even feel like observation. That's something else. You're just part of the whole thing.
Yes, you're part of it. But even to have, so the end result of that is all you're sensitive to is this causal network of what event affects what other event. I'm not making a big statement about sort of the structure of the observer. I'm simply saying, I'm simply making the argument that what happens, the microscopic order of these rewrites, is not something that any observer, any conceivable observer in this universe can be affected by. Because the only thing the observer can be affected by is this causal network of how the events in the observer are affected by other events that happen in the universe. So the only thing you have to look at is the causal network. You don't really have to look at this microscopic rewriting that's happening. So these rewrites are happening wherever they happen wherever they feel like.
Causal network. Is there, you said that there's not really, so the idea would be an undefined like what gets updated, the sequence of things is undefined. It's
Yes.
that's what you mean by the causal network. But then the
causal network is given that an update has happened. That's an event. Then the question is that event causally related to? Does that event, if that event didn't happen, then some future event couldn't happen yet.
Gotcha.
And so you build up this network of what affects what. Yeah. Okay. And so what that does, so when you build up that network, that's kind of the observable aspect of the universe in some sense.
Gotcha.
And so then you can ask questions about, how robust is that observable network of what's happening in the universe? Okay, so here's where it starts getting kind of interesting. So for certain kinds of microscopic rewriting rules, the order of rewrites does not matter to the causal network. And so this is, mathematical logic, moment. This is equivalent to the Church-Rosser property or the confluence property of rewrite rules. And it's the same reason that if you're simplifying an algebraic expression, for example, you can say, let me expand those terms out. Let me factor those pieces. Doesn't matter what order you do that in. You'll always get the same answer. And it's the same fundamental phenomenon that causes, for certain kinds of microscopic rewrite rules, that causes the causal network to be independent of the microscopic order of rewritings.
Why is that property important?
Because it implies special relativity. I mean, the reason it's important is that property, special relativity says you can look at you can look at different reference frames. You can be looking at your notion of what's space and what's time can be different, depending on whether you're traveling at a certain speed, depending on whether you're doing this, that, and the other. But nevertheless, the laws of physics are the same. That's what the principle of special relativity says, is the laws of physics are the same, independent of your reference frame. Well, turns out this sort of change of the microscopic rewriting order is essentially equivalent to a change of reference frame, or at least there's a sub-part of how that works that's equivalent to change of reference frame. So, somewhat surprisingly, and sort of for the first time in forever, it's possible for an underlying microscopic theory to imply special relativity, to be able to derive it. It's not something you put in as it's something where this other property, causal invariance, which is also the property that implies that there's a single thread of time in the universe. It might not be the case. That's what would lead to the possibility of an observer thinking that definite stuff happens. Otherwise, you've got all these possible rewriting orders, and who's to say which one occurred? But with this causal invariance property, there's a notion of a definite thread of time.
It sounds like that kind of idea of time, even space, would be emergent from the system.
Oh yeah, no, I mean,
so it's not a fundamental part of the system.
No, the fundamental level, all you've got is a bunch of nodes connected by hyperedges or whatever.
So there's no time, there's no space.
That's right. But the thing is that it's just like imagine you're just dealing with a graph, and imagine you have something like a honeycomb graph where you have a bunch of hexagons. That graph at a microscopic level, it's just a bunch of nodes connected to other nodes. But at a macroscopic level, you say that looks like a honeycomb, lattice. It looks like a two-dimensional, manifold of some kind. It looks like a two-dimensional thing. If you connect it differently, if you just connect all the nodes one to another in kind of a sort of linked list type structure, then you'd say, well, that looks like a one-dimensional space. But at the microscopic level, all these are just networks with nodes. The macroscopic level, they look like something that's like one of our sort of familiar kinds of space. And it's the same thing with these hypergraphs. Now, if you ask me, have I found one that gives me three-dimensional space? The answer is not yet. So we don't know. This is one of these things. We're kind of betting against nature, so to speak. Right. And I have no way to know. I mean, so there are many other properties of this kind of system that are very beautiful, actually, and very suggestive. And it will be very elegant if this turns out to be right, because it's very clean. I mean, you start with nothing, and everything gets built up. Everything about space, everything about time, everything about matter. It's all just emergent from the properties of this extremely low-level system. And that will be pretty cool if that's the way our universe works. Now, on the other hand, the thing that I find very confusing is, let's say we succeed. Let's say we can say, this particular sort of hypergraph rewriting rule gives the universe. Just run that hypergraph rewriting rule for enough times and you'll get everything. You'll get this conversation we're having. You'll get everything. It's that if we get to that point and we look at what is this thing, what is this rule that we just have that is giving us that whole universe, how do we think about that thing? Let's say, turns out the minimal version of this, and this is kind of cool thing for a language designer like me, the minimal version of this model is actually a single line of Wolfram language code. So that's, which I wasn't sure was going to happen that way, but it's kind of, no, we don't know what, that's just the framework. To know the actual particular hypergraph, it might be a longer, the specification of the rules might be slightly longer.
How does that help you accept marveling in the beauty and the elegance of the simplicity that creates the universe? Does that help us predict anything? Not really, because of the irreducibility.
That's correct. But so the thing that is really strange to me, and I haven't wrapped my brain around this yet, is, one keeps on realizing that we're not special in the sense that, we don't live at the center of the universe, we don't blah, blah, blah. And yet, if we produce a rule for the universe and it's quite simple and we can write it down in a couple of lines or something, that feels very special. How do we come to get a simple universe when many of the available universes, so to speak, are incredibly complicated, might be, a quintillion characters long? Why did we get one of the ones that's simple? And so I haven't wrapped my brain around that issue yet.
Us humans don't want to believe that kind of thing will achieve conceptual understanding, as you were saying. Like, you'll figure out physics, but maybe it will. Maybe.
Probably will. Well, it's worse than that. It'll understand physics in ways that we can't understand. I liked your Stephen Wolfram talk where he said, there's 3 generations of physics. There was physics by reasoning. Well, big things should fall faster than small things, right? That's reasoning. Yeah. And then there's physics by equations. Like, but the number of programs in the world that are solved with a single equation is relatively low. Almost all programs have, more than one line of code, maybe 100 million lines of code. Yeah. So he said, now we're going to physics by equation, which is his project, which is cool. Mm-hmm. I might point out there was two generations of physics before reasoning, habit. Like all animals, know things fall and, birds fly and, predators know how to, solve a differential equation to cut off a accelerating, curving animal path.
Yeah.
And then there was, the gods did it. Right. So,
yeah.
Right. So there's 5 generations. Now, Software 2.0 says programming things is not the last step. Data. So there's going to be a physics past Wolfram's
that's not explainable to us humans.
And actually, there's no reason that I can see that's the limit. Like, there's something beyond that. I mean, they're usually when you have this hierarchy, it's not like, well, if you have this step and this step and this step, and they're all qualitatively different and conceptually different, it's not obvious why 6 is the right number of hierarchy steps and not 7 or 8 or.
Well, then it's probably impossible for us to comprehend something that's beyond the thing that's not explainable.
Yeah, but the thing that understands the thing that's not explainable to us will conceive the next one, and I'm not sure why there's a limit to it. Looks like your brain hurts. It's a sad story.
Before we go into that mysterious, beautiful world, let's take a small step back. And you also, in your book, have this kind of, through the space of puzzles, through the space of ideas, have a brief history of physics, of physical ideas. Now, we talked about Newtonian mechanics, leading all through different Lagrangian, Hamiltonian mechanics. Can you describe some of the key ideas in the history of physics, maybe lingering on each, from electromagnetism to relativity to quantum mechanics and to today, as we'll talk about with quantum gravity and string theory?
Sure. So I mentioned the classical mechanics and the Euler-Lagrange formulation. One of the next important milestones for physics were the discoveries of laws of electricity and magnetism. So Maxwell put the discoveries all together in the context of what we call the Maxwell's equations. And he noticed that when he put these discoveries that Faraday's and others had made about electric and magnetic phenomena, in terms of mathematical equations, it didn't quite work. There was a mathematical inconsistency. Now, one could have two attitudes. One could say, okay, who cares about math? I'm doing nature, electric force, magnetic force, math, I don't care about. But it bothered him. It was inconsistent. The equations he were writing, the two equations he had written down, did not agree with each other. And this bothered him. But he figured out, if you jiggle this equation by adding one little term there, it works. At least it's consistent. What is the motivation for that term? He said, I don't know. Have we seen it in experiments? No. Why did you add it? Well, because of mathematical consistency. So he said, okay, math forced him to do this term. He added this term, which we now today call the Maxwell term. And once he added that term, his equations were nice, differential equations, mathematically consistent, beautiful. But he also found a new physical phenomena. He found that because of that term, he could now get electric and magnetic waves moving through space at a speed that he could calculate. So he calculated the speed of the wave, and lo and behold, he found it's the same as the speed of light, which puzzled him because he didn't think light had anything to do with electricity and magnetism. But then he was courageous enough to say, well, maybe light is nothing but these electric and magnetic fields moving around. And he wasn't alive to see the verification of that prediction, and indeed was true. So this mathematical inconsistency, which we could say, this mathematical beauty drove him to this physical, very important connection between light and electromagnetic phenomena, which was later confirmed. So then physics progressed.
What is the difference between mathematics and physics?
Well, that's a difficult question because in many ways, math and physics are unified in many ways. So to distinguish them is not an easy task. I would say that perhaps the goals of math and physics are different. Math does not care to describe reality. Physics does. That's the major difference. But a lot of the thoughts, processes, and so on, which goes to understanding the nature and reality, are the same things that mathematicians do. So in many ways, they are similar. Mathematicians care about deductive reasoning, and physicists or physics in general, we care less about that. We care more about interconnection of ideas, about how ideas support each other, or if there's a puzzle discord between ideas. That's more interesting for us. And part of the reason is that we have learned in physics that the ideas are not sequential. And if we think that there's one idea which is more important, and we start with there and go to the next idea and next one and deduce things from that like mathematicians do, we have learned that the third or fourth thing we deduce from that principle turns out later on to be the actual principle. And from a different perspective, starting from there leads to new ideas which the original one didn't lead to. And that's the beginning of a new revolution in science. So this kind of thing we have seen again and again in the history of science. We have learned to not like deductive reasoning because that gives us a bad starting point to think that we actually have the original thought process should be viewed as the primary thought, and all these are deductions, like the way mathematicians sometimes do. So in physics, we have learned to be skeptical of that way of thinking. We have to be a bit open to the possibility that what we thought is a deduction of a hypothesis, actually the reason that's true is the opposite. And so we reverse the order. And so this switching back and forth between ideas makes us more fluid about a deductive fashion. Of course, it sometimes gives a wrong impression, like physicists don't care about rigor. They just say random things. They are willing to say things that are not backed by, the logical reasoning. That's not true at all. So despite this fluidity in seeing which one is a primary thought, we are very careful about trying to understand what we have really understood in terms of relationship between ideas. So that's an important ingredient. And in fact, solid math being behind physics is, I think, one of the attractive features of a physical law. So we look for beautiful math.
So for example, I'll give you one example, this AI Feynman project that we just published, right? So we took the 100 most famous or complicated equations from one of my favorite physics textbooks. In fact, the one that got me into physics in the first place, the Feynman lectures on physics. And So you have a formula, maybe it has, what goes into the formula is 6 different variables, and then what comes out is 1. So then you can make like a giant Excel spreadsheet with 7 columns. You put in just random numbers for the 6 columns for those 6 input variables, and then you calculate with a formula the 7th column, the output. So maybe it's like the force equals, in the last column, some function of the other. And now the task is, okay, if I don't tell you what the formula was, can you figure that out from looking at my spreadsheet I gave you?
Yes.
This problem is called symbolic regression. If I tell you that the formula is what we call a linear formula, so it's just that the output is some sum of all the things inputted times some constants, that's the famous easy problem we can solve. We do it all the time in science and engineering. But the general one, if it's more complicated functions with logarithms or cosines or other math, it's a very, very hard one and probably impossible to do fast in general, just because the number of formulas with n symbols just grows exponentially, just like the number of passwords you can make grow dramatically with length. But we had this idea that if you first have a neural network that can actually approximate the formula, you just trained it, even if you don't understand how it works, that can be the first step towards actually understanding how it works. So that's what we do first. And then we study that neural network now and put in all sorts of other data that wasn't in the original training data and use that to discover simplifying properties of the formula. And that lets us break it apart often into many simpler pieces in a kind of divide and conquer approach. So we were able to solve all of those 100 formulas, discover them automatically, plus a whole bunch of other ones. And it's actually kind of humbling to see that this code, which anyone who wants now who's listening to this can type pip install AI Feynman on the computer and run it. It can actually do what Johannes Kepler spent 4 years doing when he stared at Mars data until he's like, finally, eureka, this is an ellipse. This will do it automatically for you in 1 hour, right? Or Max Planck, he was looking at how much radiation comes out from at different wavelengths from a hot object and discovered the famous black body formula. This discovers it automatically. I'm actually excited about seeing if we can discover not just old formulas again, but new formulas that no one has seen before.
I do like this process of using kind of a neural network to find some basic insights and then dissecting the neural network to then gain the final. So that's in that way you've forcing the explainability issue. Really trying to analyze a neural network for the things it knows in order to come up with the final, beautiful, simple theory underlying the initial system that you were looking at.
I love that. And the reason I'm so optimistic that it can be generalized to so much more is because that's exactly what we do as human scientists. Think of Galileo, whom we mentioned, right? I bet when he was a little kid, if his dad threw him an apple, he would catch it. Why? Because he had a neural network in his brain that he had trained to predict the parabolic orbit of apples that are thrown under gravity. If you throw a tennis ball to a dog, it also has this same ability of deep learning to figure out how the ball is going to move and catch it. But Galileo went one step further when he got older. He went back and was like, wait a minute. I can write down a formula for this. Y equals x squared, a parabola. And he helped revolutionize physics as we know it, right?
So there was a basic neural network in there from childhood that captured like the experiences of observing different kinds of trajectories. And then he was able to go back in with another extra little neural network and analyze all those experiences and be like, wait a minute, there's a deeper rule here.
Exactly. He was able to distill out in symbolic form what that complicated black box neural network was doing, right? Not only did the formula he got ultimately become more accurate, and similarly, this is how Newton got Newton's laws, which is why Elon can send rockets to the space station now, right? So it's not only more accurate, but it's also simpler, much simpler, and it's so simple that we can actually describe it to our friends and each other, right? We've talked about it just in the context of physics now, but hey, isn't this what we're doing when we're talking to each other also? We go around with our neural networks, just like dogs and cats and chipmunks and blue jays, and we experience things in the world. But then we humans do this additional step on top of that, where we then distill out certain high-level knowledge that we've extracted from this in a way that we can communicate it to each other in a symbolic form, in English in this case, right? So if we can do it, and we believe that we are information processing entities, then we should be able to make machine learning that does it also.
Well, do you think the entire thing could be learning? Because this dissection process, like for AI Feynman, the secondary stage feels like something like reasoning, and the initial step feels like more like the more basic kind of differentiable learning. Do you think the whole thing could be differentiable learning? Do you think the whole thing could be basically neural networks on top of each other? It's like turtles all the way down. Could it be neural networks all the way down?
I mean, that's a really interesting question. We know that in your case, it is neural networks all the way down, because that's
Allegedly.
all you have in your skull. There's a bunch of neurons doing their thing, right?
Yeah.
But if you ask the question more generally, what algorithms are being used in your brain, right? I think it's super interesting to compare. I think we've gone a little bit backwards historically, because we humans first discovered good old-fashioned AI, the logic-based AI that we often call Goff for good old-fashioned AI. And then more recently, we did machine learning because it required bigger computers. So we had to discover it later. So we think of machine learning with neural networks as the modern thing and the logic-based AI as the old-fashioned thing. But if you look at evolution on Earth, right, it's actually been the other way around. I would say that, for example, an eagle has a better vision system than I have using, and dogs are just as good at casting tennis balls as I am. All this stuff, which is done by training a neural network and not interpreting it in words, it's something so many of our animal friends can do, at least as well as us, right? Mm-hmm. What is it that we humans can do that the chipmunks and the eagles cannot? It's more to do with this logic-based stuff, right? Where we can extract out information in symbols, in language, and now even with equations if you're a scientist, right? Mm-hmm. So basically what happened was, first we built these computers that could multiply numbers real fast and manipulate symbols, and we felt they were pretty dumb. And then we made neural networks that can see as well as a cat can and do a lot of this inscrutable black box neural networks. What we humans can do also is put the two together in a useful way.
Yes.
So artificial
in our own brain.
Yes, in our own brain. So if we ever want to get artificial general intelligence that can do all jobs as well as humans can, right? Then that's what's going to be required, to be able to combine the neural networks with symbolic. Combine the old AI with the new AI in a good way. We do it in our brains.
Incredible. So this self-play of quarks, taking back to the beginning of our conversation a little bit, there's so many exciting possibilities about artificial intelligence understanding the basic laws of physics. Do you think AI will help us unlock? There's been quite a bit of excitement throughout the history of physics of coming up with more and more general, simple laws that explain the nature of our reality. And then the ultimate of that would be a theory of everything that combines everything together. Do you think it's possible that, we humans, but perhaps AI systems will figure out a theory of physics that unifies all the laws of physics?
Yeah, I think it's absolutely possible. I think it's very clear that we're going to see a great boost to science. We're already seeing a boost actually from machine learning helping science. AlphaFold was an example, the decades-old protein folding problem solved, and gradually, unless we go extinct by doing something dumb like we discussed, I think it's very likely that our understanding of physics will become so good that our technology will no longer be limited by human intelligence, but instead be limited by the laws of physics. So our tech today is limited by what we've been able to invent, right? I think as AI progresses, it'll just be limited by the speed of light and other physical limits, which will mean it's going to be just dramatically beyond, where we are now.
Do you think it's a fundamentally mathematical pursuit of trying to understand like the laws of that govern our universe from a mathematical perspective? It's almost like if it's AI, it's exploring the space of like theorems and those kinds of things. Or is there some other is there some other more computational ideas, more sort of empirical ideas?
They're both, I would say. It's really interesting to look out at the landscape of everything we call science today. So here you come now with this big new hammer. It says machine learning on it, and ask, where are there some nails that you can help with here that you can hammer? Ultimately, if machine learning gets to the point that it can do everything better than us, it will be able to help across the whole space of science. But maybe we can anchor it by starting a little bit right now near term and see how we kind of move forward. So like right now, first of all, you have a lot of big data science, right, where, for example, with telescopes, we are able to collect way more data every hour than a grad student can just pour over like in the old times, right? Mm-hmm. And machine learning is already being used very effectively, even at MIT, right, to find planets around other stars, to detect exciting new signatures of new particle physics in the sky, and to detect the ripples in the fabric of space-time that we call gravitational waves caused by enormous black holes crashing into each other halfway across our observable universe. Machine learning is running and ticking right now, doing all these things, and it's really helping all these experimental fields. There is a separate front of physics, computational physics, which is getting an enormous boost also. So we had to do all our computations by hand, right? People would have these giant books with tables of logarithms, and oh my God, it pains me to even think how long time it would have taken to do simple stuff. Then we started to get little calculators and computers that could do some basic math for us. Now, what we're starting to see is kind of a shift from Goff computational physics to neural network computational physics. What I mean by that is most computational physics would be done by humans programming in the intelligence of how to do the computation into the computer. Just as when Garry Kasparov got his posterior kicked by IBM's Deep Blue in chess, humans had programmed in exactly how to play chess. Yes. Intelligence came from the humans. It wasn't learned, right? mu0 can be not only Kasparov in chess, but also Stockfish, which is the best sort of Goff chess program, by learning. And we're seeing more of that now, that shift beginning to happen in physics. So let me give you an example. So lattice QCD is an area of physics whose goal is basically to take the periodic table and just compute the whole thing from first principles. Mm-hmm. This is not the search for a theory of everything. We already know the theory that's supposed to produce as output the periodic table, which atoms are stable, how heavy they are, all that good stuff. Their spectral lines. It's a theory, lattice QCD. You can put it on your T-shirt. Our colleague Frank Wilczek got the Nobel Prize for working on it. But the math is just too hard for us to solve. We have not been able to start with these equations and solve them to the extent that we can predict, and then there's carbon, and this is what the spectrum of the carbon atom looks like. But awesome people are building these supercomputer simulations where you just put in these equations and you make a big cubic lattice of space. Or actually, it's a very small lattice because you're going at the subatomic scale, down to the subatomic scale, and you try to solve this. But it's just so computationally expensive that we still haven't been able to calculate things as accurately as we measure them in many cases. And now machine learning is really revolutionizing this. So my colleague Fiona Shanahan at MIT, for example, she's been using this really cool machine learning technique called normalizing flows, where she's realized she can actually speed up the calculation dramatically by having the AI learn how to do things faster. Another area like this where where we suck up an enormous amount of supercomputer time to do physics is black hole collisions. So now that we've done the sexy stuff of detecting a bunch of this with LIGO and other experiments, we want to be able to know what we're seeing. And so it's a very simple conceptual problem. It's the two-body problem. Newton solved it for classical gravity hundreds of years ago, but the two-body problem is still not fully solved
for black holes.
And Einstein's gravity, because they won't just orbit each other forever anymore. Two things. They give off gravitational waves, and eventually they crash into each other. And the game, what you want to do is you want to figure out, okay, what kind of wave comes out as a function of the masses of the two black holes, as a function of how they're spinning relative to each other, etc. And that is so hard. It can take months of supercomputer time on massive numbers of cores to do it, Wouldn't it be great if you can use machine learning to greatly speed that up, right? Now you can use the expensive old Goff calculation as the truth, and then see if machine learning can figure out a smarter, faster way of getting the right answer. Yet another area like of computational physics. These are probably the big three that suck up the most computer time: lattice QCD, black hole collisions, and cosmological simulations, where you take not a subatomic thing and try to figure out the mass of the proton, but you take something with it's enormous and try to look at how all the galaxies get formed in there.
Oh, wow. Yeah.
There again, there are a lot of very cool ideas right now about how you can use machine learning to do this sort of stuff better. The difference between this and the big data is you kind of make the data yourself, right? So, and then finally, we're looking over the physics landscape and seeing what can we hammer with machine learning, right? So we talked about experimental data, big data, discovering cool stuff that we humans then look more closely at. Then we talked about taking the expensive computations we're doing now and figuring out how to do them much faster and better with AI. And finally, let's go really theoretical. So things like discovering equations, having deep fundamental insights. This is something closest to what I've been doing in my group. We talked earlier about the whole AI Feynman project, where if you just have some data, how do you automatically discover equations that seem to describe this well, that you can then go back as a human and work with and test and explore? And you asked a really good question also about if this is sort of a search problem in some sense. That's very deep, actually, what you said, because it is. Suppose I ask you to prove some mathematical theorem. What is a proof in math? It's just a long string of steps, logical steps that you can write out with symbols. And once you find it, it's very easy to write a program to check whether it's a valid proof or not. So why is it so hard to prove it then? Well, because there are ridiculously many possible candidate proofs you could write down, right? If the proof contains 10,000 symbols, even if there were only 10 options for what each symbol could be, that's 10 to the power 1,000 possible proofs, which is way more than there are atoms in our universe, right? So you could say it's trivial to prove these things. You just write a computer, generate all strings, and then check, is this a valid proof? No. Is this a valid proof? No. And then you just keep doing this forever. But there are but it is fundamentally a search problem. You just want to search the space of all strings of symbols to find one that is the proof, right? And there's a whole area of machine learning called search. How do you search through some giant space to find the needle in the haystack? It's easier in cases where there's a clear measure of good, like you're not just right or wrong, but this is better and this is worse. So you can maybe get some hints as to which direction to go in. That's why we talked about neural networks work so well.
So people might not know this, but you were actually episode number 1 of this podcast just a couple of years ago, and now we're back. And it so happens that a lot of exciting things happened in both physics and artificial intelligence, both fields that you're super passionate about. Can we try to catch up to some of the exciting things happening in artificial intelligence, especially in the context of the way it's cracking open the different problems of the sciences?
Yeah, I'd love to, especially now as we start 2021 here. It's a really fun time to think about what were the biggest breakthroughs in AI, not the ones necessarily that media wrote about, but that really matter. And what does that mean for our ability to do better science? What does it mean for our ability to help people around the world? And what does it mean for new problems that they could cause if we're not smart enough to avoid them? So, what do we learn basically from this?
Yes, absolutely. So one of the amazing things you're part of is the AI Institute for Artificial Intelligence and Fundamental Interactions. What's up with this institute? What are you working on? What are you thinking about?
The idea is something I'm very on fire with, which is basically AI meets physics. And, it's been almost 5 years now since I shifted my own MIT research from physics to machine learning. And in the beginning, I noticed a lot of my colleagues, even though they were polite about it, were like kind of, what is Max doing? What is this weird stuff?
He's lost his mind.
But then gradually, I, together with some colleagues, were able to persuade more and more of the other professors in our physics department to get interested in this. And now we got this amazing NSF center, so $20 million for the next 5 years, MIT and a bunch of neighboring universities here also. And I noticed now those colleagues who were looking at me funny have stopped asking what the point is of this, because it's becoming more clear. And I really believe that, of course, AI can help physics a lot to do better physics, but physics can also help AI a lot, both by building better hardware. My colleague Marin Soljacic, for example, is working on an optical chip for much faster machine learning, where the computation is done not by moving electrons around, but by moving photons around. Dramatically less energy use, faster, better. We can also help AI a lot, I think, by having a different set of tools and a different, maybe more audacious attitude. AI has, to a significant extent, been an engineering discipline where you're just trying to make things that work, and being more interested in maybe selling them than in figuring out exactly how they work and proving theorems about that they will always work, right? Yeah. Contrast that with physics. When Elon Musk sends a rocket to the International Space Station, they didn't just train with machine learning. Oh, let's fire it a little bit more to the left, a bit more to the right. Oh, that also missed. Let's try here. No, we figured out Newton's laws of gravitation and got other things and got a really deep fundamental understanding. And that's what gives us such confidence in rockets. And my vision is that in the future, all machine learning systems that actually have impact on people's lives will be understood at a really, really deep level, right? So we trust them not because some sales rep told us to, but because they've earned our trust. We can, in really safety critical things, even prove that they will always do, what we expect them to do. That's very much the physics mindset. So it's interesting if you look at big breakthroughs that have happened in machine learning this year, from dancing robots, is pretty fantastic. Not just because it's cool, but if you just think about not that many years ago, this YouTube video at this DARPA challenge where the MIT robot comes out of the car and face plants.
Yeah.
How far we've come in just a few years. Similarly, AlphaFold 2, crushing the protein folding problem. We can talk more about implications for medical research and stuff, but hey, that's huge progress. You can look at GPT-3 that can spout off English text, which sometimes really, really blows you away. Yeah. You can look at Google, at DeepMind's Mu0, which doesn't just kick our butt in Go and chess and shogi, but also in all these Atari games, and you don't even have to teach it the rules now. What all of those have in common is, besides being powerful, is we don't fully understand how they work. And that's fine if it's just some dancing robots, and the worst thing that can happen is they face plant, right? Or if they're playing Go, and the worst thing that can happen is that they make a bad move and lose the game, right? It's less fine if that's what's controlling your self-driving car or your nuclear power plant. And we've seen already that even though Hollywood had all these movies where they try to make us worry about the wrong things, like machines turning evil, the actual bad things that have happened with automation have not been machines turning evil. Mm-hmm. They've been caused by overtrust in things we didn't understand as well as we thought we did, right? Even very simple automated systems like what Boeing put into the 737 MAX, right?
Yes.
Killed a lot of people. Was it that little simple system was evil? Of course not. But we didn't understand it as well as we should have, right?
And we trusted without understanding.
Exactly.
That's the overtrust.
We didn't even understand that we didn't understand, right? The humility is really at the core of being a scientist. I think step one, if you want to be a scientist, is don't ever fool yourself into thinking you understand things when you actually don't.
Yes.
Right?
That's probably good advice for humans in general.
I think humility in general can do us good. But in science, it's like so spectacular. Like, why did we have the wrong theory of gravity ever from Aristotle onward and close until like Galileo's time? Like, why would we believe something so dumb as that if I throw this water bottle, it's going to go up with constant speed until it realizes that its natural motion is down?
It changes its mind.
You know, because people just kind of assumed Aristotle was right. He's an authority. We understand that. Why did we believe things like that the sun is going around the earth? Why did we believe that time flows at the same rate for everyone until Einstein? Same exact mistake over and over again. We just weren't humble enough to acknowledge that we actually didn't know for sure. We assumed we knew, so we didn't discover the truth because we assumed there was nothing there to be discovered, right? There was something to be discovered about the 737 MAX. And if you had been a bit more suspicious and tested it better, we would have found it. And it's the same thing with most harm that's been done by automation so far, I would say. So I don't know if did you hear of a company called Knight Capital?
No.
So good. That means you didn't invest in them earlier. They deployed this automated trading system.
Yes.
All nice and shiny. They didn't understand it as well as they thought. And it went about losing $10 million per minute.
Yeah.
For 44 minutes straight.
Oh, no.
Until someone presumably was like, oh no, shut this off. Was it evil? No, it was, again, misplaced trust, something they didn't fully understand, right? And there have been so many, even when people have been killed by robots, it's quite rare still, but in factory accidents, it's in every single case been not malice, just that the robot didn't understand that, hey, a human is different from an auto part or whatever. And so this is where I think there's so much opportunity for a physics approach, where you just aim for a higher level of understanding. And if you look at all these systems that we talked about, from reinforcement learning systems and dancing robots to all these neural networks that power GPT-3 and Go playing software and stuff, they're all basically black boxes. Much like, not so different from if you teach a human something, you have no idea how their brain works, right? Mm-hmm. Except the human brain, at least, has been error corrected during many, many centuries of evolution in a way that some of these systems have not, right? Yes. And my MIT research is entirely focused on demystifying this black box. Intelligible intelligence is my slogan.
That's a good line. Intelligible intelligence.
Yeah, it's that we shouldn't settle for something that seems intelligent, but it should be intelligible so that we actually trust it because we understand it, right? Like, again, Elon trusts his rockets because he understands Newton's laws and thrust and how everything works. And let me tell you why. Can I tell you why I'm optimistic about this?
Yes.
Please. I think we've made a bit of a mistake where some people still think that somehow we're never going to understand neural networks. And we're just going to have to learn to live with this. It's this very powerful black box. Basically, for those who haven't spent time building their own, it's super simple what happens inside. You send in a long list of numbers, and then you do a bunch of operations on them, multiply by matrices, et cetera, and some other numbers come out. That's the output of it. And then there are a bunch of knobs you can tune, and when you change them, it affects the computation, the input-output relation. And then you just give the computer some definition of good, and it keeps optimizing these knobs until it performs as good as possible. And often you go like, wow, that's really good. This robot can dance, or this machine is beating me at chess now. And in the end, you have something which, even though you can look inside it, you have very little idea of how it works. You can print out tables of all the millions of parameters in there. Is it crystal clear now how it's working? And no, of course not, right? So many of my colleagues seem willing to settle for that. And I'm like, no, that's like the halfway point. Some have even gone as far as sort of guessing that the mystery, the inscrutability of this is where some of the power comes from, and sort of some sort of mysticism. I think that's total nonsense. I think the real power of neural networks comes not from inscrutability, but from differentiability. And what I mean by that is simply that the output changes only smoothly if you tweak your knobs. And then you can use all these powerful methods we have for optimization in science. We can just tweak them a little bit and see, did that get better or worse? Right? That's the fundamental idea of machine learning, that the machine itself can keep optimizing until it gets better. Suppose you wrote this algorithm instead in Python or some other programming language. And then what the knobs did was they just changed random letters in your code. Now it would just epically fail, right? You change one thing, and instead of saying print, it says sint, syntax error. You don't even know, was that for the better or for the worse, right? This, to me, this is what I believe is the fundamental power of neural networks.
And just to clarify, the changing of the different letters in a program would not be a differentiable process.
It would make it an invalid program, typically, and then you wouldn't even know if you changed more letters, if it would make it work again, right?
So that's the magic of neural networks, the inscrutability.
The differentiability, that every setting of the parameters is a program, and you can tell is it better or worse, right? And so
you don't like the poetry of the mystery of neural networks as the source of its power?
I generally like poetry, but
not in this case.
It's so misleading, and above all, it shortchanges us. It makes us underestimate the good things we can accomplish. So what we've been doing in my group is basically step one, train the mysterious neural network to do something well. And then step two, do some additional AI techniques to see if we can now transform this black box into something equally intelligent that you can actually understand.
So as I mentioned, I talked to Sara Walker, and first of all, she says hi, spoke very highly of you. One of her concerns about physics and physicists and humans is that we may not fully understand the system that we're inside of. Meaning, like, there may be limits to the kind of physics we do in trying to understand the system of which we're part of. So, like, the observer is also the observed. In that sense, it seems like our tools of understanding the world, I mean, this is mostly centered around the questions of what is life, trying to understand the patterns that are characteristic of life and intelligence, all those kinds of things. We're not using the right tools because we're in the system. Is there something that resonates with you there? Almost like,
yes, we do have we have limitations, of course, in the amount of information we can process. On the other hand, we can get help from our silicon friends, and we can get help from all kinds of instruments that make up for our perceptual deficits. And we can use, at a conceptual level, we can use different kinds of concepts to address different kinds of questions. So I'm not sure exactly what problem she's talking about.
It's a problem akin to an organism living in a 2D plane trying to understand a three-dimensional world.
Well, we can do that. I mean, we live, in fact, for practical purposes, most of our experience is two-dimensional. It's hard to move vertically, and yet we've produced conceptually a three-dimensional symmetry. And in fact, four-dimensional space-time. So, by thinking in appropriate ways and using instruments and getting consistent accounts and rich accounts, we find out what concepts are necessary. And I don't see any end in sight of the process or any showstoppers, because let me give you an example. I mean, for instance, QCD, our theory of the strong interaction, has nice equations, which I helped to discover.
What's QCD?
Quantum chromodynamics. So it's our theory of the strong interaction, the interaction that is responsible for nuclear physics. So it's the interaction that governs how quarks and gluons interact with each other and make protons and neutrons and all the strong, the related particles and many things in physics. It's one of the four basic forces of nature as we presently understand it. So we have beautiful equations, which we can test in very special circumstances, using at high energies, at accelerators. So we're certain that these equations are correct. Prizes are given for it, and people try to knock it down, and they can't. And but the situations in which we can calculate the consequences of these equations are very limited. So, for instance, no one has been able to demonstrate that this theory, which is built on quarks and gluons, which you don't observe, actually produces protons and neutrons and the things you do observe. This is called the problem of confinement. So no one's been able to prove that analytically in a way that a human can understand. On the other hand, we can take these equations to a computer, to gigantic computers, and compute, and by God, you get the world from it. So these equations, in a way that we don't understand in terms of human concepts, we can't do the calculations, but our machines can do them. So with the help of what I like to call our silicon friends and their descendants in the future, we can understand in a different way that allows us to understand more. But I don't think we'll ever, no human is ever going to be able to solve those equations in the same way. But I think that's, when we find limitations to our natural abilities, we can try to find workarounds. And sometimes that's appropriate concepts, sometimes it's appropriate instruments, sometimes it's a combination of the two. But I think it's premature to get defeatist about it. I don't see any logical contradiction or paradox or limitation that will bring this process to a halt that way.
In your book, A Beautiful Question, you ask, does the world embody beautiful ideas? So the book is centered around this very interesting question. It's like Shakespeare. You can dig in and read into all the different interpretations of this question. But at the high level, what to you is the connection between beauty of the world and physics of the world?
In a sense, we now have a lot of insight into what the laws are, the form they take, that allow us to understand matter in great depth and control it, as we've discussed. And it's an extraordinary thing how mathematically ideal those equations turn out to be. In the early days of Greek philosophy, Plato had this model of atoms built out of the 5 perfectly symmetrical Platonic solids. So there was somehow the idea that mathematical symmetry should govern the world. And we've out-Platoed Plato by far in modern physics, because we have symmetries that are much more extensive, much more powerful, that turn out to be the ingredients out of which we construct our theory of the world. And it works. And so that's certainly beautiful. So the idea of symmetry, which is a driving inspiration in much of human art, especially decorative art, like the Alhambra or in wallpaper designs or things you see around you everywhere, also turns out to be the dominant theme in modern fundamental physics, symmetry and its manifestations, because the laws turn out to have these tremendous amounts of symmetry. You can change the symbols and move them around in different ways, and they still have the same consequences. So that's beautiful, and these things, these concepts that humans find appealing also turn out to be the concepts that govern how the world actually works. And I don't think that's an accident. I think humans were evolved to be able to interact with the world in ways that are advantageous and to learn from it. And so we are naturally evolved or designed to enjoy beauty and to symmetry, and the world has it, and that's why we resonate with it.
Well, it's interesting that the ideas of symmetry emerge at many levels of the hierarchy of the universe. So you're talking about particles, but it also is at the level of chemistry and biology, and the fact that our cognitive, sort of our perception system and whatever our cognition is, also finds it appealing, or somehow our sense of what is beautiful is grounded in this idea of symmetry or the breaking of symmetry. Yeah. Symmetry is at the core of our conception of beauty, whether it's the breaking or the non-breaking of the symmetry. Yes. It makes you wonder why. So I come from Russia, and the question of Dostoevsky, he has said that beauty will save the world. Maybe as a physicist, you can tell me, what do you think he meant by that?
I don't know if it saves the world, but it does turn out to be a tremendous source of insight into the world when we investigate kind of the most fundamental interactions, things that are hard to access because they occur at very short distances between very special kinds of particles whose properties are only revealed at high energies. We don't have much to go on from everyday life, but so we have when we guess and the experiments are difficult to do, so you can't really follow a very wholly empirical procedure to sort of in the Baconian style figure out the laws kind of step by step just by accumulating a lot of data. What we actually do is guess. And the guesses are kind of aesthetic, really. What would be a nice description that's consistent with what we know, and then you try it out and see if it works. And by gosh, it does in many profound cases. So there's that, but there's another source of symmetry which I didn't talk so much about in A Beautiful Question, but does relate to your comments, and I think very much relates to the source of symmetry that we find in biology and in our heads, in our brain, which is that it is discussed a bit in A Beautiful Question and also in Fundamentals, is that when you have symmetry is also a very important means of construction. So when you have, for instance, simple viruses that need to construct their coat, their protein coat, the coats often take the form of platonic solids. And the reason is that the viruses are really dumb and they only know how to do one thing. So they make a pentagon, then they make another pentagon, and they make another pentagon, and they all glue together in the same way. And that makes a very symmetrical object, sort of. So the rules of development, when you have simple rules and they work again and again, you get symmetrical patterns. That's kind of, in fact, it's a recipe also for generating fractals. You know, a kind of broccoli that has all this internal structure. And I wish I had a picture to show, but maybe people remember it from the supermarket, and you say, how did a vegetable get so intelligent to make such a beautiful object with all this fractal structure? And the secret is stupidity. You just do the same thing over and over again. And in our brains also, we start from single cells, and they reproduce, and they're each one does basically roughly the same thing. The program evolves in time, of course. Different modules get turned on and off. Different regions of the genetic code get turned on and off. But basically, a lot of the same things are going on, and they're simple things, and so you produce the same patterns over and over again, and that's a recipe for producing symmetry, because you're getting the same thing in many, many places. And if you look at, for instance, the beautiful drawings of Raman Ikahal, the great neuroanatomist, who drew the structure of different organs like the hippocampus, you see it's very regular and very intricate, and it's symmetry in that sense. It's because it's many repeated units that you can take from one place to the other and see that they look more or less the same.
But what you're describing, this kind of beauty that we're talking about now, is a very small sample in terms of space-time in a very big world, in a very short, brief moment in this long history. What is the most beautiful idea in physics?
The most beautiful idea in physics is that we can get a compact description of the world that's very precise and very full at the level of the operating system of the world. That's an extraordinary gift, and we get worried when we find discrepancies between our description of the world and what's actually observed at the level even of a part in a billion.
You actually have this quote from Einstein that the most incomprehensible thing about the universe is that it is comprehensible, something like that.
Yes, that's the most beautiful surprise that I think that really was to me the most profound result of the scientific revolution of the 17th century, with the shining example of Newtonian physics, that you could aspire to completeness, precision, and a concise description of the world, of the operating system. And it's gotten better and better over the years, and that's the continuing miracle. Now, there are a lot of beautiful sub-miracles, too. The form of the equations is governed by high degrees of symmetry, and they have very surprising kind of mind-expanding structure, especially in quantum mechanics. But if I had to say the single most beautiful revelation is that, in fact, the world is comprehensible.
Would you say that's a fact or a hope?
It's a fact. You can point to things like the rise of gross national products, per capita around the world as a result of the scientific revolution. You can see it all around you in recent developments with exponential production of wealth, control of nature at a very profound level, where we do things like sense tiny vibrations to tell that there are black holes colliding far away, or we test laws, as I alluded to, as a part in a billion, and do things in what appear on the surface to be entirely different conceptual universes. I mean, on the one hand, pencil and paper, or nowadays computers that calculate abstractions, and on the other hand, magnets and accelerators and detectors that look at the behavior of fundamental particles. And these different universes have to agree, or else we get very upset. And that's it's an amazing thing if you think about it. So, and it's telling us that we do understand a lot about nature at a very profound level. And there are still things we don't understand, of course, but as we get better and better answers and better ability to address difficult questions, we can ask more and more ambitious questions.
Well, I guess the hope part of that is because we are surrounded by mystery. So we've, one way to say it, if you look at the growth, GDP, over time that we figured out quite a lot, and we're able to improve the quality of life because of that. And we've figured out some fundamental things about this universe, but we still don't know how much mystery there is. And it's also possible that there's some things that are, in fact, incomprehensible to both our minds and the tools of science. Like the sad thing is we may not know it because, in fact, they are incomprehensible. And that's the open question: is how much of the universe is comprehensible? If we figured out the everything, what's inside the black hole and everything that happened at the moment of the Big Bang, does that still give us the key to understanding the human mind and the emergence of all the beautiful complexity we see around us? That's not like when I see these objects, like I don't know if you've seen them, like cellular automata. Mm-hmm. All these kinds of objects where from simple rules emerges complexity.
Yes.
It makes you wonder, maybe it's not reducible to simple, beautiful equations, the whole thing, only parts of it. That's the tension I was getting at with the hope.
Well, when we say the universe is comprehensible, we have to kind of draw careful distinctions about, or definitions about what we mean by that.
Both the universe and the comprehensible.
Exactly, right. So in certain areas of understanding reality, we've made extraordinary progress, I would say, in understanding fundamental physical processes and getting very precise equations that really work and allow us to do the profound sculpting of matter, to make computers and iPhones and everything else, and they really work, and they're extraordinary productions. That's all based on the laws of quantum mechanics, and they really work, and and they give us tremendous control of nature. On the other hand, as I say, as we get better answers, we can also ask more ambitious questions, and there are certainly things that have been observed, even in what would be usually called the realm of physics, that aren't understood. For instance, there seems to be another source of mass in the universe, the so-called dark matter, that we don't know what it is, and it's a very interesting question what it is. But also, as you were alluding to, it's one thing to know the basic equations. It's another thing to be able to solve them in important cases. So we run up against the limits of that in things like chemistry, where we'd like to be able to design molecules and predict their behavior from the equations. We think the equations could do that in principle, but in practice, it's very challenging to solve them in all but very simple cases. And then there's the other thing, which is that a lot of what we're interested in is historically conditioned. It's not a matter of the fundamental equations, but about what has evolved or come out of the early universe and formed into people and frogs and societies and things. And the laws of physics, the basic laws of physics, only take you so far. In that, it kind of provides a foundation, but doesn't really. You need entirely different concepts to deal with those kind of systems. And one thing I can say about that is that the laws themselves point out their limitations. That they kind of, they're laws for dynamical evolution. So they tell you what happens if you have a certain starting point, but they don't tell you what the starting point should be, at least. And the other thing that emerges from the equations themselves is the phenomena of chaos and sensitivity to initial conditions, which tells us that that there are intrinsic limitations on how well we can spell out the consequences of the laws if we try to apply them.
It's the old apple pie. If you want to, make an apple pie from scratch, you have to build the universe or something like that.
Well, you're much better off starting with apples than starting with quarks. Let's put it to half.
Can we talk about asymptotic freedom, this very idea that you won the Nobel Prize for?
Yeah.
So it describes a very weird effect to me. The weird in the following way. So the way I think of most forces or interactions, the closer you are, the stronger the effect, the stronger the force.
Yeah.
Right? With quarks, the closer they are, the less the strong interaction. Yeah. And in fact, they basically act like free particles when they're very close.
That's right. Yes.
But this requires a huge amount of energy. Like, can you describe me how does this even work? Given how weird it is.
A proper description must bring in quantum mechanics and relativity, and it's so a proper description and equations. So a proper description really is probably more than we have time for, and would require quite a bit of patience on your part. But
how does relativity come into play? Wait a minute.
Oh, relativity is important because when we talk about trying to think about short distances, we have to think about very large momenta, and very large momenta are connected to very large energy in relativity. And so the connection between how things behave at short distances and how things behave at high energy really is connected through relativity in sort of a slightly backhanded way. Quantum mechanics indicates that to analyze short distances, you need to bring in probes that carry a lot of momentum. This again is related to uncertainty because it's the fact that you have to bring in a lot of momentum that interferes with the possibility of determining position and momentum at the same time. If you want to determine position, you have to use instruments that bring in a lot of momentum. And because of that, those same instruments can't also measure momentum because they're disturbing the momentum. And then the momentum brings in energy, and so that there's also the effect that asymptotic freedom comes from the possibility of spontaneously making quarks and gluons for short amounts of time that fluctuate into existence and out of existence, and the fact that that can be done with a very little amount of energy, and uncertainty and energy translates into uncertainty in time. So if you do that for a short time, you can do that. It's all comes in a package, and you can. So I told you it would take a while to really explain, but the results can be understood. I mean, we can state the results pretty simply, I think. So in everyday life, we do encounter some forces that increase with distance and kind of turn off at short distances. That's the way rubber bands work, if you think about it. Or if you pull them hard, they resist, but they get flabby if the rubber band is not pulled. And so that can happen in the physical world. But what's really difficult is to see how that could be a fundamental force that's consistent with everything else we know. And that's what asymptotic freedom is. It says that there's a very particular kind of fundamental force that involves special particles called gluons with very special properties that enables that kind of behavior. So there were at the time we did our work, there were experimental indications that quarks and gluons did have this kind of property, but there were no equations that were capable of capturing it. And we found the equations and showed how they work and showed that they were basically unique. And this led to a complete theory of how the strong interaction works, which is the quantum chromodynamics we mentioned earlier. And so that's the phenomenon that quarks and gluons interact very, very weakly when they're close together. That's connected through relativity with the fact that they also interact very, very weakly at high energies. So at high energies, the simplicity of the fundamental interaction gets revealed. At the time we did our work, the clues were very subtle. But nowadays, at what are now high energy accelerators, it's all obvious. So we would have had somebody would have had a much easier time 20 years later looking at the data. You can sort of see the quarks and gluons. As I mentioned, they leave these short tracks that it would have been much, much easier. But from indirect clues, we were able to piece together enough to make that behavior a prediction rather than a post-diction, right?
So it becomes obvious at high energies.
It becomes very obvious. When we first did this work, it was frontiers of high energy physics, and at big international conferences, there would always be sessions on testing QCD and whether this proposed description of the strong interaction was in fact correct and so forth. And it was very exciting. They were big, but nowadays, the same kind of work, but much more precise, with calculations to more accuracy and experiments that are much more precise, and comparisons that are very precise. Now it's called calculating backgrounds because people take this for granted and want to see deviations from the theory, which would be the new discoveries.
Yeah, the cutting edge becomes the foundation. The foundation becomes boring. Yes. Yeah. Is there some, for basic explanation purposes, is there something to be said about strong interactions in the context of the strong nuclear force for the attraction between protons and neutrons versus the interaction between quarks within protons and so on?
Well, quarks and gluons have the same relation basically to nuclear physics as electrons and photons have to atomic and molecular physics. So atoms and photons are the dynamic entities that really come into play in chemistry and atomic physics. Of course, you have to have the atomic nuclei, but those are small and relatively inert, really the dynamical part. And, for most purposes of chemistry, you just say you have this tiny little nucleus, which QCD gives you. Don't worry about it. It's there. The real action is the electrons moving around and exchanging and things like that. But we wanted to understand the nucleus too. And so atoms are sort of quantum mechanical clouds of electrons held together by electrical forces, which is photons, and then there's radiation, which is also another aspect of photons.
That's where all the fun happens, is the electrons and the photons. And all that kind of
that's
stuff.
right. And the nucleus are kind of they're They give the positive charge and most of the mass of matter, but they don't, since they're so heavy, they don't move very much in chemistry, and I'm oversimplifying drastically.
They're not contributing much to the interaction in chemistry.
For most purposes in chemistry, you can just idealize them as concentrations of positive mass and charge that are you don't have to look inside, but people are curious what's inside. What really, and that was a big thing on the agenda of 20th century physics, starting with the 20th century and unfolding throughout, of trying to understand what forces held the atomic nucleus together, what it was, and so. Anyway, the story that emerges from QCD is that very similar to the way that, well, broadly similar to the way that clouds of electrons held together by electrical forces give you atoms and ultimately molecules. Protons and neutrons are like atoms made now out of quark clouds held together by gluons, which are like the photons that give the electric forces, but this is giving a different force, the strong force, and the residual forces between protons and neutrons that are left over from their basic binding are like the residual forces between atoms that give molecules, but in the case of protons and neutrons, it gives you atomic nuclei.
So again, for definitional purposes, QCD, quantum chromodynamics, is basically the physics of strong interaction.
Yeah, we understand. We now would I think most physicists would say it's the theory of quarks and gluons and how they interact. But okay. It's a very precise, and I think it's fair to say very beautiful theory based on mathematical symmetry of a high order. And another thing that's beautiful about it is that it's kind of in the same family as electrodynamics. The conceptual structure of the equations are very similar. They're based on having particles that respond to charge in a very symmetric way. In the case of electrodynamics, it's photons that respond to electric charge. In the case of quantum chromodynamics, there are three kinds of charge that we call colors, but they're nothing like colors. They really are like different kinds of charge.
But they rhyme with the same kind of it's similar kind of dynamics.
Similar kind of dynamics. I like to say that QCD is like QED on steroids. And instead of one photon, you have 8 gluons. Instead of one charge, you have 3 color charges. But there's a strong family resemblance between.
But the context in which QCD does its thing is it's at much higher energies. Like that's where it comes to life.
It's a stronger force, so that to access how it works and kind of pry things apart, you have to inject more energy.
And so that gives us, in some sense, a hint of how things were in the earlier universe.
Yeah, well, in that regard, asymptotic freedom is a tremendous blessing because it means things get simpler at high energy. And
the universe was born free.
Born free. That's very good, yes. The universe was born. So in atomic physics, I mean, a similar thing happens in the theory of stars. Stars are hot enough that the interactions between electrons and photons they're liberated. They don't form atoms anymore. They make a plasma, which in some ways is simpler to understand. You don't have complicated chemistry. And in the early universe, according to QCD, similarly, atomic nuclei dissolved into the constituent quarks and gluons, which are moving around very fast and interacting in relatively simple ways. And so this opened up the early universe to scientific calculation.
Maybe can we backtrack to the standard model and say what kind of particles there are, period, and maybe the history of kind of assembling that the standard model of physics, and then how that leads up to the hopes and dreams and the accomplishments of the Large Hadron Collider.
Yeah, sure. Okay. So all of 20th century physics in like 5 minutes. That's fine.
Please.
So, the story really begins properly end of the 19th century. The basic view of matter is that matter is made of atoms, and that atoms are indestructible, immutable little spheres like the things we were talking about that don't really exist. And there's, one atom for every chemical element. So there's an atom for hydrogen, for helium, for carbon, for iron, etc. And they're all different. Then in 1897, experiments done at the Cavendish Laboratory in Cambridge, which is where I'm based, showed that there are actually smaller particles inside the atom, which eventually became known as electrons. So these are these negatively charged things that go around the outside. A few years later, Ernest Rutherford, very famous nuclear physicist, one of the pioneers of nuclear physics, shows that the atom has a tiny nugget in the center, which we call the nucleus, which is a positively charged object. So then by like 1910, 11, we have this model of the atom that we learn in school, which is you've got a nucleus, electrons go around it. Fast forward, a few years, the nucleus, people start doing experiments with radioactivity where they use alpha particles that are spat out of radioactive elements as bullets, and they fire them at other atoms. And by banging things into each other, they see that they can knock bits out of the nucleus. So these things come out called protons, first of all, which are positively charged particles, about 2,000 times heavier than the electron. And then 10 years later, more or less, a neutral particle is discovered called the neutron. So those are the three basic building blocks of atoms. You have protons and neutrons in the nucleus that are stuck together by something called the strong force, the strong nuclear force. And you have electrons in orbit around that, held in by the electromagnetic force, which is one of the the forces of nature. That's sort of where we get to by like 1932, more or less. Then what happens is physics is nice and neat. In 1932, everything looks great. We've got three particles, we know what the atoms are made of, that's fine. But then cloud chamber experiments. So these are devices that can be used the first device is capable of imaging subatomic particles so you can see their tracks. And they're used to study cosmic rays, particles that come from outer space and bang into the atmosphere. And in these experiments, people start to see a whole load of new particles. So they discover, for one thing, antimatter, which is a sort of a mirror image of the particles. So we discover that there's also, as well as a negatively charged electron, there's something called a positron, which is a positively charged version of the electron. And there's an antiproton, which is negatively charged. And then a whole load of other weird particles start to get discovered. And no one really knows what they are. This is known as the zoo of particles.
Are these discoveries fundamentally first theoretical discoveries, or are they discoveries in experiment? So like, what's the process of discovery for these early sets of
It's a mixture. I mean, the early stuff around the atom is really experimentally driven. It's not based on some theory. It's exploration in the lab using equipment. So it's really people just figuring out, getting hands-on with the phenomena, figuring out what these things are. And the theory comes a bit later. That's not always the case. So in the discovery of the anti-electron, the positron, that was predicted from quantum mechanics and relativity by a very clever theoretical physicist called Paul Dirac, who was probably the second brightest, physicist of the 20th century, apart from Einstein, but isn't anywhere near as well known. So he predicted the existence of the anti-electron from basically a combination of the theories of quantum mechanics and relativity, and it was discovered about a year after he made the prediction.
What happens when an electron meets a positron?
They annihilate each other. So when you bring a particle and its antiparticle together, they react. Well, they don't react. They just wipe each other out, and their mass is turned into energy, usually in the form of photons. So you get light produced.
So when you have that kind of situation, why does the universe exist at all if there's matter and antimatter?
Oh God, now we're getting into the really big questions. So depends if you want to go there now.
Maybe let's go there later. Let's
because that is a very big question.
Yeah. Let's take it slow with the standard model. So there's matter and antimatter in the 30s. So what else?
So matter, antimatter, and then a load of new particles start turning up in these cosmic ray experiments, first of all. And they don't seem to be particles that make up atoms. There's something else. They all mostly interact with a strong nuclear force. So they're a bit like protons and neutrons. And by in the 1960s, in America particularly, but also in Europe and Russia, scientists start to build particle accelerators. So these are the forerunners of the LHC. So big ring-shaped machines that were, hundreds of meters long, which in those days was enormous. Most physics up until that point had been done in labs in universities, with small bits of kit. So this is a big change. And when these accelerators are built, they start to find they can produce even more of these particles. So I don't know the exact numbers, but by around 1960, there are of order 100 of these things that have been discovered. And physicists are kind of tearing their hair out because physics is all about simplification, and suddenly what was simple has become messy and complicated, and everyone sort of wants to understand what's going on.
As a quick kind of aside, and probably a really dumb question, but how is it possible to take something like a photon or electron and be able to control it enough, like to be able to do a controlled experiment where you collide it against something else?
Yeah,
that seems like an exceptionally difficult engineering challenge, because you mentioned vacuum too, so you basically want to remove every other distraction and really focus on this collision. How difficult of an engineering challenge is that, just to get a sense?
And it is very hard. I mean, in the early days, particularly when the first accelerators are being built in like 1932, Ernest Lawrence builds the first, what we call a cyclotron, which is like a little accelerator this big or so. There's another one.
Literally that big?
This tiny little thing, yeah. I mean, so most of the first accelerators were what we call fixed target experiments. So you had a ring, you accelerate particles around the ring, and then you fire them out the side into some target. So that makes the kind of the colliding bit is relatively straightforward, because you just fire it, whatever it is you want to fire it at. The hard bit is the steering the beams with the magnetic fields, getting strong enough electric fields to accelerate them, all that kind of stuff. The first colliders, where you have two beams colliding head on, that comes later, and I don't think it's done until maybe the 1980s. I'm not entirely sure, but it's a much harder problem.
That's crazy, because you have to like perfectly get them to hit each other. I mean, we're talking about, what scale? Like, what's the temporal thing is a giant mess, but the spatially, like the size is tiny.
Well, to give you a sense, so the LHC beams, the cross-sectional diameter is, I think, around a dozen or so microns. So, 10 millionths of a meter. So
and a beam, sorry, just to clarify, a beam contains how many? Is it the bunches that you mentioned? Is it multiple parts, or is it just one particle?
Oh, no. The bunches contain, say, 100 billion protons each. So a bunch is not really bunch shaped. They're actually quite long. They're like 30 centimeters long, but thinner than a human hair. So like very, very narrow, long sort of objects. So those are the things. So what happens in the LHC is you steer the beams so that they cross in the middle of the detector. So they basically have these swarms of protons that are flying through each other. And most of you have 100 billion coming one way, 100 billion another way, maybe 10 of them will hit each other.
Oh, okay. So that makes a lot more sense. So that's nice. So you're trying to use sort of, it's like probabilistically. You
can't make a single particle collide with a single other particle. So that's not an efficient way to do it. You'd be waiting a very long time to get anything. Yeah.
So you're basically right. So you're relying on probability to be that some fraction of them are going to collide.
Yeah.
And then which, because it's a swarm of the same kind of particle.
So it doesn't matter which ones hit each other exactly. I mean, that's not to say it's not hard. You've got one of the challenges to make the collisions work is you have to squash these beams to very, very, basically the narrower they are, the better, because the higher the chances of them colliding. If you think about two flocks of birds flying through each other, if the birds are all far apart in the flocks, there's not much chance that they'll collide. If they're all flying densely together, and they're much more likely to collide with each other. So that's the sort of problem. And it's tuning those magnetic fields, getting the magnetic fields powerful enough that you squash the beams and focus them so that you get enough collisions.
That's super cool. Do you know how much software is involved here? I mean, it's sort of, I come from the software world, and it's fascinating. This seems like the software is buggy and messy, and so like you almost don't want to rely on software too much. Like if you do, it has to be like low level, like Fortran style programming. Do you know how much software is in a Large Hadron Collider?
I mean, it depends at which level. A lot. I mean, the whole thing is obviously computer controlled. So I mean, I don't know a huge amount about how the software for the actual accelerator works. But I've been in the control center. So at CERN, there's this big control room, which is like a bit like a NASA mission control, with big banks of desks where the engineers sit and they monitor the LHC, because you obviously can't be in the tunnel when it's running, so everything's remote. I mean, one sort of anecdote about the sort of software side. In 2008, when the LHC first switched on, they had this big launch event, and then, big press conference party to inaugurate the machine. And about 10 days after that, they were doing some tests, and this dramatic event happened where a huge explosion basically took place in a tunnel that destroyed or badly damaged about half a kilometer of the machine. But the story is, the engineers who were in the control room that day, one guy told me this story about, basically all these screens they have in the control room started going red. So all these alarms, kind of in software going off, and then they assumed, there's something wrong with the software, because there's no way something this catastrophic could have happened.
Yeah.
But I mean, when I worked when I was a PhD student, one of my jobs was to help to maintain the software that's used to control the detector that we work on. And it's relatively robust, not sort of, you don't want it to be too fancy, you don't want it to sort of fall over too easily. The more clever stuff comes when you're talking about analyzing the data, and that's where the sort of,
Are we jumping around too much? Did we finish with the standard model?
We didn't, no.
We didn't. So have we even started talking about quarks?
We haven't talked about them yet. No, we got to the messy zoo of particles.
Let me let's go back there if it's okay.
Okay, that's fine.
Can you take us to the rest of the history of physics in the 20th century?
Okay, sure. Okay, so circa 1960, you have these 100 or so particles. It's a bit like the periodic table all over again. So you've got like having 100 elements. It's sort of a bit like that, and people start to try to impose some order. So Murray Gell-Mann, he's a theoretical physicist, American from New York. He realizes that there are these symmetries in these particles, that if you arrange them in certain ways, they relate to each other, and he uses these symmetry principles to predict the existence of particles that haven't been discovered, which are then discovered in accelerators. So this starts to suggest there's not just random collections of crap. There's actually some order to this underlying it. A little bit later, in 1960, again, it's around the 1960s, he proposes, along with another physicist called George Zweig, that these symmetries arise because, just like the patterns in the periodic table arise because atoms are made of electrons and protons, that these patterns are due to the fact that these particles are made of smaller things, and they are called quarks. So these are the particles. They're predicted from theory. For a long time, no one really believes they're real. A lot of people think that they're a kind of theoretical convenience that happen to fit the data, but there's no evidence. No one's ever seen a quark in any experiment. And lots of experiments are done to try to find quarks, to try to knock a quark out of so the idea, if protons and neutrons, say, are made of quarks, you should be able to knock a quark out and see the quark. That never happens. And we still have never actually managed to do that.
Wait, really?
No. So the way that it's done in the end is this machine that's built in California at the Stanford lab, Stanford Linear Accelerator, which is essentially a gigantic 3-kilometer long electron gun. It fires electrons almost the speed of light at protons. And when you do these experiments, what you find is at very high energy, the electrons bounce off small, hard objects inside the proton. So it's a bit like taking an X-ray of the proton. You're firing these very light, high energy particles, and they're pinging off little things inside the proton that are like ball bearings, if you like. Mm-hmm. So you actually, that way, they resolve that there are 3 things inside the proton, which are quarks, the quarks that Gell-Mann and Zweig had predicted. So that's really the evidence that convinces people that these things are real. The fact that we've never seen one in an experiment directly, they're always stuck inside other particles. And the reason for that is essentially to do with the strong force. The strong force is the force that holds quarks together. And it's so strong, it's impossible to actually liberate a quark. So if you try and pull a quark out of a proton, what actually ends up happening is that you kind of create this spring-like bond in the strong force. You imagine 2 quarks that are held together by a very powerful spring. You pull and pull and pull, more and more energy gets stored in that bond, like stretching a spring. And eventually the tension gets so great, the spring snaps, and the energy in that bond gets turned into 2 new quarks that go on the broken ends. So you started with 2 quarks, you end up with 4 quarks. So you never actually get to take a quark out. You just end up making loads more quarks in the process.
So how do we, again, forgive the dumb question, how do we know quarks are real then?
Well, from these experiments where we can scatter, you fire electrons into the protons. They can burrow into the proton and knock off, and they can bounce off these quarks. So you can see from the angles the electrons come out.
I see. You can infer.
You can infer that these things are there. the quark model can also be used. It has a lot of successes. You can use it to predict the existence of new particles that hadn't been seen. So, and it basically, there's lots of data basically showing from, when we fire protons at each other at the LHC, a lot of quarks get knocked all over the place. And every time they try and escape from, say, one of their protons, they make a whole jet of quarks that go flying off as bound up in other sorts of particles made of quarks. So all the sort of the theoretical predictions from the basic theory of the strong force and the quarks all agrees with what we are seeing in experiments. We've just never seen an actual quark on its own because unfortunately it's impossible to get them out on their own.
So quarks, these crazy smaller things that are hard to imagine are real. So what else? What else is part of the story here?
So the other thing that's going on at the time, around the 60s, is an attempt to understand the forces that make these particles interact with each other. So you have the electromagnetic force, which is the force that was sort of discovered to some extent in this room, or at least in this building. So the first, what we call quantum field theory of the electromagnetic force, is developed in the 1940s and 50s by Richard Feynman, amongst other people, Julian Schwinger, Tomonaga, who come up with the first, what we call a quantum field theory of the electromagnetic force. And this is where this description of, which I gave you at the beginning, that particles are ripples in fields. Well, in this theory, the photon, the particle of light, is described as a ripple in this quantum field called the electromagnetic field. And the attempt then is made to try, well, can we come up with a quantum field theory of the other forces, of the strong force and the weak, the third force, which we haven't discussed, which is the weak force, which is a nuclear force. We don't really experience it in our everyday lives, but it's responsible for radioactive decay. It's the force that allows, a radioactive atom to turn into a different element, for example.
And I don't know if we've explicitly mentioned, but so there's technically four forces.
Yes.
I guess three of them would be in the standard model, like the weak, the strong, and the electromagnetic, and then there's gravity.
And there's gravity, which we don't worry about that because it's too hard.
Well,
no, maybe bring that up at the end. But gravity so far we don't have a quantum theory of, and if you can solve that problem, you'll win a Nobel Prize.
Well, we're going to have to bring up the graviton at some point. I'm going to ask you, but let's leave that to the side for now. So those three, okay, Feynman, electromagnetic force, the quantum field, and where does the weak force come in?
So first of all, the strong force is a bit easier. So the strong force is a little bit like the electromagnetic force. It's a force that binds things together. So that's the force that holds quarks together inside the proton, for example. So a quantum field theory of that force is discovered I think it's in the 60s. And it predicts the existence of new force particles called gluons. So gluons are a bit like the photon. The photon is the particle of electromagnetism. Gluons are the particles of the strong force. And so there's just like there's an electromagnetic field, there's something called a gluon field, which is also all around us.
So some of these particles, I guess, are the force carriers or whatever. Yeah. They carry the...
Well, it depends how you want to think about it. Really the field, the strong force field, the gluon field is the thing that binds the quarks together. The gluons are the little ripples in that field. So that in the same way that the photon is a ripple in the electromagnetic field. But the thing that really does the binding is the field. You may have heard people talk about things like have you heard the phrase virtual particle? Sometimes if you hear people describing how forces are exchanged between particles, they quite often talk about the idea that, if you have an electron and another electron, say, and they're repelling each other through the electromagnetic force, you can think of that as if they're exchanging photons. So they're kind of firing photons backwards and forwards between each other, and that causes them to repel.
That photon is then a virtual particle.
Yes, that's what we call a virtual particle. In other words, it's not a real thing. It doesn't actually exist. So it's an artifact of the way theorists do calculations. So when they do calculations in quantum field theory, rather than there's no one's discovered a way of just treating the whole field. You have to break the field down into simpler things. So you can basically treat the field as if it's made up of lots of these virtual photons. But there's no experiment that you can do that can detect these particles being exchanged. What's really happening in reality is that the electromagnetic field is warped by the charge of the electron, and that causes the force. But the way we do calculations involves particles. So it's a bit confusing, but it's really a mathematical technique. It's not something that corresponds to reality.
I mean, that's part, I guess, of the Feynman diagrams.
Yes.
Is this these virtual particles? Okay.
That's right. Yeah.
Some of these have mass, some of them don't.
Mm-hmm.
Is that what does that even mean? Not to have mass, and maybe you can say which one of them have mass and which don't.
Okay. So
and why is mass important or relevant in this field view of the universe?
Well, there are actually only two particles in the standard model that don't have mass, which are the photon and the gluons. So they are massless particles. But the electron, the quarks, and there are a bunch of other particles I haven't discussed. There's something called a muon and a tau, which are basically heavy versions of the electron that are unstable. You can make them in accelerators, but they don't form atoms or anything. They don't exist for long enough. But all the matter particles, there are 12 of them, 6 quarks and 6 what we call leptons, which includes the electron and its 2 heavy versions and 3 neutrinos. All of them have mass. And so this is the critical bit, so the weak force, which is the third of these quantum forces, which is one of the hardest to understand, the force particles of that force have very large masses, and there are 3 of them. They're called the W plus, the W minus, and the Z boson, and they have masses of between 80 and 90 times that of the proton. So they're very heavy.
Wow,
they're very heavy things.
So they're the heaviest, I guess.
They're not the heaviest. The heaviest particle is the top quark, which has a mass of about 175-ish protons. So that's really massive. And we don't know why it's so massive. But coming back to the weak force, so the problem in the 60s and 70s was that the reason that the electromagnetic force is a force that we can experience in our everyday lives. So if we have a magnet and a piece of metal, you can hold it, a meter apart if it's powerful enough and you'll feel a force. Whereas the weak force only becomes apparent when you basically have 2 particles touching at the scale of a nucleus. So we get to very short distances before this force becomes manifest. Mm-hmm. We don't get weak forces going on in this room. We don't notice them. And the reason for that is that the field that transmits the weak force, the particle that's associated with that field has a very large mass, which means that the field dies off very quickly. Mm-hmm. So whereas an electric charge, if you were to look at the shape of the electromagnetic field, it would fall off with this, you have this thing called the inverse square law, which is the idea that the force halves every time you double the distance. It doesn't halve, it quarters every time you double the distance between, say, the 2 particles. Whereas the weak force you move a little bit away from the nucleus and it just disappears. The reason for that is because these fields, the particles that go with them, have a very large mass. But the problem that theorists faced in the 60s was that if you tried to introduce massive force fields, the theory gave you nonsensical answers. So you'd end up with infinite results for a lot of the calculations you tried to do. So it seemed that quantum field theory was incompatible with having massive particles. Not just the force particles, actually, but even the electron was a problem. So this is where the Higgs that we sort of alluded to comes in. And the solution was to say, okay, well, actually, all the particles in the standard model are mass. They have no mass. So the quarks, the electron, they don't have a mass. Neither do these weak particles. They don't have mass either. What happens is they actually acquire mass through another process. They get it from somewhere else. They don't actually have it intrinsically. Mm-hmm. So this idea that was introduced by, Peter Higgs is the most famous, but actually there are about 6 people that came up with the idea more or less at the same time, is that you introduce a new quantum field, which is another one of these invisible things that's everywhere. Mm-hmm. And it's through the interaction with this field that particles get mass. So you can think of, say, an electron in the Higgs field. The Higgs field kind of bunches around the electron. It's sort of drawn towards the electron. And that energy that's stored in that field around the electron is what we see as the mass of the electron. But if you could somehow turn off the Higgs field, then all the particles in nature would become massless and fly around at the speed of light. So this idea of the Higgs field allowed other theorists to come up with basically a unified theory of the electromagnetic force and the weak force. So once you bring in the Higgs field, you can combine 2 of the forces into one. So it turns out the electromagnetic force and the weak force are just two aspects of the same fundamental force. And at the LHC, we go to high enough energies that you see these two forces unifying effectively.
Let's start with probably one of the coolest things that human beings have ever created, the Large Hadron Collider, LHC. What is it? How does it work?
Okay, so it's essentially this gigantic 27-kilometer circumference particle accelerator. It's this big ring. It's buried about 100 meters underneath the surface in the countryside just outside Geneva in Switzerland. And really what it's for, ultimately, is to try to understand what are the basic building blocks of the universe. So you can think of it in a way as like a gigantic microscope, and the analogy is actually fairly precise. So
gigantic microscope.
Effectively, except it's a microscope that looks at the structure of the vacuum.
In order for this kind of thing to study particles, which are the microscopic entities, it has to be huge. So
yes.
It's a gigantic microscope. So what do you mean by studying vacuum?
Okay, so particle physics as a field is kind of badly named in a way, because particles are not the fundamental ingredients of the universe. They're not fundamental at all. So the things that we believe are the real building blocks of the universe are objects, invisible fluid-like objects called quantum fields. So these are fields like the magnetic field around a magnet that exist everywhere in space. They're always there. In fact, actually, it's funny that we're in the Royal Institution, because this is where the idea of the field was effectively invented by Michael Faraday doing experiments with magnets and coils of wire. So he noticed that, it's a very famous experiment that he did where he got a magnet and put it on top of it a piece of paper and then sprinkled iron filings. And he found the iron filings arranged themselves into these kind of loops which was actually mapping out the invisible influence of this magnetic field, which is a thing, we've all experienced. We've all held a magnet or two poles of the magnet and pushed them together and felt this force pushing back. So these are real physical objects. And the way we think of particles in modern physics is that they are essentially little vibrations, little ripples in these otherwise invisible fields that are everywhere. They fill the whole universe.
I apologize perhaps for the ridiculous question. Are you comfortable with the idea of the fundamental nature of our reality being fields? Because to me, particles, a bunch of different building blocks makes more sense sort of intellectually, sort of visually. Like it seems to, I seem to be able to visualize that kind of idea easier.
Yeah.
Are you comfortable psychologically with the idea that the basic building block is not a block, but a field?
I think it's quite a magical idea. I find it quite appealing, and it comes from a misunderstanding of what particles are. So, like when we do science at school and we draw a picture of an atom, you draw a nucleus with some protons and neutrons, these little spheres in the middle, and then you have some electrons that are like little flies flying around the atom. And that is a completely misleading picture of what an atom is like. It's nothing like that. The electron is not like a little planet orbiting the atom. It's this spread out, wibbly wobbly wave-like thing, and we've known that since the early 20th century, thanks to quantum mechanics. So when we carry on using this word particle, because sometimes when we do experiments, particles do behave like they're little marbles or little bullets. So in the LHC, when we collide particles together, you'll get like hundreds of particles all flying out through the detector, and they all take a trajectory, and you can see from the detector where they've gone, and they look like they're little bullets. So they behave that way, a lot of the time. But when you really study them carefully, you'll see that they are not little spheres. They are these ethereal disturbances in these underlying fields. So this is really how we think nature is. Which is surprising, but also I think kind of magic. So our bodies are basically made up of like little knots of energy in these invisible objects that are all around us.
And what is the story of the vacuum when it comes to LHC? So why did you mention the word vacuum?
Okay, so if we go back to like the physics we do know, so atoms are made of electrons, which were discovered 100 or so years ago, and then in the nucleus of the atom you have two other types of particles. There's something called an up quark and a down quark, and those three particles make up every atom in the universe. So we think of these as ripples in fields. So there is something called the electron field, And every electron in the universe is a ripple moving about in this electron field. So the electron field is all around us. We can't see it, but every electron in our body is a little ripple in this thing that's there all the time. And the quark field's the same. So there's an up quark field, and an up quark is a little ripple in the up quark field, and the down quark is a little ripple in something else called the down quark field. So these fields are always there. Now, there are potentially, we know about a certain number of fields in what we call the standard model of particle physics. And the most recent one we discovered was the Higgs field. And the way we discovered the Higgs field was to make a little ripple in it. So what the LHC did, it fired two protons into each other very, very hard with enough energy that you could create a disturbance in this Higgs field. And that's what shows up as what we call the Higgs boson. So this particle that everyone was going on about 8 or so years ago is proof, really. The particle in itself is, I mean, it's interesting, but the thing that's really interesting is the field, because it's the Higgs field that we believe is the reason that electrons and quarks have mass. And it's that invisible field that's always there that gives mass to the particles. The Higgs boson is just our way of checking it's there, basically.
And so the Large Hadron Collider, in order to get that ripple in the Higgs field, it requires a huge amount of energy, I suppose. And so that's why you need this huge, that's why size matters here. So maybe there's a million questions here, but let's backtrack. Why does size matter in the context of a particle collider? So why does bigger allow you for higher energy collisions?
Right. So the reason, well, it's kind of simple, really, which is that there are two types of particle accelerator that you can build. One is circular, which is like the LHC. The other is a great long line. Mm-hmm. So the advantage of a circular machine is that you can send particles round a ring and you can give them a kick every time they go round. So imagine there's actually a bit of the LHC that's about only 30 meters long, where you have a bunch of metal boxes which have oscillating 2 million volt electric fields inside them, which are timed so that when a proton goes through one of these boxes, the field it sees as it approaches is attractive, and then as it leaves the box, it flips and becomes repulsive, and the proton gets attracted and kicked out the other side, so it gets a bit faster. So you send it, and then you send it back round again. And
that's incredible. Like the timing of that, the synchronization. Wait, really?
Yeah.
I think there's going to be a multiplicative effect on the questions I have. Okay, let me just take that tangent for a second. How the orchestration of that, is that fundamentally a hardware problem or a software problem? Like how do you get that?
I mean, so I should first of all say I'm not an engineer. So the guys, I did not build the LHC. So there are people much, much better at this stuff than I.
For sure, but maybe, but from your sort of intuition, from the echoes of what you understand, what you heard of how it's designed, what's your sense? What's the engineering aspects of it?
So the acceleration bit is not challenging. Okay, I mean, there's always challenges with everything, but basically you have these. The beams that go around the LHC, the beams of particles, are divided into little bunches. So they're a bit like swarms of bees, if you like. And there are around, I think it's something of the order 2,000 bunches spaced around the ring. And if you're at a given point on the ring counting bunches, you get 40 million bunches passing you every second. So they come in like cars going past on a very fast motorway. Yeah. So you need to have, if your electric field that you're using to accelerate the particles, that needs to be timed so that as a bunch of protons arrives, it's got the right sign to attract them and then flips at the right moment. But I think the voltage in those boxes oscillates at hundreds of megahertz. So the beam's at like 40 megahertz, but it's oscillating much more quickly than the beam. So I think, it's difficult engineering, but in principle, it's not, a really serious challenge. The bigger problem.
There's probably engineers like screaming at you right now.
Probably.
Yeah.
Okay. So in terms of coming back to this thing, why is it so big? Well, the reason is you want to get the particles through that accelerating element over and over again. Yeah. So you want to bring them back round. That's why it's round. The question is, why couldn't you make it smaller? Well, the basic answer is that these particles are going unbelievably quickly. So they travel at 99.9999991% of the speed of light in the LHC. And if you think about, say, driving your car around a corner at a high speed, if you go fast, you need a lot of friction in the tires to make sure you don't slide off the road. So the limiting factor is how powerful a magnet can you make, because it's what we do is magnets are used to bend the particles around the ring. And essentially the LHC, when it was designed with the most powerful magnets that could conceivably be built at the time. And so that's your kind of limiting factor. So if you wanted to make the machine smaller, that means a tighter bend, you need to have a more powerful magnet. So it's this toss-up between how strong are your magnets versus how big a tunnel can you afford. The bigger the tunnel, the weaker the magnets can be. The smaller the tunnel, the stronger they've got to be.
Okay, so do good science. One of the things I don't think we really mentioned is on the final side, that's sort of the data analysis side. Is there breakthroughs possible there? And the machine learning side, like, is there a lot more signal to be mined in more effective ways from the actual raw data?
Yeah, a lot of people are looking into that. I mean, so, you know, I use machine learning in my data analysis, but pretty noddy, you know, basic stuff, because I'm not a machine learning expert. I'm just a physicist who had to learn to do this stuff, you know, for my day job. So what a lot of people do is they use kind of off-the-shelf packages that you can train to do signal noise, you know,
just clean up all the data.
But one of the big challenges is, you know, the big challenge of the data is its volume. There's huge amounts of data. So the LHC generates... Now, okay, I try to remember what the actual numbers are, but we don't record all our data. We record a tiny fraction of the data. It's like of order 1/10,000th or something, I think. Is that right? Around that. So most of it gets thrown away. You couldn't record all the LHC data because it would fill up every computer in the world in a matter of days, basically. Yeah. So there's this process that happens live on the detector, something called a trigger, which in real time, 40 million times every second, has to make a decision about whether this collision is likely to contain an interesting object like a Higgs boson or a dark matter particle. And it has to do that very fast. And the software algorithms in the past were quite relatively basic. You know, they did things like measure momentas and energies of particles and put some requirements. So you would say, if there's a particle with an energy above some threshold, then record this collision. But if there isn't, don't. Whereas now the attempt is to get more and more machine learning in at the earliest possible stage, because
that's cool, at the stage of deciding whether we want to keep this data or not.
But also even lower down than that, which is the point where there's this, you know, so generally how the data is reconstructed is you start off with a set of digital hits in your detector. So channels saying, did you see something? Did you not see something? That has to be then turned into tracks, particles going in different directions. And that's done by using fits that fit through the data points. And then that's passed to the algorithms that then go, is this interesting or not? What would be better is if you could train machine learning to just look at the raw hits, the real base level information, not have any of the reconstruction done. And it just goes, and it can learn to do pattern recognition on this strange 3-dimensional image that you get. And potentially that's where you could get really big gains, because our triggers tend to be quite inefficient because they don't have time to do the full whiz-bang processing to get all the information out that we would like, because you have to do the decision very quickly. So if you can come up with some clever machine learning technique, then potentially you can massively increase the amount of useful data you record and, you know, get rid of more of the background earlier in the process.
Yeah, to me, that's an exciting possibility, because then you don't have to build a you can get a gain without having to
build any hardware, I suppose. Yeah.
Hardware, yeah.
Although you need lots of new GPU farms, I guess.
So hardware still helps, but
yeah.
So let me ask the romantic question of what to you is the most, perhaps an unfair question, what is the most beautiful idea in physics? One that fills you with awe, is the most surprising, the strangest, the weirdest. There's a lot of different definitions of beauty. And I'm sure there's several for you, but is there something that just jumps to mind that you think is just especially beautiful?
There's a specific thing and a more general thing. So maybe the specific thing first, which is, when I first came across this as an undergraduate, I found this amazing. So this idea that the forces of nature, electromagnetism, the strong force, the weak force, they arise in our theories as a consequence of symmetries. So symmetries in the laws of nature, in the equations, essentially, that you use to describe these ideas. The process whereby theories come up with these sorts of models is they say, imagine the universe obeys this particular type of symmetry. It's a symmetry that isn't so far removed from a geometrical symmetry like the rotations of a cube. It's not, you can't think of it quite that way, but it's sort of a similar sort of idea. And you say, okay, if the universe respects this symmetry, you find that you have to introduce a force which has the properties of electromagnetism. Or a different symmetry, you get the strong force. Or a different symmetry, you get the weak force. Mm-hmm. So these interactions seem to come from some deeper, it suggests that they come from some deeper symmetry principle. I mean, depends a bit how you look at it, because it could be that we're actually just recognizing symmetries in the things that we see. But there's something rather lovely about that. But I mean, I suppose a bigger thing that makes me wonder is actually, if you look at the laws of nature, you look at how particles interact when you get really close down, they're basically pretty simple things. They bounce off each other by exchanging, through force fields, and they move around in very simple ways. And somehow these basic ingredients, these few particles that we know about and the forces, creates this universe which is unbelievably complicated and has things like you and me in it, and the Earth and stars that make matter in their cores from the gravitational energy of their own bulk that then gets sprayed into the universe that forms other things. I mean, the fact that there's this incredibly long story that goes right back to the beginning. We can take this story right back to a trillionth of a second after the Big Bang, and we can trace the origins of the stuff that we're made from, and it all ultimately comes from these simple ingredients with these simple rules. Yeah. And the fact you can generate such complexity from that is really mysterious, I think, and strange. And it's not even a question that physicists can really tackle, because we are sort of trying to find these really elementary laws. But it turns out that going from elementary laws in a few particles to something even as complicated as a molecule becomes very difficult. Mm-hmm. So going from a molecule to a human being is a problem that just, can't be tackled, at least not at the moment. So
yeah, the emergence of complexity from simple rules is so beautiful and so mysterious, and we don't have good mathematics to even try to approach that emergent phenomena.
That's why we have chemistry and biology and all the other subjects. Yeah, I guess.
I don't think there's a better way to end it, Harry. I think I speak for a lot of people that can't wait to see what happens in the next 5, 10, 20 years with you. I think you're one of the great communicators of our time. So I hope you continue that, and I hope that grows. And I'm definitely a huge fan. So it was an honor to talk to you today. Thanks so much, man.
Thanks very much.
Thanks for listening to this conversation with Harry Cliff, and thank you to our sponsors, ExpressVPN and Cash App. Please consider supporting the podcast by getting ExpressVPN at expressvpn.com/LexPod and downloading Cash App and using code LEXPODCAST. If you enjoy this podcast, subscribe on YouTube, review it with 5 stars on Apple Podcasts, support it on Patreon, or simply connect with me on Twitter at Lex Fridman. And now, let me leave you with some words from Harry Cliff. You and I are leftovers. Every particle in our bodies is a survivor from an almighty shootout between matter and antimatter that happened a little after the Big Bang. In fact, only 1 in a billion particles created at the beginning of time have survived to the present day. Thank you for listening, and hope to see you next time. Do you think we will ever create an AI system that we can love and loves us back in a deep, meaningful way, like in the movie Her?
I think AI will be capable of convincing you to fall in love with it very well.
And that's different than us humans?
We start getting into a metaphysical question of, like, do emotions and thoughts exist in a different realm than the physical? And maybe they do, maybe they don't. I don't know. But from a physics standpoint, I tend to think of things, like physics was my main sort of training, and from a physics standpoint, essentially, if it loves you in a way that you can't tell whether it's real or not, it is real.
That's a physics view of love.
Yeah. If you cannot prove that it does not, if there's no test that you can apply that would allow you to tell the difference, then there is no difference.
Right. And it's similar to seeing our world as simulation. There may not be a test to tell the difference between what the real world and the simulation, and therefore, from a physics perspective, it might as well be the same thing.
Yes. And there may be ways to test whether it's a simulation. There might be. I'm not saying there aren't. But you could certainly imagine that a simulation could correct that. Once an entity in the simulation found a way to detect the simulation, it could either restart, pause the simulation, start a new simulation, or do one of many other things that then corrects for that error.
So time and space are emergent. We kind of mentioned it in the beginning, but can you elaborate? What do you feel hope is fundamental in our universe?
A wave function living in Hilbert space.
A wave function in Hilbert space that we can't intellectualize or visualize, really.
We can't visualize it. We can intellectualize it very easily.
Like, well, how do you think about...
It's a vector in a 10 to the 10 to the 122 dimensional vector space. It's a complex vector, unit norm. It evolves according to the Schrodinger equation.
Got it. When you put it that way...
What's so hard, really?
It's like... what's the difference between math and physics to you?
To me, very, very roughly, math is about the logical structure of all possible worlds, and physics is about our actual world.
And it just feels like our actual world is a gray area when you start talking about interpretations of quantum mechanics, or no?
I'm certainly using the word world in the broadest sense, all of reality. So I think that reality is specific. I don't think that there's every possible thing going on in reality. I think that there are rules, whether it's the Schrodinger equation or whatever. So I think that there's a sensible notion of the set of all possible worlds, and we live in one of them. The world that we're talking about might be a multiverse, might be many worlds of quantum mechanics, might be much bigger than the world of our everyday experience, but it's still one physically contiguous world in some sense.
But, so if you look at the overlap of math and physics, it feels like when physics tries to reach for understanding of our world, it uses the tools of math to sort of reach beyond the limit of our current understanding. What do you make of that process of sort of using math to, so you start maybe with intuition, or you might start with the math and then build up an intuition, but this kind of reaching into the darkness, into the mystery of the world with math?
Well, I think I would put it a little bit differently. I think we have theories of the physical world, which we then extrapolate and ask, what do we conclude if we take these seriously well beyond where we've actually tested them? It is separately true that math is really, really useful when we construct physical theories. And, famously, Eugene Wigner asked about the unreasonable success of mathematics and physics. I think that's a little bit wrong, because anything that could happen, any other theory of physics that wasn't the real world but some other world, you could always describe it mathematically. It's just that it might be a mess. The surprising thing is not that math works, but that the math is so simple and easy that you can write it down on a t-shirt, right? I mean, that's what is amazing. That's an enormous compression of information that seems to be valid in the real world. So that's an interesting fact about our world, which maybe we could hope to explain or just take as a brute fact. I don't know. But once you have that, there's the indelible relationship between math and physics. But philosophically, I do want to separate them. What we extrapolate, we don't extrapolate math because there's a whole bunch of wrong math, that doesn't apply to our world, right? We extrapolate the physical theory that we best think explains our world.
Isaac Newton developed what we now call classical mechanics, that you describe very nicely in your book, as you do with a lot of basic concepts in physics. So, what's classical mechanics? I can throw a rock and can predict the trajectory of that rock's flight. But if we could put ourselves back into Newton's time, his theories worked to predict things, but as I understand, he himself thought that their interpretations of those predictions were absurd. Perhaps he just said it for religious reasons and so on. But in particular, sort of a world of interaction without contact. So action at a distance. It didn't make sense to him on a sort of a human interpretation level. Does it make sense to you that things can affect other things at a distance?
It does, but that was one of Newton's worries. You're actually right in a slightly different way about the religious worries. He was smart enough. This is off the topic, but still fascinating. Newton almost invented chaos theory as soon as he invented classical mechanics. He realized that in the solar system, so he was able to explain how planets move around the sun, but typically you would described the orbit of the Earth, ignoring the effects of Jupiter and Saturn and so forth, just doing the Earth and the Sun. He kind of knew, even though he couldn't do the math, that if you included the effects of Jupiter and Saturn and the other planets, the solar system would be unstable, like the orbits of the planets would get out of whack. So he thought that God would intervene occasionally to sort of move the planets back into orbit, which is only way you could explain how they were there, presumably forever. But the worries about classical mechanics were a little bit different. The worry about gravity in particular. It wasn't a worry about classical mechanics. It was a worry about gravity. How in the world does the Earth know that there's something called the sun 93 million miles away that is exerting a gravitational force on it? And he literally said, I leave that for future generations to think about because I don't know what the answer is. And in fact, the people underemphasize this, but future generations figured it out. Pierre-Simon Laplace in circa 1800 showed that you could rewrite Newtonian gravity as a field theory. So instead of just talking about the force due to gravity, you can talk about the gravitational field or the gravitational potential field. And then there's no action at a distance. It's exactly the same theory empirically. It makes exactly the same predictions. But what's happening is instead of the sun just reaching out across the void, there is a gravitational field in between the sun and the Earth that obeys an equation, Laplace's equation, cleverly enough, and that tells us exactly what the field does. So even in Newtonian gravity, you don't need action at a distance. Now, what many people say is that Einstein solved this problem because he invented general relativity. And in general relativity, there's certainly a field in between the Earth and the sun, but also there's the speed of light as a limit. In Laplace's theory, which was exactly Newton's theory, just in a different mathematical language, there could still be instantaneous action across the universe. Whereas in general relativity, if you shake something here, its gravitational impulse radiates out at the speed of light, and we call that a gravitational wave, and we can detect those. So, but I really, it rubs me the wrong way to think that we should presume the answer should look one way or the other. Like if it turned out that there was action at a distance in physics, and that was the best way to describe things, then I would do it that way. It's actually a very deep question because when we don't know what the right laws of physics are, when we're guessing at them, when we're hypothesizing at what they might be, we are often guided by our intuitions about what they should be. I mean, Einstein famously was very guided by his intuitions, and he did not like the idea of action at a distance. We don't know whether he was right or not. It depends on your interpretation of quantum mechanics, and it depends on even how you talk about quantum mechanics within any one interpretation.
So if you see every force as a field or any other interpretation of action at a distance, I mean, it's just stepping back to sort of caveman thinking. Like, can you really sort of understand what it means for a force to be a field that's everywhere? So if you look at gravity, like what do you think about?
I think so.
So is this something that you've been conditioned by society to think that, to map the fact that science is extremely well predictive of something to believing that you actually understand it, like you can intuitively, to the degree that human beings can understand anything, that you actually understand it? Or are you just trusting the beauty and the power of the predictive power of science?
That depends on what you mean by this idea of truly understanding something, right? I mean, can I truly understand Fermat's last theorem? It's easy to state it, but do I really appreciate what it means for incredibly large numbers, right? Yeah, I think yes. I think I do understand it. But like, if you want to just push people on, well, but your intuition doesn't go to the places where Andrew Wiles needed to go to prove Fermat's last theorem, then I can say, fine, but I still think I understand the theorem. And likewise, I think that I do have a pretty good intuitive understanding of fields pervading space-time, whether it's the gravitational field or the electromagnetic field or whatever, the Higgs field. Of course, one's intuition gets worse and worse as you get trickier into quantum field theory and all sorts of new phenomena that come up in quantum field theory. So our intuitions aren't perfect. But I think it's also okay to say that our intuitions get trained, right? Like, I have different intuitions now than I had when I was a baby. That's okay. That's not, an intuition is not necessarily intrinsic to who we are. We can train it a little bit.
So that's where I'm going to bring in Noam Chomsky for a second, who thinks that our cognitive abilities are sort of evolved through time. And so they're biologically constrained. And so there's a clear limit, as he puts it, to our cognitive abilities. And it's a very harsh limit. But you actually kind of said something interesting, the nature versus nurture thing here is we can train our intuitions to sort of build up the cognitive muscles to be able to understand some of these tricky concepts. So do you think there's limits to our understanding that's deeply rooted, hard-coded into our biology that we can't overcome?
There could be limits to things like our ability to visualize, okay? But when someone like Ed Witten proves a theorem about, 100-dimensional mathematical spaces, he's not visualizing it, he's doing the math. That doesn't stop him from understanding the result. I think, and I would love to understand this better, but my rough feeling, which is not very educated, is that, there's some threshold that one crosses in abstraction when one becomes kind of like a Turing machine, right? One has the ability to contain in one's brain logical, formal, symbolic structures and manipulate them. And that's a leap that we can make as human beings that dogs and cats haven't made. And once you get there, I'm not sure that there are any limits to our ability to understand the scientific world at all. Maybe there are. There's certainly limits on our ability to calculate things, right? People are not very good at taking cube roots of million-digit numbers in their head. But that's not a limit of understanding. It's certainly not a limit of principle.
So, of course, as a human, you would say there doesn't feel to be limits to our understanding. But sort of, have you thought that the universe is actually a lot simpler than it appears to us, and we just will never be able to, it's outside of our, so our cognitive abilities combined with our mathematical prowess and whatever kind of experimental simulation devices we can put together, is there limits to that? Is it possible there's limits to that?
Well, of course it's possible that there are limits to that. Is there any good reason to think that we're anywhere close to the limits is a harder question. Look, imagine asking this question 500 years ago to the world's greatest thinkers, right? Are we approaching the limits of our ability to understand the natural world? And by definition, there are questions about the natural world that are most interesting to us that are the ones we don't quite yet understand, right? So we're always faced with these puzzles we don't yet know. And I don't know what they would have said 500 years ago, but they didn't even know about classical mechanics, much less quantum mechanics. So we know that they were nowhere close to how well they could do, right? They could do enormously better than they were doing at the time. I see no reason why the same thing isn't true for us today. So of all the worries that keep me awake at night, the human mind's inability to rationally comprehend the world is low on the list.
Well, what are the most exciting problems in physics that are just within our reach of understanding and maybe solve the next few decades that you may be able to see?
So in physics, you limited it to physics.
Physics, mathematics, this kind of space of problems that fascinate you.
Well, the one that looks on the immediate horizon like we're going to get to is quantum computing. And if we actually get there, that's going to be extraordinarily interesting.
Do you think that's a fundamentally problem of theory, or is it now in the space of engineering?
It's in the space of engineering. I was out at Q Station. As you may know, Microsoft has this research facility in Santa Barbara. Mm-hmm. I was out there a couple of months in my capacity as vice president of the American Physical Society. And I had some things that were like lectures, and they were telling me what they were doing. And it sure sounded like they knew what they were doing and that they were close to major breakthroughs.
Yeah, that's a really exciting possibility. What to you is the most beautiful idea, maybe the most surprising or mysterious idea in physics?
The most surprising idea to me is that we can actually do physics. The universe did not have to be constructed in such a way that with our limited intellectual capacity, that is actually put together in such a way, and that we are put together in such a way that we can, with our mind's eye, delve incredibly deeply into the structure of the universe. That, to me, is pretty close to a miracle.
So there's simple equations, relatively simple, that can describe things, the fundamental functions They can describe everything about our reality. That's not. Can you imagine universes where everything is a lot more complicated? Do you think there's something inherent about universes that simple laws are?
Well, first of all, let me. This is a question that I encounter in a number of guises. A lot of people will raise the question about whether mathematics is the language of the universe. And my response is mathematics is the language that we humans are capable of using in describing the universe. It may have little to do with the universe, but in terms of our capacity, it's the microscope, it's the telescope through which it's the lens through which we are able to view the universe with a precision that no other human language allows. So could there be other universes? Well, I don't even know if this one looks like I think it does.
But the beautiful, surprising thing is that physics, there are laws of physics, very few laws of physics that can effectively compress down the functioning of the universe.
Yes, that's extraordinarily surprising. I like to use the analogy with computers and information technology. If you worry about transmitting large bundles of data, one of the things that computer scientists do for us is they allow for processes that are called compression, where you take big packets of data and you press them down into much smaller packets, and then you transmit those and then unpack them at the other end. And so it looks a little bit to me like the universe has kind of done us a favor. It's constructed our minds in such a way that we have this thing called mathematics, which then as we look at the universe teaches us how to carry out the compression process.
Maybe we should begin even before that at the very base layer of the Wolfram Physics Project. Maybe you can give a broad overview, once again, really quick about this hypergraph model.
Yes.
And also, what is it, a year and a half ago since you've brought this project to the world? What is the status update? What are all the beautiful ideas you have come across? What are the interesting things you can sort of mention?
It's a frigging Cambrian explosion. I mean, it's crazy. I mean, there are all these things which I've kind of wondered about for years, and suddenly there's actually a way to think about them. Mm-hmm. And I really did not see. I mean, the real strength of what's happened, I absolutely did not see coming. And the real strength of it is we've got this model for physics, but it turns out it's a foundational kind of model that's a different kind of computation-like model that I'm kind of calling the sort of multi-computational model. Mm-hmm. And that kind of model is applicable not only to physics, but also to lots of other kinds of things. And one reason that's extremely powerful is because physics has been very successful. So we know a lot based on what we figured out in physics. And if we know that the same model governs physics and governs, I don't know, economics, linguistics, immunology, whatever, we know that the same kind of model governs those things. We can start using things that we've successfully discovered in physics and applying those intuitions in all these other areas. And that's pretty exciting and very surprising to me. And in fact, it's kind of like in the original story of sort of you go and you explain why is there complexity in the natural world, then you realize, well, there's all this complexity, there's all this computational irreducibility, there's a lot we can't know about what's going to happen. It's kind of a very confusing thing for people who say, science has nailed everything down. We're going to, based on science, we can know everything. Mm-hmm. Well, actually, there's this computational irreducibility thing right in the middle of that, thrown up by science, so to speak. And then the question is, well, given computational irreducibility, how can we actually figure out anything about what happens in the world? Why are we able to predict anything? Why are we able to sort of operate in the world? And the answer is that we sort of live in these slices of computational reusability that exist in this kind of ocean of computational irreducibility. And it turns out that it seems that it's a very fundamental feature of the kind of model that seems to operate in physics and perhaps in a lot of these other areas, that there are these particular slices of computational reducibility that are relevant to us. And those are the things that both allow us to operate in the world mm-hmm. and not just have everything be completely unpredictable, but they're also things that potentially give us what amount to sort of physics-like laws mm-hmm. in all these other areas. So that's been sort of an exciting thing. But I would say that in general for our project, it's been going spectacularly well. I mean, it's very, honestly, it wasn't something I expected to happen in my lifetime. I mean, it's something where and in fact, one of the things about it, some of the things that we've discovered are things where I was pretty sure that wasn't how things worked. And turns out I'm wrong. And, in a major area in mathematics, I'd be realizing that something I've long believed, we can talk about it later, that just really isn't right. But I think that the thing that, so what's happened with the physics project, I mean, it can explain a little bit about how the model works, but basically...
We can maybe ask you the following question. So, it's easy through words to describe how cellular automata works. You've explained this. And it's the fundamental mechanism by which you, in your book, A New Kind of Science, explored the idea of complexity and how to do science in this world of reducible islands and general irreducibility. Okay, so how does the model of hypergraphs differ from cellular automata, and how does the idea of multi-computation differ? Like maybe that's a way to describe it.
All right. We're right. This is my life is, like all of our lives, something of a story of computational irreducibility.
Yes.
And, it's been going for a few years now. So it's always a challenge to kind of find these appropriate pockets of reducibility. But let me see what I can do.
Great.
So I mean, first of all, let's talk about physics, first of all. And, a key observation that the starting point of our physics project is things about what is space? What is the universe made of? And, ever since Euclid, people just sort of say space is just this thing where you can put things at any position you want. And they're just points and they're just geometrical things that you can just arbitrarily put at different coordinate positions. Sort of the first thing in our physics project is the idea that space is made of something. Just like water is made of molecules, space is made of kind of atoms of space. And the only thing we can say about these atoms of space is they have some identity. It's this atom as opposed to this atom. And, you could give them, if you were a computer person, you give them UUIDs or something. But,
yes.
But that's all there is to say about them, so to speak. And then all we know about these atoms of space is how they relate to each other. So we say these three atoms of space are associated with each other in some relation. So you can think about that as, what atom of space is friends with what other atom of space. You can build this essentially friend network of the atoms of space. And the sort of starting point of our physics project is that's what our universe is. It's a giant friend network of the atoms of space. And so how can that possibly represent our universe? Well, it's like in something like water, there are molecules bouncing around, but on a large scale, that produces fluid flow, and we have fluid vortices, and we have all of these phenomena that are sort of the emergent phenomena from that underlying kind of collection of molecules bouncing around. And by the way, it's important that collection of molecules bouncing around have this phenomenon of computational irreducibility. That's actually what leads to the second law of thermodynamics, among other things. And that leads to the sort of randomness of the underlying behavior, which is what gives you something which on a large scale seems like it's a smooth, continuous type of thing. And so first thing is space is made of something. It's made of all these atoms of space connected together in this network. And then everything that we experience is sort of features of that structure of space. So, when we have an electron or something or a photon, it's some kind of tangle in the structure of space, much like kind of a vortex in a fluid would be just this thing that is, it can actually, the vortex can move around. It can involve different molecules in the fluid, but the vortex still stays there.
And if you zoom out enough, the vortex looks like an atom itself, like a basic element.
Yes.
So there's the levels of abstraction. If you squint and kind of blur things out, it looks like at every level of abstraction, you can define what is a basic individual entity.
Yes, but in this model, there's a bottom level.
Yeah.
There's an elementary length. Maybe
that
it's 10 to the minus 100 meters, let's say, which is really small. A proton is 10 to the minus 15 meters. The smallest we've ever been able to sort of see with a particle accelerator is around 10 to the minus 21 meters. So, if we don't know precisely what the correct scale is, but it's perhaps over the order of 10 to the minus 100 meters. So it's pretty small. But that's the end. That's what things are made of.
What's your intuition where the 10 to the minus 100 comes from? What's your intuition about this scale?
Well, okay, so there's a calculation which I consider to be somewhat rickety, okay, which has to do with comparing. So there are various fundamental constants. There's the speed of light. The speed of light, once you know the elementary time, the speed of light tells you the conversion from the elementary time to the elementary length. Then there's the question of how do you convert to the elementary energy, and how do you convert to between other things? And the various constants we know. We know the speed of light. We know the gravitational constant. We know Planck's constant in quantum mechanics. Those are the three important ones. And we actually know some other things. We know things like the size of the universe, the Hubble constant, things like that. And essentially this calculation of the elementary length comes from looking at these sort of combination of those. Okay, so the most obvious thing, people have sort of assumed that quantum gravity happens at this thing, the Planck scale, 10 to the minus 34 meters, which is the sort of the combination of Planck's constant and the gravitational constant, the speed of light, that gives you that kind of length. Turns out in our model, there is an additional parameter, which is essentially the number of simultaneous threads of execution of the universe, which is essentially the number of sort of independent quantum processes that are going on. And that number, let's see if I remember that number is 10 to the 170, I think. And so it's a big number. But that number then connects, sort of modifies what you might think from all these Planck units to give you the things we're giving. And there's been sort of a mystery, actually, there's a more technical physics thing, that the Planck mass, the Planck energy is actually surprisingly big. The Planck length is tiny, 10 to the minus 34 meters. Planck time, 10 to the minus 43 meters, I think, seconds, I think. But the Planck energy is like the energy of a lightning strike, okay, which is pretty weird. In our models, the actual elementary energy is that divided by the number of sort of simultaneous quantum threads, and it ends up being really small too. And that sort of explains that mystery that's been around for a while about how Planck units work. But whether that precise estimate is right, we don't know yet. I mean, that's one of the things that's sort of been a thing we've been pretty interested in, is how do you see through, how do you make a gravitational microscope that can kind of see through to the atoms of space? How do you get in fluid flow, for example, if you go to hypersonic flow or something, you've got a Mach 20, space plane or something, it really matters that there are individual molecules hitting the space plane, not a continuous fluid. The question is, what is the analogous kind of, what is the analog of hypersonic flow for things about the structure of space-time? And it looks like a rapidly rotating black hole, right at the sort of critical rotation rate, it looks as if that's a case where essentially the structure of space-time is just about to fall apart, and you may be able to kind of see the evidence of sort of discrete elements. You may be able to kind of see the sort of gravitational microscope of actually seeing these discrete elements of space. And there may be some effect in, for example, gravitational waves produced by rapidly rotating black hole, that in which one could actually see some phenomenon where one can say, yes, these don't come out the way one would expect based on having a continuous structure of space-time. It is something where you can kind of see through to the discrete structure. We don't know that yet.
You often talk about getting off this planet. And I think you don't often talk about extraterrestrial life, intelligent life out there. Do you wonder about this kind of thing, about intelligent civilizations out there?
I do, but I try to not wonder about it in a particular way. In a certain sense, I do find that speculating about Bigfoot and the Loch Ness Monster and space aliens is kind of a recreation for when things aren't going very well. At least it gives us some meaning and purpose in our lives. So I worry about, for example, the simulation hypothesis is taking over from religion. You can't quite believe enough to go to church or synagogue or the mosque on the weekend, so then you just take up an interest in the simulation theory because that's something like what you do for your job coding. I do think that in some sense the issue of aliens is a really interesting one, but has been spoiled by too much sort of recreational escapism. The key question that I find is, let's assume that it is possible to look out at the night sky and see all of these distant worlds and then go visit them. If that is possible, it's almost certainly possible through some as yet unknown or not accepted theory of physics beyond Einstein. And I mean, it doesn't have to be that way, but probably is. If that theory exists, there would be a percentage of the worlds that have life in sort of a Drake equation kind of a way that would have encountered the ability to escape soon enough after unlocking the power of the atom at a minimum and whatever they have that is probably analogous to the cell on that world. So assuming that life is a fairly generic thing that arises, probably not carbon-based, probably doesn't have DNA, but that something that fits the pattern of Darwinian theory, which is descent with variation, differential success,
and thereby constantly improving and so on, that through time there will be a trajectory where there will be something increasingly complex and fascinating and beautiful like us humans, but much more.
That can also off-gas whatever entropy it creates to give an illusion that you're defeating thermodynamics, right? So whatever these things are, probably has an analog of the bilipid layer so that cells can get rid of the chaos on one side of the barrier and keep order on the other. Whatever these things are that create life, assuming that there is a theory to be found that allows that civilization to diversify, we would have to imagine that such a civilization might have taken an interest in its concept of the universe and have come here.
They would come here. They would have a deep understanding of the physics of the universe sufficient to have arrived here.
Well, there's two questions, whether they could arrive physically and whether their information could be sent here and whether they could gain information from us. It's possible that they would have a way of looking into our world without actually reaching it. I don't know. But yes, if my hope, which is that we can escape this world, can be realized, if that's feasible, then you would have to imagine that the reverse is true and that somebody else should be here.
You're both a physicist and a mathematician. So let me ask, what is the difference between physics and mathematics?
Well, there's kind of a conventional understanding of the subject that they're two, quite different things. So that mathematics is about, making rigorous statements about these abstract things of mathematics and proving them rigorously. And physics is about, doing experiments and testing various models and that. But I think the more interesting thing is that there's a wide variety of what people do as mathematics, what they do as physics, and there's a significant overlap. And that I think is actually the much very, very interesting area. And if you go back kind of far enough to in history and look at figures like Newton or something, I mean, at that point, you can't really tell, was Newton a physicist or a mathematician? The mathematicians will tell you he's a mathematician, the physicists will tell you he's a physicist. But
he would say he's a philosopher.
Yeah, that's interesting. But anyway, there was kind of no such distinction then. It's more of a modern thing. But anyway, I think these days there's a very interesting space in between the two.
So in the story of the 20th century and the early 21st century, what is the overlap between mathematics and physics, would you say?
Well, I think it's actually become very, very complicated. I think it's really interesting to see a lot of what my colleagues in the math department are doing. Most of what they're doing all sorts of different things, but most of them have some kind of overlap with physics or other. So, I mean, I'm personally interested in one particular aspect of this overlap, which I think has a lot to do with the most fundamental ideas about physics and about mathematics. But there's just you kind of see this really everywhere at this point.
Which particular overlap are you looking at? Group theory?
Yeah. So at least the way it seems to me that if you look at physics and look at our most successful laws of fundamental physics, they're really, they have a certain kind of mathematical structure. It's based upon certain kind of mathematical objects and geometry, connections and curvature, the spinors, the Dirac equation, and this very deep mathematics provides kind of a unifying set of ways of thinking that allow you to make a unified theory of physics. But the interesting thing is that if you go to mathematics and look at what's been going on in mathematics the last 50, 100 years, and even especially recently, there's similarly some kind of unifying ideas which bring together different areas of mathematics, and which have been especially powerful in number theory recently. And there's a book, for instance, by Edward Frankel about love and math. And
that book's great. I recommend it highly. It's partially accessible, but there's a nice audiobook that I listened to while running an exceptionally long distance, like across the San Francisco bridge. And there's something magic about the way he writes about it. But some of the group theory in there is a little bit difficult.
That's the problem with any of these things. To kind of really say what's going on and make it accessible is very hard. He, in this book and elsewhere, I think, takes the attitude that kinds of mathematics he's interested in and that he's talking about provide kind of a grand unified theory of mathematics. They bring together geometry and number theory and representation theory, a lot of different ideas in a really unexpected way. But I think to me the most fascinating thing is if you look at the kind of grand unified theory of mathematics he's talking about, and you look at the physicists' kind of ideas about unification, it's more or less the same mathematical objects are appearing in both. So it's this, I think we're seeing a really strong indication that, the deepest ideas that we're discovering about physics and some of the deepest ideas that mathematicians are learning about are intimately connected.
Is there something, like, if I was 5 years old and you were trying to explain this to me, is there ways to try to sneak up to what this unified world of mathematics looks like? You said number theory, you said geometry, words like topology. What does this universe begin to look like? What should we imagine in our mind? Is it a three-dimensional surface and we're trying to say something about it? Is it triangles and squares and cubes? Like, what are we supposed to imagine in our minds? Is this natural number? What's a good thing to try for people that don't know any of these tools except maybe some basic calculus and geometry from high school that they should keep in their minds as to the unified world of mathematics that also allows us to explore the unified world of physics?
What I find kind of remarkable about this is the way in which we've discovered these ideas, but they're actually quite alien to our everyday understanding. We grow up in this three spatial dimensional world, and we have intimate understanding of certain kinds of geometry and certain kinds of things. But these things that we've discovered in both math and physics they're not at all close, have any obvious connection to kind of human everyday experience. They're really quite different. And I can say some of my initial fascination with this when I was young and starting to learn about it was actually exactly this kind of arcane nature of these things. It was a little bit like being told, well, there are these kind of semi-mystical experience that you can acquire by long study and whatever, except that it was actually true. There's actually evidence that this actually works. So, I'm a little bit wary of trying to give people that kind of thing because I think it's mostly misleading. But one thing to say is that, that geometry is a large part of it. And maybe one interesting thing to say that's about some of the most recent ideas is that when we think about the geometry of our space and time, it's kind of three spatial and one time dimension. It's physics is in some sense about something that's kind of four-dimensional in a way. Mm-hmm. And a really interesting thing about some of the recent developments in number theory have been to realize that these ideas that we were looking at, naturally fit into a context where your theory is kind of four-dimensional. So geometry is a big part of this, and we know a lot and feel a lot about 1, 2, 3-dimensional geometry.
So wait a minute. So we can at least rely on the 4 dimensions of space and time and say that we can get pretty far by working in that in those 4 dimensions? I thought you were going to scare me that we're going to have to go to many, 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 many more dimensions than that.
My point of view, which goes against a lot of these ideas about unification, is that no, this is really everything we know about really is about 4 dimensions. That and that you can actually understand a lot of these structures that we've been seeing in fundamental physics and in number theory, just in terms of 4 dimensions. That it's in some sense, I would claim, has been kind of a mistake that physicists have made for decades and decades to try to go to higher dimensions, to try to formulate a theory in higher dimensions, and then you're stuck with the problem of how do you get rid of all these extra dimensions that you've created, and because we only ever see anything in 4 dimensions. That
kind of thing leads us astray, you think? So creating all these extra dimensions just to give yourself extra degrees of freedom. Yeah. Isn't that the process of mathematics, is to create all of these trajectories for yourself, but eventually you have to end up at like a final place. But it's okay to sort of create abstract objects on your path to proving something.
Yeah, certainly. And from mathematicians' point of view, I mean, the kinds of mathematicians also are very different than physicists in that we like to develop very general theories. We like to, if we have an idea, we want to see what's the greatest generality in which you can talk about it. Mm-hmm. So from the point of view of most of the ways geometry is formulated by mathematicians, it really doesn't matter. It works in any dimension. We can do 1, 2, 3, 4, any number. There's no particular, for most of geometry, there's no particular special thing about 4. But and anyway, but what physicists have been trying to do over the years is try to understand these fundamental theories in a geometrical way, and it's very tempting to kind of just start bringing in extra dimensions and using them to explain the structure. But it typically this attempt kind of founders because you just don't know. You end up not being able to explain why we only see 4. And anyway.
It is nice in the space of physics that, like if you look at Fermat's last theorem, it's much easier to prove that there's no solution for n equals 3 than it is for the general case. And so I guess that's the nice benefit of being a physicist, is you don't have to worry about the general case because we live in a universe with n equals 4 in this case.
Yeah, physicists are very interested in saying something about specific examples. And I find that interesting. Even when I'm trying to do things in mathematics, and I'm even teaching courses to mathematics students, I find that I'm teaching them in a different way than most mathematicians, because I'm very often very focused on examples, on what's kind of the crucial example that shows how this powerful new mathematical technique, how it works and why you would want to do it. And I'm less interested in kind of, proving a precise theorem about exactly when it's going to work and when it's not going to work.
Do you usually think about really simple examples, like both for teaching and when you try to solve a difficult problem? Do you construct like the simplest possible examples that captures the fundamentals of the problem and try to solve it?
Yeah, exactly. That's often a really fruitful way to, if you've got some idea, to just kind of try to boil it down to what's the simplest situation in which this kind of thing is going to happen, and then try to really understand that, and that is almost always a really good way to get insight into.
Do you work with paper and pen, or like, for example, for me, coming from the programming side, if I look at a model, if I look at some kind of mathematical object, I like to mess around with it sort of numerically. I just visualize different parts of it, visualize however I can. So most of the work is like with neural networks, for example, is you try to play with the simplest possible example and just to build up intuition by, any kind of object has a bunch of variables in it. Yeah. And you start to mess around with them in different ways and visualize in different ways to start to build intuition. Or do you go the Einstein route and just imagine like everything inside your mind and sort of build like thought experiments and then work purely on paper and pen?
Well, the problem with this kind of stuff that I'm interested in is you rarely can kind of, it's rarely something that is really kind of or even the simplest example, you can kind of see what's going on by looking at something happening in 3 dimensions. There's generally the structures involved are either they're more abstract, or if you try to kind of embed them in some kind of space where you could manipulate them in some kind of geometrical way, it's going to be a much higher dimensional space.
So even simple examples, the embedding them into 3-dimensional space, you're losing a lot.
Yeah, but to capture what you're trying to understand about them, you have to go to 4 or more dimensions. So it starts to get to be hard to. I mean, you can train yourself to try it as much as to kind of think about things in your mind. And I often use pad and paper, and if I'm in my office, I often use the blackboard. And you are kind of drawing things, but they're really kind of more abstract representations of how things are supposed to fit together, and they're not really, unfortunately, not just kind of really living in 3 dimensions where you can.
Are we supposed to be sad or excited by the fact that our human minds can't fully comprehend the kind of mathematics you're talking about? I mean, what do we make of that? I mean, to me, that makes me quite sad. It makes it seem like there's a giant mystery out there that we'll never truly get to experience directly.
It is kind of sad, how difficult this is. I mean, or I would put it a different way that, most questions that people have about this kind of thing, you can give them a really a true answer and really understand it, but the problem is one more of time. It's like, yes, I could explain to you how this works, but you'd have to be willing to sit down with me and work at this repeatedly for hours and days and weeks, and it's just going to take that long for your mind to really wrap itself around what's going on, and that does make things inaccessible, which is sad, but it's just kind of part of life that we all have a limited amount of time, and we have to decide what we're gonna spend our time doing.
Speaking of a limited amount of time, think about the potential of quantum computers simulating quantum mechanical systems, and through that sneak up to sort of through simulation, sneak up to a deep understanding of the fundamental physics.
The problem there is that's promising more for this for Phil Anderson's problem, that if you want to, there's lots and lots of, if you start putting together lots and lots of things, and we think we know that are pair by pair interactions, but what this thing is going to do, we don't have any good calculational techniques. Quantum computers may very well give you those, and so they may, what we think of as kind of strong coupling behavior, we have no good way to calculate. Even though we can write down the theory, we don't know how to calculate anything with any accuracy in it. The quantum computers may solve that problem, but the problem is that I don't think that they're going to solve the problem, that they help you with the problem of not having of knowing what the right underlying theory is.
As somebody who likes experimental validation, let me ask you the perhaps ridiculous sounding, but I don't think it's actually a ridiculous question of, do you think we live in a simulation? Do you find that thought experiment at all useful or interesting?
Not really. Not really. I don't. It just doesn't. Yeah. And anyway, to me, it doesn't actually lead to any kind of lead anywhere interesting. And
yeah, to me, so maybe I'll throw a wrench into your thing. To me, it's super interesting from an engineering perspective. So if you look at virtual reality systems, the actual question is, how much computation and how difficult is it to construct a world that, there's several levels here. One is you won't know our human perception systems, and maybe even the tools of physics won't know the difference between the simulated world and the real world. That's sort of more of a physics question. The most interesting question to me has more to do with why food tastes delicious, which is how difficult and how much computation is required to construct a simulation where you kind of know it's a simulation at first, but you want to stay there anyway. And over time, you don't even remember.
Yeah. Well, anyway, I agree. These are kind of fascinating questions, and they may be very, very relevant to our future as a species. But yeah, they're just very far from anything
But so from a physics perspective, it's not useful to you to think, taking a computational perspective to our universe, thinking of it as an information processing system, and then think of it as doing computation, and then you think about the resources required to do that kind of computation and all that kind of stuff. You could just look at the basic physics, and who cares what the computer it's running on is.
Yeah, it just, I mean, the kinds of, I mean, I'm willing to agree that you can get into interesting kinds of questions going down that road, but they're just so different from anything, from what I've found interesting, that I just have to kind of go back to life is too short. And I'm very glad other people are thinking about this, but I just don't see anything I can do with it.
Let me ask, from what field do you think the biggest breakthroughs in understanding the mind will come in the next decades? Is it neuroscience, computer science, neurobiology, psychology, physics, maybe math, maybe literature?
Well, of course, I see the world always through a lens of physics. I grew up in physics, and the way I pick problems is very characteristic of physics and of an intellectual background, which is not psychology, which is not chemistry, and so on and so on.
Both of your parents are physicists.
Both of my parents were physicists, and the real thing I got out of that was a feeling that the world is an understandable place. And if you do enough experiments and think about what they mean and structure things so you can do the mathematics of the relevant to the experiments, you ought to be able to understand how things work.
But that was a few years ago. Did you change your mind at all through many decades of trying to understand the mind, of studying it different kinds of ways? Not even the mind, just biological systems. You still have hope that physics, that you can understand?
There's a question of, what do you mean by understand?
Of course.
When I taught freshman physics, I used to say, I wanted to get physics to understand this subject, to understand Newton's laws. I didn't want them simply to memorize a set of examples to which they knew the equations to write down to generate the answers. I had this nebulous idea of understanding, so that if you looked at a situation, you could say, oh, I expect the ball to make that trajectory, or I expect some intuitive notion of understanding. And I don't know how to express that very well, and I've never known how to express it well. And you run smack up against it when you do look at these simple neural nets, feed-forward neural nets, which do amazing things, and yet contain nothing of the essence of what I would have felt was understanding. Understanding is more than just an enormous lookup table.
Let's linger on that. How sure you are of that? What if the table gets really big? So, I mean, asked another way, these feed-forward neural networks, do you think they'll ever understand?
Could answer that in two ways. I think if you look at real systems, feedback is an essential aspect of how these real systems compute. On the other hand, if I have a mathematical system with feedback, I know I can unlayer this and do it feed forward. But I have an exponential expansion in the amount of stuff I have to build if I'm going to solve the problem that way.
So feedback is essential. So we can talk even about recurrent neural networks, so recurrence. But do you think all the pieces are there to achieve understanding through these simple mechanisms? Like, back to our original question, is there a fundamental difference between artificial neural networks and biological, or is it just a bunch of surface stuff?
Suppose you ask a neurosurgeon, when is somebody dead?
Yeah.
They'll probably go back to saying, well, I can look at the brain rhythms and tell you this is a brain which is never going to function again. This other one is one that if we treat it well is still recoverable. And then just do that by some electrodes looking at simple electrical patterns which don't look in any detail at all at what individual neurons are doing. These rhythms are utterly absent from anything which goes on at Google.
Yeah, but the rhythms...
But the rhythms what?
So, well, that's like comparing... Okay, I'll tell you. It's like you're comparing the greatest classical musician in the world to a child first learning to play. The question I'm at... But they're still both playing the piano. I'm asking, will it ever go on at Google? Do you have a hope? Because you're one of the seminal figures in launching both disciplines, both sides of the river.
I think it's going to go on generation after generation the way it has, where what you might call the AI computer science community says, let's take the following. This is our model of neurobiology at the moment. Let's pretend it's good enough and do everything we can with it. And it does interesting things, and after the while, it sort of grinds into the sand. And you say, something else is needed for neurobiology, and some other grand thing comes in and enables you to go a lot further. But we'll go into the sand again. And I think there can be generations of this evolution. And I don't know how many of them, and each one is going to get you further into what a brain does, and in some sense, past the Turing test, longer and in more broad aspects. And how many of these there are going to have to be before you say, I've made a human, I don't know.
But your sense is it might be a couple.
My sense is it might be a couple more.
Yeah.
And going back to my brain waves, as it were.
Yes.
From the AI point of view, they would say, maybe these are an epiphenomenon and not important at all. The first car I had, a real wreck of a 1936 Dodge, go above about 45 miles an hour and the wheels would shimmy.
Yeah.
Good speedometer, that. Now, nobody designed the car that way. The car is malfunctioning to have that. But in biology, if it were useful to know when are you going more than 45 miles an hour, you just capture that, and you wouldn't worry about where it came from.
Yeah.
And it's going to be a long time before that kind of thing, which can take place in large, complex networks of things, is actually used in the computation. Look, how many transistors are there in your laptop these days?
Actually, I don't know the number. It's
on the scale of 10 to the 10. I can't remember the number either.
Yeah.
And all the transistors are somewhat similar. And most physical systems with that many parts, all of which are similar, have collective properties.
Yes.
Sound waves in air, earthquakes, what have you, have collective properties. Weather. There are no collective properties used in artificial neural networks, in AI.
Yeah, it's very...
If biology uses them, it's going to take us to more generations of things for people to actually dig in and see how they are used and what they mean.
See, you're very right. We might have to return several times to neurobiology and try to make our transistors more messy.
Yeah. At the same time, the simple ones will conquer big aspects. And I think one of the biggest surprises to me was how well learning systems which are manifestly non-biological, how important they can be actually, and how important and how useful they can be in AI.
There, but let's go back to Moscow. So for episode 100, I talked to my dad, and also I grew up with my dad, I guess. So I had to put up with him for many years, and he went to the Fistech or MIPT. It's weird to say in English because I've heard all of this in Russian. Moscow Institute of Physics and Technology, and to me that was like, I met some super interesting, as a child, I met some super interesting characters. It felt to me like the greatest university in the world, the most elite university in the world. And just the people that I met that came out of there were like, not only brilliant, but also special humans. It seems like that place really tested the soul, both like in terms of technically and like spiritually. So that could be just the romanticization of that place. I'm not sure, but so maybe you can speak to it. But is it correct to say that you spent some time at Fistech?
Yeah, that's right. 6 years. I got my bachelor's and master's in physics and math there. And it's actually interesting because my dad, and actually both my parents went there. And I think all the stories that I heard, just like you, Alex, growing up about the place and how interesting and special and magical it was, I think that was a significant, maybe the main reason I wanted to go there for college. Enough so that I actually went back to Russia from the U.S. I graduated high school in the U.S. And
you went back there?
I went back there, yeah.
Wow.
Exactly the reaction most of my peers in college had, but perhaps a little bit stronger. That point me out as this crazy kid.
Were your parents supportive of that?
Yeah. Like to your previous question, they supported me in letting me pursue my passions and the things that I was.
That's a bold move. Wow. What was it like there?
It was interesting. Definitely fairly hardcore on the fundamentals of math and physics, and lots of good memories from those.
Now I was talking about you being a scientist on Earth, but say you were a scientist that were shipped over to Europa to investigate if there's life. What would you look for in terms of signs of life?
Life is unmistakable, I would say. The way that life transforms a planet surrounding it is not the kind of thing that you would expect from the physical laws alone. So I would say that as soon as life arises, it creates this compartmentalization. It starts pushing things away. It starts sort of keeping things inside that are self. And there's a whole signature that you can see from that. So when I was organizing my Meaning of Life symposium, my friend who's an astrophysicist, basically we were deciding on what would be the themes for the symposium. And then I said, well, we're going to have biology, we're going to have physics. And she's like, come on, biology is just a small part of physics.
Everything's a small part of physics,
and,
right?
I mean, in many ways it is. But my immediate answer was, no, wait. Life challenges physics. It supersedes physics. It sort of fights against physics. And that's what I would look for in Europa. I would basically look for this fight against physics, for anything that sort of signatures of not just entropy at work, not just things diffusing away, not just gravitational pulls, but clear signatures of, remember when I was talking earlier about this whole selection for environments, selection for biospheres, for ecosystems, for this multi-organism form of life. And I think that's sort of the first thing that you can look for, chemical signatures that are not simply predicted from the reactions you would get randomly.
Such a beautiful way to look at life. So you're basically leveraging some energy source to enable you to resist the physics of the universe.
Fighting against physics. But that's the first transformation. If you look at humans, we're way past that.
What do you mean by transformation?
So basically there's layers. I sort of see life, when we talk about the meaning of life can be construed at many levels. We talked about life in the simplest form of sort of the ignition of evolution. And that's sort of the basic definition that you can check off. Yes, it's alive. But when Alexander the Great was asked to whom do you owe your life? To your teachers or to your parents? And Alexander the Great answered, I owe to my parents the zine, the life itself, and I owe to my teachers the F zine, like euphony. F means good, the opposite of cacophony, which means, bad. So F zine, in his words, was basically living a human life, a proper life. So basically we can go from the zine to the F zine. And that transformation has taken several additional leaps. So basically, life on Europa, I'm pretty sure has gotten to the stage of A makes B, makes C, makes A again. But getting to the F zine is a whole other level. And that level requires cooperation. That level requires altruism. That level requires specialization. Remember how we were talking about the RNA specializing into DNA for storage, proteins, and then compartmentalizations? And if you look at prokaryotic life, there's no nucleus. It's all one soup of things intermingling. If you look at eukaryotic life, again, U for true, good, So a eukaryote basically has a nucleus. And that's where you compartmentalize further the organization of the information storage from all of the daily activities. If you look at a, human body plan or any animal, you have a compartmentalization of the germline. You basically have one lineage that will basically be saved for the future generations. And everything outside that lineage is almost superfluous. If you think about it, the rest of your body, all it does is ensure that that lineage will make it to the next generation, that these germlines will make it to the next generation. The rest is packaging. I'm sorry to be so blunt.
Yeah.
And if you look at nutrition, we're deuterostomes. What does deuterostome mean? Deutero means second, where this is the second mouth. The first mouth is actually down here, it's the esophagus. So deuterostomes have evolved a second layer of eating, kind of like Alien with the two mouths.
Yeah.
So you can think of us as Alien, where the first mouth is up here, and then the second mouth is down there.
Of course, is the first mouth just the physical manipulation of the food to make it more consumable?
Correct. And basically, again, if you look at a worm, it's an extremely simple life form. It basically has a mouth, it has an anus, and it has just some organs in between that consume the food and just spit out poop.
Yeah.
Humans are basically a fancy form of that. So you basically have the mouth, you have the digestive tract, and then you have limbs to get better at getting food. You have eyesight, hearing, etc., to get better at getting food.
Yeah.
And then you have, of course, the germline, and all of this food part, it's just auxiliary to the germline. So you basically have layers of addition, of compartmentalization, of specialization on top of this zine to get all the way to the F zine.
Yeah, so like the worm is like Windows 95, very few features, very basic, and then us humans are like Windows Vista or Windows 10, whatever it is.
Well, a few innovations beyond that, but yeah.
Beyond that, all right. Where, I don't know.
We're Windows 2000, at least put it that way.
You've mentioned that you were always curious about the physical world, and that an early question you remember stood out where you asked your dad, why does ice float on water? And he couldn't answer. And this was very surprising to you. So you went on to learn why. Maybe you can speak to what are some early questions in math and physics that really sparked your curiosity?
Yeah, that memory is kind of something I use to illustrate something I think that's common in science, that people that do science somehow have maintained something that kids always have. A small kid, 8 years old or so, asks you so many questions, typically, that you consider them pests. You tell them to stop asking so many questions. And somehow our system manages to kill that in most people. So in school, we make people study and do their things, but not to pester them by asking too many questions. And I think not just myself, but I think it's typical of scientists like myself that have somehow escaped that. Maybe we're still children, or maybe we somehow didn't get it beaten out of us. But I think I teach in college level, and it's, to me, one of the biggest deficits is the lack of curiosity, if you want, that we've beaten out of them, because I think it's an innate human quality.
Is there some advice or insights you can give to how to keep that flame of curiosity
I think it's
going?
a problem of both parents, and the parents should realize that's a great quality we have, that you're curious, and that's good. Instead, we have expressions like "curiosity killed the cat," and then more. But I mean, basically, it's not thought to be a good thing. Curiosity killed the cat means if you're too curious, you get in trouble. And
I don't like cats anyway, so maybe it's a good thing.
Yeah. That, to me, needs to be solved, really, in education and in homes. That's a realization that there's certain human qualities that we should try to build on and not destroy. One of them is curiosity. Anyway, back to me and curiosity. I was a pest and asked a lot of questions. My father generally could answer them, and at that age. And the first one I remember that he couldn't answer was not a very original question, but basically that ice is made out of water. And so why does it float on water? And he couldn't answer it. And it may not have been the first question. It's the first one that I remember. And that was the first time that I realized that to learn and answer your own curiosity or questions, there's various mechanisms. In this case, it was going to the library or asking people who know more and so forth. But eventually you do it by what we call research. But it's driven by, hopefully you ask good questions. If you ask good questions and you have the mechanisms to solve them, then you do what I do in life, basically. Not necessarily physics, but... and it's a great quality in humans, and we should nurture it.
Do you remember any other kind of, in high school, maybe early college, more basic physics ideas that sparked your curiosity, or mathematics or science in general?
I wasn't really into science until I got to college, to be honest with you. But just staying with water for a minute, I remember that I was curious what happens to water? It rains and there's water, a wet pavement, and then the pavement dries out. What happened to this water that came down? And I didn't know that much. And then eventually I learned in chemistry or something, water's made out of hydrogen and oxygen. Those are both gases. So how the heck does it make this substance? It's liquid.
Yeah, so that has to do with states of matter. You've, I know, perhaps LIGO and the thing for which you've gotten the Nobel Prize and the things, much of your life work, perhaps was a happy accident in some sense in the early days. But is there a moment where you looked up to the stars, and also the same way you wondered about water, wondered about some of the things that are out there in the universe?
Oh yeah, I think everybody's looks and is in awe and is curious about what it is out there. And and as I learned more, I learned, of course, that we don't know very much about what's there. And the more we learn, the more we know we don't know. I mean, we don't know what the majority of anything is out there. It's all what we call dark matter or dark energy. And that's one of the big questions. 20 years when I was a student, those weren't questions. So we even know less, in a sense, the more we look. So of course, I think that's one of the areas that almost it's universal. People see the sky, they see the stars, and they're beautiful, and see it looks different on different nights, and it's a curiosity that we all have.
What are some questions about the universe that in the same way that you felt about the ice, that today, you mentioned to me offline you're teaching a course on the frontiers of science, frontiers of physics.
Yeah.
What are some questions, outside the ones we'll probably talk about, that kind of, fill you with, get your flame of curiosity up and firing up, fill you with awe?
Well, first, I'm a physicist, not an astronomer. So I'm interested in the physical phenomenon, really. So the question of dark matter and dark energy, which we probably won't talk about, are recent. They're in the last 20, 30 years, or certainly dark energy. Dark energy is a complete puzzle. It goes against what you will ask me about, which is general relativity and Einstein's general relativity. It basically takes something that he thought was what he called a constant, which isn't, if that's even the right theory, and it represents most of the universe. And then we have something called dark matter, and there's good reason to believe it might be an exotic form of particles. And that is something I've always worked on particle accelerators and so forth. And it's a big puzzle what it is. It's a bit of a cottage industry in that there's lots and lots of searches. But it may be a little bit like, looking for a treasure under rocks or something. It's hard to, we don't have really good guidance, except that we have very, very good information that it's pervasive and it's there. Mm-hmm. And that it's probably particles, small, that the evidence is all of those things. But then the most logical solution doesn't seem to work, something called supersymmetry.
Mm-hmm. And do you think the answer could be something very complicated?
I like to think that most things that appear complicated are actually simple if you really understand them. I think we just don't know at the present time, and it isn't something that affects us. It affects how the stars go around each other and so forth, because we detect that there's missing gravity, but it doesn't affect everyday life at all. I tend to think and expect maybe, and that the answers will be simple, and we just haven't found it yet.
Do you think those answers might change the way we see other sources of gravity, black holes, the way we see the parts of the universe that we do study?
It's conceivable. The black holes that we've found in our experiment, and we're trying now to understand the origin of those. It's conceivable, but doesn't seem the most likely that they were primordial. That is, they were made at the beginning. Mm-hmm. And in that sense, they could represent at least part of the dark matter. So there can be connections. Dark black holes are, how many there are, how much of the mass they encompass is still pretty primitive. We don't know.
So before I talk to you more about black holes, let me take a step back to, I went to high school in Chicago and would go to take classes at Fermilab, watch the buffalo and so on.
Yeah.